Hi everyone and welcome back to the channel. My name is Martin Yanev, a software engineer and a computer science professor at Fitchburg State University. And in this course, you are going to learn about the Zig programming language. Zig is one of the most modern programming languages that is a great alternative on C. It becomes more and more popular for embedded systems and system-level applications, so it is definitely worth it learning it. The full code for this video is going to be linked in the description. Make sure you subscribe my channel for more similar videos like this one. And now let's get started.
Zig is an exciting programming language that's gaining traction for its simplicity, performance, and safety. Today, we're embarking on a journey to explore the fundamental aspects of Zig programming. By the end of this session, you'll have a solid understanding of how to structure your Zig programs, including an important topic: documentation comments. Next, we will explore how to implement date and time manipulation in Zig. The code begins with a doc comment that succinctly describes the purpose of the module, providing functions for date and time operations. This is an important aspect, as it ensures that anyone reading the code can quickly understand its functionality. Now let's dive into the core of the implementation. The code imports the standard library using const std import std, which gives us access to a variety of useful functions and types provided by Zig's standard library. Following this, we define a public function named getCurrentDate, meant to eventually hold the logic for retrieving the current date. The function is declared with the void return type, indicating that it will not return any data once called, at least not in the current form. Currently, the function only contains a comment placeholder, denoting where the actual implementation will go. This structure allows for further development, making it easy to expand on the functionality in the future as you continue to build your date and time handling capabilities in Zig. Now let's see how we can implement a simple example showcasing an invalid doc comment in Zig. In this snippet, we begin by importing the standard library, which provides necessary functionalities to our program. Then we declare a constant named value and try to precede it with a doc comment that states, "This is an invalid doc comment." However, this placement of the doc comment is problematic because it's situated right before a non-doc comment. In Zig, it is crucial to place documentation comments strategically to maintain clarity and adhere to best practices. Instead of placing a doc comment after a declaration, it should ideally be placed before any declarations or definitions to avoid compiler errors. This reinforces the importance of understanding the structural rules in Zig. By learning these conventions, you gain insight into how to effectively document your code, which ultimately enhances its maintainability and readability for yourself and others. Properly placed documentation comments are essential for creating a clear and communicative codebase, which is one of Zig's core philosophies. Now let's see how we can declare variables in Zig, which allows us to define both the type and value of our data in a clear and concise manner. In the following example, we begin by importing the standard library, providing us access to useful functionalities such as printing to the console. Next, we define the main function, which is the entry point of our program. Within this function, we declare two constants: number, assigned the integer value of 42, and name, which is a string of characters representing Zig. When declaring the variable number, we specify its type directly as i32, indicating that it is a 32-bit signed integer. This clear typing helps Zig's compiler catch potential type-related errors at compile time, ensuring that our code behaves exactly as intended. Finally, we use the standard library's debug print function to output our variables to the console. By placing number name in the print statement, we seamlessly insert the values of our declared variables. This demonstrates the clarity and efficiency of Zig's variable declarations, significantly enhancing code readability and maintainability. Now let's see how we can implement a function that performs division while handling potential errors. The divide function is defined to accept two floating point parameters, numerator and denominator. It returns a special type called anyError f32, which indicates that the function can either return a floating point value or signal an error. Inside the function, we first check if the denominator is 0. If it is, the function returns an error defined earlier in the code, labeled as error. This practice of returning errors explicitly enhances clarity, making it evident that the division operation may not always succeed. If the denominator is not 0, the function proceeds to return the result of the division. This structure not only clarifies the expected output but also sets a foundation for robust error handling. It allows users of the function to actively manage potential errors rather than having them silently ignored, as is often the case in other programming languages. This is a powerful feature of Zig, enabling more predictable and maintainable code. Now let's see how we can implement error handling in Zig using the previously defined divide function. In this example, we are trying to divide the number 10 by 0, which is an invalid operation. The result of this division attempt is captured in the result variable, which can either hold a successful floating point value or an error. To effectively handle the potential outcomes, we employ a switch statement that evaluates the contents of result. If result contains an error indicated by the error case, our program will execute the corresponding branch, which prints a clear error message stating that the division failed. This approach allows users to understand what went wrong without crashing the program. Conversely, if the division is successful, the else branch is executed, displaying the computed result. This structure provides a robust way to manage both expected and unexpected scenarios seamlessly, showcasing Zig's emphasis on safety and clarity in error handling. Now let's take a look at how to work with arrays and slices in Zig. In the code, we begin by declaring a fixed-size array, which is a fundamental data structure that holds a predetermined number of elements. Here, we've created an array of 3 unsigned integers initialized with the values 1, 2, and 3. Next, we create a slice that references the entire array. This slice is significant because it allows us to interact with a subset of the array's data without copying it, enhancing performance. Slices provide a flexible way to manipulate data, letting you work with portions as needed. After defining these structures, we utilize the std debug print function to output the contents of both the array and the slice. This visibility into data allows us to see how the slice behaves in relation to the original array. With these tools, you can efficiently manage and access data, which is central to programming in Zig. Now let's take a look at how we can efficiently use slices in Zig to work with portions of an array. In this example, we define an array called numbers that contains 5 unsigned integers. By specifying a range, we create a slice from the original array that includes the elements from index 1 to index 4, effectively extracting a subarray that includes the values 2, 3, and 4. Next, we iterate over this slice using a for loop, which allows us to access each item in the slice sequentially. This approach emphasizes Zig's clean and expressive syntax, enabling you to focus on your logic without becoming overwhelmed by complex syntax. As we print each item in the slice to the console, this demonstrates not only how to manipulate array segments, but also how slicing promotes memory safety by preventing out-of-bounds access. By utilizing slices this way, you can handle data more flexibly and efficiently in your applications, showcasing one of Zig's standout features, a strong emphasis on both performance and safety in memory management. Zig is much more than just a syntax and a set of rules. It's about building a robust solution with an eye on performance and safety. As you continue your journey in programming with Zig, remember that every feature you learn interlocks with the concepts of clarity, performance, and safety. I hope you're as excited as I am about the power of Zig programming and its clean approach to both documentation and the overall structural integrity of code. Embrace the intricacies, keep practicing, and soon enough, you'll be adept at crafting elegant programs in Zig that are not only efficient but are also a joy to read. In this lesson, we are diving into some of the advanced features of the Zig programming language. We'll explore arbitrary bit width integers, algebraic data types, and more to enhance our understanding and capabilities with Zig. So far, we learned that Zig is a programming language focused on simplicity, performance, and safety, emphasizing the importance of properly placed documentation comments to ensure code clarity. We explored variable declarations, types, and error handling with examples, highlighting how to handle potential errors clearly and safely. Additionally, we covered data structures, particularly arrays and slices, showcasing Zig's efficiency in memory management and safety features. As we progress, we'll build on these foundational concepts, allowing us to write robust and efficient programs in Zig. Now let's take a look at how we can declare and utilize arbitrary bit width integers in Zig. The code begins by importing the standard library with import std, which provides essential functionalities for printing and debugging. In the main function, we define 2 constants, large int as a signed integer of 128 bits and large uint as an unsigned integer of 256 bits. These values are specifically chosen to exceed the typical 64-bit integer limits found in many programming languages, highlighting Zig's capability to handle significantly larger integers seamlessly. We then use std debug print to output these values to the console. The formatting string signed integer \n indicates where to place our large int variable, followed by another print statement for large uint. This code elegantly showcases the flexibility of arbitrary bit width integers, allowing us to work with high-precision values without the risk of overflow. Running this code will print the large integers accurately, demonstrating Zig's powerful capabilities for handling large numerical calculations, which can be particularly advantageous in areas such as cryptography or complex data processing. Now let's dive into an example that demonstrates addition and multiplication with arbitrary bit width integers in Zig. In this code, we declare two integers, num1 and num2. The variable num1 is initialized to a large value, specifically close to the maximum for a 64-bit integer, while num2 is assigned the value of 2. This allows us to explore arithmetic operations that can yield results exceeding conventional integer limits. Next, we'll perform two key arithmetic operations, addition and multiplication. We calculate the sum of num1 and num2, storing the result in a constant named sum, and similarly we compute the product of num1 and num2, storing it in product. Finally, we use Zig's debugging functions to print the results of these computations clearly to the console. This example effectively illustrates the flexibility and robustness of Zig when working with arbitrary bit width integers, showcasing how easily we can handle large numerical values while emphasizing the importance of Zig's error handling capabilities to manage potential overflow, thus ensuring the program operates safely and as expected. Now let's see how we can implement algebraic data types in Zig using a union that represents different geometric shapes. Here, we define a shape union that can either be a circle or a rectangle, each with its own properties. The circle struct contains a single field for the radius, while the rectangle struct has fields for width and height. In the main function, we create two instances of shape, one for a circle with a radius of 10 and another for a rectangle with dimensions 5 by 10. This structured representation not only organizes our data effectively, but also keeps related attributes together, enhancing code clarity. We then utilize Zig's standard library to print out the circle's radius and the rectangle's dimensions. The advantage of this approach is that it allows for cleaner, more maintainable code. When working with complex data, Zig's type system ensures that we retrieve or compute properties of each shape accurately, reducing ambiguity and improving robustness in our programs. This is the power of using algebraic data types in Zig. Now let's see how we can implement runtime checks to ensure our shapes have valid dimensions. In this code, we define a union type, shape, that can be either a circle or a rectangle, each with their respective properties. To validate the dimensions, we create a function called isValid, which uses a switch statement to determine the type of shape being passed. For each shape, it checks whether the radius for circles is non-negative, and both the width and height for rectangles are also non-negative. Within the main function, we create instances of a circle and a rectangle with specific dimensions. Notably, the rectangle has a negative width, which is invalid. We then call the isValid function for both shapes, and based on the return value, we output whether each shape is valid or invalid. If a shape is valid, we print its properties. Otherwise, we indicate that it's invalid. This approach demonstrates how runtime checks contribute to ensuring data integrity, especially when dealing with potentially unreliable external inputs or interactions with other systems, which is vital for developing robust applications. Now let's take a look at how we can leverage compile time evaluation in Zig to enhance our performance. In the given example, we declare a constant pi representing the mathematical constant for pi, and the function area of circle computes the area of a circle based on a specified radius. The beauty of this code lies in the ability to calculate the area using compile time expressions if we provide constant values, enabling Zig to optimize the computation even before the program runs. In the main function, we define a constant radius and set it to 10. We then call the area of circle function with this radius to get the area. Zig's std debug print function is used to output the result, neatly displaying both the radius and the computed area to the console. This approach demonstrates not only how to define and use functions in Zig, but also how to take advantage of compile-time optimizations that can lead to more efficient code execution, embodying what Zig aims to achieve with simplicity and performance. Such functionalities allow developers to build applications that run faster and with reduced overhead. By now, we've covered a wide array of advanced Zig features, from arbitrary bit width integers to algebraic data types, valid shape checks, and even compile-time performance optimizations. The versatility and simplicity that Zig brings to the table empower developers to create high-quality, efficient applications while minimizing the common pitfalls encountered in other languages. As you continue to work with Zig, I encourage you to experiment with these features. Break down complex problems into smaller parts, leverage the powerful type system, and always keep an eye on both performance and safety. Zig gives you the tools to build robust programs that are easy to maintain and understand. Thank you for joining me on this adventure through Zig's advanced capabilities. Keep coding, and I look forward to our next exploration together. Undefined behavior is a concept that every programmer must grasp, especially those who work with lower-level languages like Zig. When we say something is undefined, we mean that the value can be anything, even something nonsensical according to its expected type. This can have significant implications for performance, debugging, and the overall behavior of your programs. Today, we're going to unravel the mysteries of undefined behavior, explore its causes, illustrate with code examples, and discuss how to avoid pitfalls in your coding journey. Now let's take a look at how we can implement a simple division function in Zig that showcases the concept of undefined behavior. In this example, we define a function called divide that takes two integer parameters, x and y. The fundamental operation here is dividing x by y. However, a critical element to note is the check for division by 0. If y equals 0, we don't perform the division. Rather, we return 0 arbitrarily, which should ideally trigger a runtime error. This highlights a potential pitfall in error handling. Returning a fixed value in an erroneous situation might lead to confusion and undefined behavior later in the program. Next, we call this divide function with arguments 10 and 0. This deliberate choice of a 0 divisor leads us directly into the context of undefined behavior, as operations involving 0 and division must be handled with care. Understanding what happens at runtime is crucial, as different environments or compilers might react differently. Some could throw an error, while others might yield unpredictable results. This simple illustration emerges as a powerful reminder of the importance of robust error handling in programming to ensure the reliability of our applications. Now let's take a look at an example that demonstrates how accessing out-of-bounds elements in an array can result in undefined behavior. In this code, we start by importing the standard library in Zig, which gives us access to useful functions for debugging and other utilities. We declare an array, R, with a specified size of 3 elements containing the integers 1, 2, and 3. However, the line that follows attempts to access R3, which is beyond the bounds of the declared array. While the array is indexed from 0 to 2, attempting to access the fourth element, index 3, is a violation of the array's defined limits and results in trying to read data from an area that hasn't been allocated for our array. Fortunately, Zig incorporates runtime safety checks that will identify this out-of-bounds access. When this code is executed, Zig will catch this mistake and throw an error, preventing the program from crashing or behaving unpredictably. This highlights the critical need for safe indexing practices and careful array management to avoid the pitfalls of undefined behavior in programming. Now let's take a look at a function that exemplifies the risks associated with uninitialized variables in Zig. In this function, we declare a variable named uninitialized variable of type i32, but we do not assign it an initial value. This means that when we attempt to return this variable, we risk retrieving an unpredictable value, as it holds whatever data happened to be in that memory location at the time. Such behavior can lead to severe bugs, particularly in more complex programs where the output of this function might influence other operations or logic. It's crucial to understand that utilizing uninitialized variables is a common pitfall leading to undefined behavior, where the program behaves unexpectedly. In this example, we subsequently call our function within the std debug print statement to display the returned value, since we have not guaranteed that uninitialized variable contains a valid predetermined state. The output will be indeterminate. This reinforces the importance of always initializing your variables, as it ensures they start from a known state, thus contributing to safe and reliable code execution. Now let's take a look at how typecasting can lead to unexpected results in Zig. In this example, we start by declaring a variable num with a value of 300, which is of type i32. When we cast this integer to u8, we use the Zig function at int to int, which allows type conversion between integers of different sizes. However, it's crucial to remember that u8 has a maximum value of 255. This means that when we convert our variable num, the value exceeds the limit of u8 and will wrap around. The resulting value from this cast will not be the expected 300. Instead, it will yield a value of 44 due to this overflow. Such behavior illustrates the importance of understanding type ranges and the implications of improper casting. Following this, we print the result to the console. While seemingly innocuous, this incorrect casting can lead to serious logical errors in programs where numeric comparisons are made. Hence, it is vital to handle types carefully and ensure that we are always aware of their possible values to avoid undefined behavior in our applications. Now let's see how we can implement a scenario that demonstrates race conditions in concurrent programming using Zig. In this example, the function concurrent_access initializes a shared variable shared value to 0. The crucial part of this code is the spawning of two threads, thread 1 and thread 2, both of which are set to access and modify shared value. When both threads operate on the variable simultaneously, the operation shared value plus equals 1 becomes susceptible to a race condition. This means that if one thread updates shared value while the other is reading it, the outcome can lead to inconsistent or unexpected results. For instance, if both threads increment the value of shared value at the same time, there's no guarantee that the final value will accurately reflect both increments. It might only register one. To mitigate this issue, implementing synchronization mechanisms such as locks is essential. By controlling access to shared value, we can prevent the unpredictable behavior caused by simultaneous modifications. It's important to remember that concurrent programming requires careful handling of shared resources to ensure data integrity. The implications of undefined behavior stretch far and wide. Understanding the concept ensures better programming practices and safer code. But what's the takeaway? One of the key defenses against undefined behavior is thorough testing and the use of tools designed to catch potential pitfalls early in the development process. Zig provides features aimed at promoting safe programming. For example, compile-time safety checks can give you valuable information before you even execute your code. When you routinely perform checks and leverage Zig's safety features, you can mitigate undefined behavior risks. Here's a reminder tip: when coding, always consider what potential pitfalls exist and how to handle them appropriately. Whether it's by checking bounds, managing types properly, or ensuring thread safety, you build a more robust application. In conclusion, undefined behavior might seem intimidating at first, but grasping its principles is essential for writing high-quality, maintainable code in Zig. With clear awareness of the examples we discussed, you can navigate around these pitfalls. Keep in mind that safe coding practices not only lead to effective applications, but also save you from running into frustrating bugs down the line. As our programming journey continues, remember that every potential issue is just another opportunity for growth and learning in code mastery. Thank you for joining me today. Happy coding. Zig is a powerful programming language that emphasizes safety, performance, and simplicity. Today, we're going to delve into testing in Zig, a fundamental practice to ensure your code runs correctly and efficiently. We will explore the built-in testing framework, what Zig Test does, and how to write effective tests that can help maintain the reliability of your applications. So far, we have learned about undefined behavior in programming, particularly in the Zig language, emphasizing its implications on performance and reliability. We explored various causes of undefined behavior, such as division by zero, out-of-bounds array access, using uninitialized variables, improper typecasting, and race conditions in concurrent programming. Understanding these pitfalls and leveraging Zig's safety features such as compile-time checks can significantly improve coding practices. Now we will cover the importance of testing in Zig and how to effectively apply it in your projects. Now let's take a look at a simple example of a function in Zig that adds two integers and includes a test case to verify its correctness. The code begins by importing Zig's standard library, which provides essential functionalities. We then define a public function named add, taking two integer parameters, a and b, and returning their sum. This straightforward implementation ensures that we can efficiently add any two integers. Next, we want to ensure that our add function works as intended, so we write a test case for it. In Zig, test cases are defined using the test keyword, and we name our test add function. Inside the test, we call the add function with the arguments 2 and 3, storing the result in a variable. We then use Zig's built-in assertion function, std testing expect, to check if the result equals 5. This testing mechanism provides instant feedback. If the assertion fails, we know that there is an issue with our function. This approach not only aids in maintaining code reliability, but also cultivates good testing practices that help catch errors early in the development cycle. Now let's see how we can implement a function that handles division while properly managing potential errors. The divide function takes two integers, the numerator and the denominator, and utilizes Zig's error handling mechanism. If the denominator is 0, it returns an error, specifically error division by 0, to signal that this operation cannot be performed. This demonstration is crucial as it highlights the importance of anticipating edge cases in your functions. Next, we will write a test case to evaluate the functionality of our divide function. The test begins by attempting to divide 10 by 2, which is a valid operation. If an error occurs during this operation, we catch it, print an error message, and exit the test gracefully. This not only ensures that unexpected errors don't cause the tests to fail abruptly, but also provides useful feedback for debugging. Moreover, we'll also test the scenario where division by 0 is attempted. Here, we expect the function to return the division by 0 error. By explicitly verifying both the successful and erroneous cases, we reinforce the reliability of our code in handling various scenarios effectively. This comprehensive testing strategy helps maintain the integrity of our application, ensuring robust error handling. Now let's take a look at how we can implement a user management system with the ability to authenticate users. We begin by defining a user structure that includes fields for the username and password. This encapsulation allows us to represent users in a straightforward manner while maintaining their associated data. Within the user structure, we define a method called authenticate that checks if the provided password matches the user's stored password. This is achieved using Zig's memory comparison function, ensuring efficient and safe operations. Next, we will write test cases to validate the user authentication functionality. The test case named User Authentication creates an instance of user with a username and a predefined password. Here we utilize the std testing expect function to make assertions about the behavior of the authenticate method. The test confirms that calling authenticate with the correct password returns true, while calling it with an incorrect password results in a false outcome. This testing setup is essential as it not only verifies that our user structure works as intended, but it also helps ensure that components of our application interact correctly, promoting higher reliability in our user management processes. Now let's implement the following simple function and its corresponding test case. Here, we define a function called add that takes two integers as parameters and returns their sum. This is a straightforward implementation, making it easy to understand the fundamentals of function creation in Zig. Next, we will write a test case for our add function. It is essential to validate that the function behaves as expected, so we create a test labeled add function. Within this test, we call the add function with the values 2 and 3 and store the result. To verify that our function works correctly, we employ std testing expect, which checks if the result equals 5. If the test fails, Zig provides clear feedback, allowing us to quickly identify and address issues. Now let's see how we can benchmark the add function. In the benchmark section, we measure the performance by executing the add function 1,000,000 times using a loop. This benchmarking capability is vital for ensuring that performance remains optimal as we develop more complex applications, enabling us to catch inefficiencies before they become problematic. Now let's take a look at how we can implement a test for reading a file in Zig. In this example, we utilize Zig's std.fs file to open a file called testfile.txt for reading. We use error handling with the catch statement to gracefully manage the scenario where the file might not be found, avoiding abrupt test failures. Next, after successfully opening the file, we employ the defer keyword, which is crucial in resource management. By placing file close after the file opening, we ensure that the file will be closed automatically after the test case concludes, regardless of whether the test passes or fails. This practice prevents resource leaks and promotes clean code. Following this, we read the entire content of the file using read-to-end alloc, leveraging Zig's memory allocator. Again, we handle any potential reading errors. Finally, we assert that the file's content begins with the expected string using std, testing expect, providing a confirmation of the correct behavior. This structure not only ensures our test is thorough, but also showcases the importance of resource cleanup and error handling in testing scenarios. As we wrap up this lesson on testing in Zig, it's vital to remember the key message. Testing is not just a checkbox on your development process, but an integral part of building reliable software. By writing tests, you're investing in the long-term health of your codebase, making future changes safer and easier. We have covered a wide range of topics today, from writing simple tests for basic functions to more complex scenarios involving error handling and interactions between components. You also learned about the organization of test files and the significance of benchmarks and resource cleanup in ensuring tests run smoothly. As you continue your journey with Zig, keep in mind that adopting testing best practices will undoubtedly pay off, leading you to develop robust applications that stand the test of time. Thank you for joining me today, and happy coding. A variable is a fundamental concept in programming, especially when it comes to storing data. In essence, a variable is a unit of memory storage where you can hold different types of values. Think of it as a labeled box where we can put different items. Depending on what we store, we can manipulate or retrieve it later. Now let's take a look at a simple example of variable declaration and usage in Zig. In this code, we first import the standard library which provides various functionalities including input and output operations. We define a main function which serves as the entry point of the program. Within this function, we declare a mutable variable named age, specifying its type as an unsigned 32-bit integer and initializing it with a value of 30. This demonstrates how Zig allows us to create variables that can hold specific data types. Additionally, we declare a constant named name, representing a string, initialized to John Doe. The use of const indicates that this value cannot be altered, reinforcing data integrity throughout the program. Following the variable declarations, we employ std debug print to output the values of both name and age to the console. This illustrative example highlights how we can effectively manage and display variable content. Lastly, to showcase the mutability of age, we demonstrate how to update its value to 32, emphasizing the flexibility offered by variable manipulation in Zig. Now let's see how we can implement mutable and immutable variables in Zig. In this example, we start by importing the standard library which provides useful utility functions. We then define our main function where the execution of our code begins. Here we declare a mutable variable named count and initialize it with the value 10. This means we can change count throughout the program without any issues. For instance, we can simply add 5 to count, effectively updating its value to 15. On the other hand, we also declare a constant variable called limit and initialize it to 100. Unlike count, limit cannot be altered after its initial assignment, which ensures that its value remains fixed. If we attempt to change limit by adding 5, although it seems intuitive, doing so would cause a compile time error, demonstrating the enforcement of immutability with const. Finally, we use the standard library's printing function to output the values of count and limit. This example effectively illustrates the distinction between mutable and immutable variables in Zig, emphasizing how and when to use each type to enhance code reliability and performance. Now let's take a look at how local variables function in Zig. In the following code, we define a function called myFunction where a local variable named local_var is created. This variable is an integer type and is initialized to 5. Importantly, local variables have a limited scope. They can only be accessed within the function where they are declared. When we print the value of local_var, it displays 5, confirming that it operates as expected. However, if we try to access local_var outside of this function, the program will raise an error, illustrating the concept of variable scope effectively. Next, we will write the following code that introduces container-level variables. Here, we define a struct named container, which holds a variable value initialized to 42. This variable can be accessed throughout the program by creating an instance of container, as seen when we initialize myContainer with a new value of 50. When we print this value, we see it reflects the latest value assigned to it, demonstrating how container-level variables can be modified and accessed across various functions and instances, unlike local variables. This distinction is crucial for managing data and ensuring it remains accessible where needed. Now let's take a look at how we can implement thread local variables in Zig, which are essential for managing data in a multi-threaded environment. In our code, we define a variable thread_var as a thread local variable using the thread local keyword. This means that each thread created in our program will have its own unique instance of thread_var, preventing any race conditions that could arise from shared access to the same variable. Within the thread function, we increment thread_var by 1, demonstrating how each thread updates its individual instance independently. We then utilize std debug print to display the current value of thread_var, allowing us to see the effect of thread local storage in action. Next, we spawn two threads, thread 1 and thread 2, each executing the thread function. By joining the threads afterward, we ensure that the main function waits for both threads to finish before it concludes. This code illustrates the power of thread local variables in concurrent programming, where maintaining separate instances of data helps avoid data corruption and enhances overall program reliability. Now let's take a look at a simple example of variable declaration and usage in Zig. In this code, we begin by importing the standard library using the const std import std statement, which provides access to standard functions such as printing to the console. Next, we define the main function where we declare a variable named validIdentifier of type U32, representing an unsigned 32-bit integer. This variable is initialized with a value of 10, showcasing correct usage of identifiers. It's important to note that identifiers must begin with an alphabetic character or an underscore, as shown here. To reinforce the concept of variable naming, the code includes a commented out line that attempts to declare a variable with an invalid identifier. One invalid. Such a declaration will produce an error during compilation, highlighting the necessity for adhering to identifier naming conventions. This example emphasizes the significance of using valid identifiers when creating variables, and sets the foundation for understanding how to effectively name and utilize variables in your code. Now that we have established a foundation regarding how to declare variables, their types, and scope, let's conclude by emphasizing the importance of best practices. Using const when the value does not need to change, preferring meaningful names for your variables, and understanding variable scope and lifetime can lead to better, more maintainable code. Always remember that variables are the building blocks of your programs. Using them effectively can make the difference between a program that runs efficiently and one that's slow and cumbersome. As you continue to dive deeper into programming, mastering variables will serve as a critical step in your journey. This wraps up our discussion on variables in Zig. We've covered the essentials from declaration and usage to the importance of identifiers and scope. Next time, we'll explore more complex data types and how they can be leveraged for even greater control over data in our applications. Stay tuned for more exciting content. Now let's see how we can implement a player struct in Zig to illustrate the concept of container-level variables. In this struct, we define two variables, scar, initialized to 0, and level, starting at 1. These variables are container-level because they persist for the lifetime of the player instance created in the main function. Next, we provide two functions within the struct. The increaseScar function allows us to add points to the player's scar, while the levelUp function increments the level. Notice how these functions maintain the state of scar and level even after their execution, showcasing the advantage of using container-level variables. In the main function, we create a new player instance and call the increaseScar method to add 10 points, followed by invoking levelUp to increment the player's level. Finally, we utilize the standard debugging print functionality to display the updated values of the player's scar and level. This demonstrates how container-level variables can effectively retain and manipulate state across function calls in Zig, enhancing our programming capabilities. Now let's take a look at how we can implement a game config struct to demonstrate the characteristics of container-level variables, particularly their auto independence. In this example, the game config struct houses two container-level variables, sound-enabled and difficulty. The order of initialization does not impact functionality, as evidenced by the printConfig function, which accesses these variables regardless of when they were initialized. When we instantiate config as a game config, the default values are set for sound-enabled and difficulty. The role of the printConfig function here is to output the current state of these variables. After calling this function the first time, we change the difficulty variable to signify a transition to a harder game setting. This showcases how container-level variables can maintain their state and still be modified dynamically, reflecting their importance in maintaining configuration settings in a cohesive manner throughout the code. This approach underlines the benefits of organizing configurations within a struct, particularly for larger projects where multiple developers need to interact with shared settings reliably. Now let's take a look at how we can implement lazy analysis in our player struct to optimize performance. In this design, we introduce a variable called rank, which is not initialized during the creation of the player instance. Instead, we utilize a function called calculateRank that determines the player's rank based on their score, which enhances efficiency since the rank is only calculated when the score changes. This approach prevents unnecessary computations at startup, ensuring that resources are utilized effectively. For instance, when we update the player's score using the updateScore function, we both update the score and call calculateRank to reassess the rank accordingly. This means if a player only scores a few points and doesn't reach the thresholds for a higher rank, we avoid calculating potentially redundant ranks. Moreover, because the rank computation is executed conditionally upon score updates, it aligns perfectly with the principles of lazy evaluation. This way, we ensure that the player's state remains efficient and responsive, illustrating how container-level variables can be thoughtfully leveraged to maintain clarity and performance in code. Now, integrating advanced variable types with the standard practices we covered previously can lead to incredibly maintainable and efficient code. You can encapsulate not only data but behavior within your data structures, which leads to more organized code. Emphasis on clarity and purpose in your container-level variables can improve not just performance, but also collaboration among teams working on the same code base. To sum this up, understanding the implications of using container-level variables in Zig is crucial for any developer looking to write clean and efficient code. These variables enable referencing data that has a static lifetime and are flexible in terms of initialization order and efficiency due to lazy analysis. Whether you're building complex applications or simple scripts, these advanced variable types can help streamline your code while maintaining clarity. In conclusion, we have covered a lot today regarding advanced variable types in Zig, especially container-level variables. We explored the static lifetime, order independence, and the benefits of lazy evaluation. Utilizing these features properly can significantly enhance the efficiency, maintainability, and clarity of your code, making your journey into programming with Zig all the more powerful. Keep experimenting with these concepts in your projects, and happy coding. Zig is an exciting language that keeps things straightforward, especially when it comes to operators. Today, we'll dive deep into the realm of operators in Zig, understanding their functionality and usage without any operator overloading. That means when you pick a Zig operator, you know exactly what it's doing and where it stands. So far, we have covered advanced variable types in Zig, focusing on container-level variables, their characteristics, and how they optimize resource usage in our code. Now, we will explore operators in Zig, how they work, and the various types available, enhancing our understanding of this efficient programming language. Now let's see how we can implement a basic addition operation using Zig. In this example, we start by importing the standard library which provides essential functions for input and output. We define the main function, the entry point of our code, where we declare two constant integers, a and b, and assign them the values 5 and 7 respectively. Next, we compute their sum using the plus operator, storing the result in a variable named sum. This usage of the addition operator demonstrates Zig's straightforward approach to arithmetic, ensuring clarity and predictability in operations. Finally, we utilize the std debug print function to display the result. The placeholder allows us to insert the computed sum into the output string, effectively showing 5 plus 7 equals 12 on the screen. This simple yet effective example highlights how easily Zig handles basic operations, reinforcing the language's commitment to simplicity and readability, which makes it an excellent choice for developers aiming for efficient and understandable code. Next, we will write the following code to demonstrate subtraction in Zig. We begin by declaring two constant integers, a and b, with values 10 and 4 respectively. The code uses the subtraction operator to compute the difference between these two constants, storing the result in the variable difference. This showcases how straightforward and predictable arithmetic operations are in Zig. After performing the subtraction, we use the std debug print function to output the result in a formatted string. The format specifier is used to insert the computed difference into the string, resulting in the output 10 4 equals 6 when the program runs. This example illustrates not only the basic usage of the subtraction operator, but also how Zig's debug print function helps present the results clearly. By observing this, you can see how simple and effective arithmetic operations are in Zig, enhancing our understanding of the language's design focused on clarity and reliability. Now let's see how we can implement multiplication in Zig using the asterisk operator. In this example, we first import the standard library which provides essential functionalities. We define a main function where two constant variables, a and b, are initialized with the values 6 and 7 respectively. We then calculate the product of these two numbers by multiplying them, storing the result in the variable product. The use of the multiplication operator is straightforward, reflecting its conventional mathematical usage. Finally, we utilize std debug print to output the result in a formatted string showing the multiplication equation clearly. Next, we will write the following code to demonstrate division using the slash operator. Similar to before, we declare two constants, a and b, assigned with the values 56 and 8. We compute the quotient and store it in the variable quotient. Just like multiplication, division is performed seamlessly in Zig. The key aspect to highlight is that Zig will raise an error if division by 0 is attempted, emphasizing the language's robust error handling. Finally, we print the result in a formatted string, ensuring clarity in the output as we continue our exploration of arithmetic operations in Zig. Next, we will explore the modulo operator %, which is essential for obtaining the remainder of a division operation. Now let's implement the following code to see how it works in Zig. We begin by declaring two constants, a and b, with values 15 and 4 respectively. The expression a %b calculates the remainder when 15 is divided by 4. In this case, 15 divided by 4 equals 3 with a remainder of 3, which is exactly what the modulo operator is designed to return. After performing the operation, we store the result in a variable called remainder. To display the outcome, we use Zig's standard debugging functionality to print out the result formatted as 15% 4 equals remainder. This clear output illustrates how the modulo operator functions and its utility in determining values, such as whether a number is even or odd. Understanding and implementing the modulo operation expands your arsenal of tools within Zig, allowing you to tackle a variety of problems efficiently. Now let's see how we can implement a bitwise AND operation in Zig using the AND operator. In this example, we first declare two unsigned 8-bit integer constants, a and b, assigning them the binary values 0b1100 and 0b101010 respectively. The bitwise AND operation will compare the bits of these two numbers. Next, we perform the operation and store the result in a constant named result. The expression a and b evaluates each pair of corresponding bits from a and b. If both bits are 1, the resulting bit in result remains 1, otherwise it is set to 0. To visualize the outcome of this operation, we use the std debug print function which outputs the binary representation of the result. The specific format, b, ensures that the output is displayed in binary, allowing us to see clearly how the operation was conducted. The expected output will be 0b1100 and 0b101010 equals 0b1000, demonstrating the bit comparison logic applied during the AND operation. This showcases the clear and predictable behavior of bitwise operations in Zig, reinforcing the language's focus on straightforward coding practices. Now let's explore the bitwise OR operation in Zig. In our code, we begin by importing the standard library, which allows us to use important functions like std debug print for output. We define two constant 8-bit unsigned integers, a and b, initialized with the binary values 0b1100 and 0b101010 respectively. The OR operator will allow us to combine these two binary numbers. When we perform the operation a b, we compare each bit in the two operands. The result is a new binary number where each bit is set to 1 if at least one corresponding bit in the operands is 1. This results in the binary output of 0b1110 1110. Finally, we use std debug print to format and display the result, clearly demonstrating how the OR operation functions visually. By running this code, you can see firsthand how bitwise operations work, providing a powerful tool for manipulating data at the binary level. This behavior emphasizes the efficiency and predictability of operators in Zig, making bitwise logic straightforward and easy to understand. Now let's take a look at the bitwise XOR operator, which is represented by the caret symbol. This operator is particularly interesting because it returns a 1 in the resulting binary number wherever the corresponding bits of the two operands differ. In the code, we declare two constants, a and b, initialized to binary values 0b 1100 1100 and 0b 10 10 10 10, respectively. By using the XOR operator, we are able to compute the result of a b where each pair of bits is evaluated. If the bits are different, the result is 1, otherwise it is 0. Once the computation is complete, we can see the output printed in binary format using Zig's standard debugging function. This showcases how the XOR operation operates on the individual bits of the two numbers to yield a new binary number. The result in this case, 0b 110 110, clearly illustrates the behavior of the XOR operator, making it a powerful tool, for instance, in situations requiring toggling bits or checksums in data. Understanding how to effectively apply this operator can enhance your ability to manipulate binary data in Zig efficiently. Now let's take a look at how to perform bit shifting, which is an important operation that allows us to manipulate the binary representation of numbers by moving bits left or right. In this example, we start by defining a constant a with a binary value of 0b 1 1100, which is the binary representation for the decimal number 28. Next, we use the left shift operator to shift the bits of a to the left by 2 positions. This operation effectively multiplies the original number by 2 raised to the power of the number of positions shifted, in this case, multiplying by 4. The result of this operation is stored in the shifted variable, and we then print out the result formatted as a binary string. Here, the output shows that shifting the original number left by 2 places produces 0b 1110 0, which equals 112 in decimal. This demonstrates not only how bits are moved but also how bit shifting relates directly to multiplication, showcasing a powerful and efficient way to perform calculations in binary without using multiplication operators. Now let's take a look at how to perform right bit shifting in Zig using the operator. This operator allows us to shift the bits of a number to the right, effectively dividing the number by 2 for each shift position. In this instance, we start with the binary representation of 0b 1 1100, which is the decimal number 28. By applying the operator to this value with a shift amount of 2, we are moving each bit 2 positions to the right. This action transforms our original number into 0b0111, which, as a result of the bit shift, is now equal to the decimal number 7. This operation is particularly important in various algorithms and optimizations because it directly manipulates the binary data, offering significant performance advantages in scenarios where efficiency is paramount. Finally, the print function in our code showcases the outcome, demonstrating how the right shift syntax works in practice while providing clarity in how shifts operate, emphasizing the predictable nature of operators in Zig. Now let's take a look at how we can implement logical operators in Zig to make decisions based on Boolean values. In this example, we declare 2 Boolean constants, a which is set to true and b which is set to false. We then utilize the logical and operator to evaluate these 2 conditions. The expression a and b checks if both a and b are true. After the evaluation, the result of this operation is stored in the constant result. To provide feedback on the outcome, we use std debug, print to output the phrase true and false equals followed by the value of result. In this case, since both conditions need to be true for result to be true, the output will indicate that the result is false, demonstrating how logical operators can streamline decision-making in your code. This functionality not only enhances code clarity but also reinforces the importance of Boolean logic in programming, allowing us to control the flow of our applications effectively. Now let's examine the OR operator in Zig, which is used to evaluate logical conditions. In the following code, we declare 2 Boolean constants, a set to true and b set to false. With the OR operator, we combine these 2 conditions to determine the overall result. The logical OR will return true if at least one of the conditions is true. In this case, since a is true, the result of the expression OR b evaluates to true. We then utilize Zig's built-in debugging function to print the result in a formatted string. the output will clearly display true or false equals true, illustrating the characteristics of the OR operator. This example emphasizes the straightforwardness of logical operations in Zig, where the expectation aligns with the actual behavior. By using clear Boolean expressions, we can easily manipulate conditional logic, thus enhancing our programming efficiency and readability. This contributes to writing clean and concise code, a crucial aspect of the Zig language's design philosophy. Now let's take a look at the negation operator in Zig, which is represented by the exclamation mark. In our example, we begin by importing the standard library and defining the main function where we declare a constant Boolean variable, initialized to true. The key operation takes place when we introduce another constant, negated, which applies the negation operator to a. This action flips the true value of a to false, showcasing the fundamental operation of negation in Boolean logic. To illustrate this concept, we then utilize the std debug print function to output the result of our negation operation. The formatted string displays not true equals false, demonstrating the straightforward nature of the not operator. This operation is critical in controlling program flow based on conditions, allowing developers to effectively manage decision-making processes. With this simple yet powerful operator, you gain the ability to invert Boolean expressions throughout your Zig programs. As we conclude our deep dive into operators in Zig, it's evident that this language emphasizes clarity and directness. Operators function consistently, allowing programmers to write code that is easy to read and understand. Zig ensures that you don't have to worry about the unexpected behavior that might confuse you in other languages, especially with operator overloading, which simply doesn't exist. We have covered a great deal today, from basic arithmetic operators to bitwise and logical operators, highlighting the ease of use and predictability of Zig. Despite the simplicity, these operators allow for elegant and expressive code that executes efficiently. Remember, when you see an operator in Zig, it's doing something defined in its reliable table of operations. We can all appreciate that. Every aspect of this operator system promotes better coding practices and understanding of underlying processes, which ultimately makes for robust software development. Happy coding! Floating point operations are crucial in programming, especially when dealing with real numbers and requiring a high degree of precision. In Zig, floating point operations are designed to be both efficient and predictable, with a feature that enables developers to switch between strict and optimized modes depending on their needs. So far, we learned about the exciting programming language Zig, focusing on its straightforward approach to operators. We explored various operators, including arithmetic, bitwise, and logical operators, highlighting their predictable behaviors and efficient usage in code. Understanding these operators enhances our coding practices and promotes clarity in programming. Zig's emphasis on simplicity aids developers in writing elegant and efficient code, without the complications of operator overloading. Now we will talk about advanced floating point operations in Zig and how to utilize strict and optimized modes effectively. Now let's see how we can implement a straightforward addition of two floating point numbers in Zig. The code begins by importing the standard library, which provides useful functions for debugging and other operations. In the main function, we declare two constants, x and y, both of type F64, which is a double precision floating point type. We assign 1 to x and 2 to y. The operation we are interested in is the addition of these two values. By declaring another constant result, we store the sum of x and y. Lastly, we utilize the std debug print function to output the result of the addition, demonstrating how Zig's strict mode governs these operations, ensuring that we obtain the expected output of 3. This simple code effectively showcases how Zig handles floating point arithmetic while following the IEEE 754 standard, thereby highlighting the importance of precision and predictability in calculations. Now let's see how we can utilize Zig's optimized mode for executing floating point operations efficiently. In this example, we define a function called optimized operations. Inside this function, we declare two floating point constants, x as a large number 1e10 and y as a very small number 1e10. We employ an inline loop that executes twice, where each iteration performs different computations. The first iteration adds x and y, while the second subtracts y from x. By handling the operations in optimized mode, Zig is configured to enable faster execution of these calculations, which is particularly advantageous in performance-critical applications such as graphics rendering or real-time physics simulations. To observe the results, we use std debug print, which will output the results of our calculations, indicating which block was executed and displaying the resulting value. This approach highlights how switching to optimized mode can not only enhance speed but also streamline feedback during testing, particularly when handling large datasets or complex numerical calculations. Finally, in the main function we call optimized operations, invoking our defined computations and showcasing the efficacy of optimized floating point arithmetic in Zig. Now let's take a look at how floating point precision can be tested through a simple multiplication operation in Zig. In this example, we define two constants, small set to a very small value of 1e10 and large set to a very large value of 1e10. By multiplying these two numbers, we aim to observe how floating point arithmetic handles this scenario. Here, the result of the multiplication is assigned to the product variable, which could lead to potential precision issues. When printed, this result might yield 1 instead of the anticipated output of 1e0. This discrepancy occurs due to the limitations of floating point representation in handling extreme values, illustrating the critical importance of understanding precision in calculations. By running this code, you will see firsthand how Zig's default strict mode helps to catch such precision-related issues. It's particularly insightful, as the behavior highlighted here emphasizes the necessity to consider floating point representations carefully, especially in applications where accuracy is paramount. Understanding these challenges will guide you in structuring your calculations more effectively as your needs evolve. Now let's see how we can handle division by zero in Zig, which demonstrates the language's robust handling of special floating point values. In the following code, we define two variables, a and b, where a is set to 1 and b to 0, 0. The crux of this demonstration lies in the division operation where we divide a by b. It's important to note that this calculation would normally lead to a division by zero, a common source of runtime errors in many programming languages. However, Zig gracefully handles this situation by returning positive infinity in accordance with the IEEE 754 floating point standard. The output is printed to the console, providing clear feedback of the operation's result. This behavior ensures that the program does not crash and instead continues executing, which is crucial for applications where stability is paramount. By leveraging Zig's capabilities in managing such scenarios, developers can create algorithms that can confidently handle unexpected inputs or calculations without compromising reliability or performance. This feature is vital in scientific computations and other critical applications where precision and consistency are essential. Now let's take a look at how we can examine the precision of floating point operations in Zig through incremental increases. We will write a simple program that starts from 0 and adds a very small value, specifically 1e10, in a loop running 100 times. In this example, we define a variable number initialized to 0, 0, and each iteration of the loop increments number by the increment value. As we execute the loop, we print the current index and the resulting value of number after each addition. By doing this, we can observe how the results evolve as we continue to add a small increment to a larger value. It's critical to recognize that, due to the limitations of floating point precision, the output may diverge from our expectations as number grows. This exercise reinforces the necessity of being aware of precision issues that can affect calculations in real-world applications and encourages students to code with a discerning perspective towards floating point arithmetic. Understanding such nuances is essential to ensure accuracy and reliability in software development. Now let's take a look at how to perform rounding operations on floating point values in Zig. In this specific code snippet, we begin by importing the standard library, allowing us to utilize various functions and features provided by Zig. We define a floating point variable called value, initialized to 2.7. Using the std_math round function, we round this value to the nearest integer, assigning the rounded result to rounded value. Next, we use std_debug print to output the value of rounded value. When we run this code, it demonstrates the rounding functionality effectively, producing the output rounded value 3, 0. This showcases how Zig's math capabilities can enhance your application by controlling the precision of floating point calculations. Furthermore, rounding operations are integral when dealing with real numbers, as they can dictate how results are interpreted and manipulated within the context of your application. This flexibility allows developers to tailor their mathematical operations based on specific needs, leveraging the robustness of Zig's features for improved numerical handling. Now let's take a look at a practical example of comparing floating point numbers in Zig, which is crucial due to the inherent precision issues that arise in floating-point arithmetic. We begin by defining a function called requal, which takes two floating-point numbers and a small margin known as epsilon. This epsilon serves as a threshold for determining whether the two numbers can be considered equal. The function calculates the absolute difference between the two numbers and checks if this difference is less than epsilon, thereby allowing us to account for minor discrepancies that often occur in floating-point calculations. Next, we implement the main function where we define two floating-point numbers, a and b, that are very close in value along with a defined epsilon. By utilizing the requal function, we can effectively compare these two values. Depending on the outcome of this comparison, the program will either print a message indicating that the values are considered equal, or it will state that they are not equal. This comparison approach is essential for developers to ensure that their floating-point operations remain reliable, even when dealing with very small differences. In conclusion, understanding advanced floating-point operations in Zig allows developers to handle real numbers with confidence and control. From determining when to use strict versus optimized mode, to recognizing the challenges posed by precision, zeros, and special values, Zig empowers you with the tools necessary for ensuring the integrity of your calculations within your applications. Embracing the nuances of floating-point arithmetic will not only enhance your coding practice, but also solidify your applications, reliability, and efficiency. So next time you encounter floating-point math, remember that Zig's got your back, whether you're rigorously adhering to standards in strict mode or speeding through your calculations in optimized mode. Happy coding and keep exploring the exciting world of Zig. Arrays are a fundamental aspect of programming that allow you to store multiple values in a single variable. They are like libraries in which you store various books, but here, each book can be a piece of data. In Zig, an array is declared using a specific syntax that not only creates a list of values but also provides efficient access to those values. Now let's take a look at a basic array declaration in Zig. Here, we create an array named message that consists of 5 elements, each of type U8, which represents an unsigned 8-bit integer, commonly known as a byte. This particular declaration utilizes a special syntax where the size of the array is inferred at compile time, indicated by the notation. Inside the braces, we populate the array with a list of characters, H, E, L, L, and O, which together spell the word hello. This approach not only initializes the array but also ensures that all its elements are of the same data type, ensuring type safety, one of the key benefits of using arrays in Zig. By embedding the characters directly, we achieve a concise representation of string data as an array of bytes, which can be manipulated efficiently. This method is beneficial for not only storing textual information but also for operations requiring raw byte manipulation, showcasing the versatility and power of array declarations in Zig. Now let's see how we can implement a fixed-size array directly in Zig. The code defines an array named alt_message, which is explicitly sized to hold 5 elements of type U8, representing unsigned 8-bit integers or bytes. The array is initialized using .syntax, a method that clearly indicates the intended length. Each element is assigned a byte value that corresponds to the ASCII characters of the word hello. Using a fixed size for the array enhances readability, making it immediately clear to anyone reading the code exactly how many elements the array will hold. An advantage of this declaration style is that it helps ensure that the array remains consistent in size throughout the program, preventing potential out-of-bounds errors when accessing its elements. Both this declaration and the previous one demonstrate the principle that all elements within an array must be of the same data type. This structured approach allows for efficient memory management and data handling within Zig, which is essential for effective programming. Now let's see how we can ensure that our array declarations meet specific expectations at compile time. In this snippet, we utilize the assert function within a comptime block to verify the length of our previously declared message array. Specifically, we check that message.len equals 5, which corresponds to the number of elements we initialized it with. This approach serves as an important debugging tool, allowing us to catch potential errors during compilation rather than at runtime, ultimately enhancing code safety and reliability. By employing assertions like this, you can ensure your arrays have the correct dimensions before proceeding with further manipulations or operations, thereby preventing out-of-bounds errors which can occur if the array is accessed incorrectly. It reinforces good programming practices in Zig as it promotes cautious, mindful coding habits while developing. In effect, this line not only checks for correctness but also documents the expected size of the array, encouraging clearer, more maintainable code. Now let's take a look at how Zig handles string literals and their interaction with arrays. In the presented code, we declare same message as a string literal set to hello. String literals in Zig are distinctive because they refer to arrays of bytes that are generated implicitly by the compiler. The following block, wrapped in a comptime section, allows us to perform compile-time assertions which help validate our assumptions during development. Here, we utilize the assert function, which compares the memory contents of message, an explicitly declared array of bytes representing hello with same message. By using mem_equal, we check if these two entities point to the same underlying data in memory. This reinforces the concept that even though strings and arrays are different constructs, they can seamlessly interact under the hood. This duality is crucial for debugging, ensuring precisely that the expected values align, thus helping to catch potential errors early in the development phase. Through these mechanisms, Zig effectively illustrates how strings can be treated as arrays, demonstrating flexibility in handling character data. Now let's see how we can implement a function to iterate over the message array and calculate the sum of its byte values. The code begins by defining a test function named iterate over an array. Inside this function, we initialize a variable called sum to 0, which will hold the cumulative total of the byte values. Next, we utilize a for loop to traverse each byte in the message array. Within the loop, the variable byte represents the current element we are processing in that iteration. The sum is updated by adding each byte's value to the total using the += operator. After completing the loop, we include an assertion to verify our calculation. This assertion checks if the computed sum equals the ASCII values of the characters forming hello, where L is counted twice. This line not only serves as a validation step but also illustrates the efficiency of managing arrays, demonstrating how we can perform bulk operations seamlessly while ensuring our calculations align with the expected outcomes. Through this example, we emphasize how arrays provide powerful tools for manipulating collections of data effectively in Zig. Now let's take a look at how we can declare a modifiable array and initialize its elements in Zig. The first line of code constructs an array named SumIntegers, which is specified to hold 100 integers but is initially set to undefined, indicating that it hasn't received any values yet. This presents an opportunity for us to fill it with data through iteration. Next, we define a test function called modify an array. In this function, we iterate through the SumIntegers array using a for loop where each element can be modified in place. The use of and before SumIntegers allows us to access the pointers to the array's items directly. Within the loop, we assign each element the value of its index I, while casting it to I32 with @intCast I. This ensures that the data type remains consistent. Finally, we use an expect statement to verify that the 10th element of the array indeed holds the value 10, confirming that our initialization was successful. This example illustrates both the mutability of arrays and the importance of type safety in Zig programming. Now let's examine how we can concatenate arrays in Zig, which is a powerful feature that enhances the language's flexibility. First, we declare two arrays named part1 and part2, each containing a set of integers. The ++ operator is then used to combine these two arrays into a new array called all of it. This operator allows us to merge arrays explicitly at compile time, enabling the creation of composite data structures without additional overhead. To ensure that our concatenation is functioning correctly, we include a compile-time assertion using the assert function. This statement checks that the contents of all of it match a predefined array containing the expected combined values. By utilizing assertions and compile-time checks, we can confidently verify that our code behaves as intended, minimizing potential errors during runtime. This approach of array concatenation is particularly useful for developers who wish to build more complex data structures while maintaining clear and efficient code. Now let's see how we can repeat elements within an array using Zig syntax. The code creates a constant variable named pattern, where the string ab is repeated 3 times through the use of the *** operator. This results in the string ababab. By using the *** operator, we can streamline our code when working with repeated patterns, making it not only more concise but also enhancing its readability, which is crucial for maintenance and collaboration. Furthermore, the comptime block ensures that this assertion is checked at compile time, confirming that the generated array indeed matches the expected string ababab. This is an effective way to catch errors early in the development process. By understanding this functionality, you can leverage Zig's powerful capabilities to simplify your code while maintaining strong type safety. ultimately improving both your programming approach and the performance of your applications. Now let's take a look at how to initialize an array to a specified size filled with zeros, a common requirement in many programming scenarios. The code snippet demonstrates the declaration of an array named all0, which is defined to hold 10 elements of type U16. By using the syntax U16 0*10, we are effectively instructing Zig to create an array of 10 U16 integers, all initialized to 0. This method is particularly useful for preparing data structures like buffers before their actual usage, ensuring that they contain no random or undefined values. Instead, every element in the all0 array is explicitly set to 0. To confirm that our array has been created correctly, the following assertions check its length and validate that the sixth element, index 5, is indeed 0. This type of initialization not only enhances data integrity, but also aids in debugging and reduces potential errors caused by uninitialized memory, making it a best practice to adopt in various programming tasks. Now let's take a look at how to create and manipulate multidimensional arrays in Zig. In our example, we define a 4x5 matrix of floats named mat4x5. This is done by nesting arrays where each row of the matrix is defined as an array of 5 F32 values. This structure is particularly useful for various applications, such as representing mathematical data, grids, or images. Next, we implement a test to access elements in this two-dimensional array. We check if the value at the position 34 equals 9.9, demonstrating how to access specific elements directly using their indices. Additionally, we iterate over each row of the matrix and its corresponding cells using nested loops. Here, a conditional check compares row and column indices, asserting that diagonal elements, where the row index matches the column index, are equal to 1, 0. This reinforces an understanding of how to traverse and manipulate multidimensional arrays effectively. By mastering these techniques, you'll enhance your ability to manage and represent complex datasets efficiently in your Zig programs. Now let's take a look at a practical application of array destructuring in Zig. In this example, we define a function named swizzle RGBA to bgra, which takes an RGBA color array consisting of 4 U8 elements representing red, green, blue, and alpha values. The beauty of destructuring is showcased here as we unpack the array directly into individual variables, A, G, B, and A. This not only streamlines our code but also enhances readability, allowing us to refer to each color component succinctly. Next, we return a new array structured as bgra, where the elements are reordered to place blue first, followed by green, red, and finally alpha. This function is particularly useful in graphics programming, where different color formats may require data to be reorganized for compatibility with various systems or frameworks. By understanding and utilizing array destructuring, we can make our code cleaner and more efficient, minimizing potential errors associated with manual indexing. This approach exemplifies how Zig's array features can facilitate effective data manipulation in a clean and approachable manner. Finally, understanding improper access patterns is vital when working with arrays. Zig will enforce the type safety, which dramatically reduces runtime errors and ensures that your array manipulation is safe and predictable. In summary, arrays in Zig provide a powerful, flexible way to manage data in programs. You can declare them in several ways, iterate over them, concatenate them, and even nest them for multidimensional constructs. We've covered how to declare, modify, and make use of arrays efficiently, enhancing your coding toolset for upcoming projects. The next time you need to manage collections of data, remember the power of arrays in the Zig programming language. Let's dive into advanced array manipulation in the Zig programming language. This lesson is particularly exciting because we'll explore how to initialize arrays using function calls, among other powerful techniques. So far, we learned about the importance of arrays in programming, particularly in the Zig language, where they allow for efficient storage and manipulation of multiple values. We discussed how to declare arrays, access their lengths, and perform operations such as iteration, modification, and concatenation. Additionally, we explored advanced features like repeating patterns and multidimensional arrays. Overall, understanding arrays significantly enhances your ability to manage data structures effectively in your programs. Now, we will focus on initializing arrays using functions and more advanced manipulations. Now let's see how we can define a simple structure to hold our data points in Zig. We start by creating a struct called point, which contains two integer fields, x and y, representing the coordinates. This allows us to encapsulate the coordinates effectively and prepare for filling an array with multiple instances of point. Next, we will implement a function named makePoint. This function takes an integer input for the x coordinate and computes the y coordinate by doubling the value of x. It returns a point instance with the appropriate values. This function encapsulates the logic for initializing our points, showcasing how function calls can help maintain clean and reusable code. Now let's see how we can populate an array using our makePoint function. By employing the array repeating pattern syntax, we create an array called maPoints, which contains 10 identical point instances, all initialized with x set to 3. This use of array initialization demonstrates the efficiency of using function calls to construct arrays while maintaining clarity. Finally, we validate that our points were correctly initialized by checking the expected values for one of the elements and confirming the array's length. Now let's see how we can implement compile-time array initialization in Zig, which demonstrates how to optimize data structures directly at compilation. We start by using a labeled block called init, where we define an array called initialValue to hold 10 point instances, though they are initially undefined. The power of compile-time evaluation is showcased through the loop that iterates index values from 0 to 9. During each iteration, we access a pointer to the current point and assign the x coordinate as the loop index while setting the y coordinate to be double that index. This method not only simplifies the logic for populating the array, but also leverages compile-time code execution for enhanced efficiency. The use of a break statement concludes the initialization block, allowing us to return the fully populated array. To ensure our implementation works correctly, we validate it through a test that checks if the fourth element in the array has the expected x and y values, confirming that they are initialized accurately. With this technique, we gain valuable insights into optimizing data setup through compile-time calculations, which can significantly enhance performance in Zig. Now let's take a look at how we can perform element-wise transformations on an array in Zig. In this example, we start with an array of integers named original, which contains the values from 1 to 5. Next, we declare an empty array called squared that is set to hold the squared results of each element in the original array. To achieve this transformation, we use a for loop that iterates over the original array. Within the loop, we utilize destructuring to capture each number, num, and its index, ix. For each iteration, we calculate the square of num by multiplying it by itself, and then assign this value to the corresponding index in the squared array. This direct mapping not only keeps our implementation straightforward but also clarifies our intention to convert each number into its square. Finally, to verify that the transformation has been executed correctly, we employ several expect statements to assert that each element in the squared array matches the expected squared values, ranging from 1 to 25. This method effectively showcases how Zig facilitates clean and efficient data transformations through loops. Now let's take a look at how to work with a 2D array in Zig, which is particularly useful for handling matrices. We first define a 4x5 matrix named mat4x5, where we initialize it with specific float values. Each row of this matrix contains 5 float elements, allowing us to represent complex data like mathematical matrices efficiently. The unique syntax used ensures that we maintain clarity and structure in our array initialization. Next, we will test our matrix to confirm that we can accurately access its elements. We write a test that attempts to retrieve the value located in the 4th row and 5th column, which we expect to be 9, 9. Additionally, we'll implement a nested loop to traverse each row of the matrix. Within this loop, when the row index matches the column index, we will check that the diagonal elements equal 1, 0. This not only verifies our data structure's integrity, but also reinforces the importance of accessing and manipulating elements in multidimensional arrays effectively. Overall, this example demonstrates the critical principles of 2D arrays, including initialization and element access, showcasing their utility in programming. Now let's take a look at how we can rearrange color values using an advanced method called destructuring in Zig. In the code, we define a function named swizzle_RGBA to bgra, which takes an array of 4 unsigned 8-bit integers representing RGBA values. By utilizing destructuring, we extract the individual components, red, green, blue, and alpha, from the input array with a simple syntax that enhances readability. The magic happens in the return statement, where we create a new array reflecting the BGRA order instead of the conventional RGBA. This allows for an efficient transformation of color formats without manually accessing each index of the array. The clarity of our code is greatly improved by destructuring, making it immediately apparent what each component corresponds to and how they are rearranged into the new format. This technique is particularly useful in graphics programming when working with color data that may need to be adjusted for various rendering systems. In essence, this function illustrates how to use destructuring not only to simplify access to array elements, but also to enhance the overall efficiency and expressiveness of your code. Now let's put all of this into practice with an overall summary of our learning journey today. We explored advanced aspects of array manipulation in Zig, focusing predominantly on initialization via functions and compile-time coding techniques, which allows for elegant and efficient programming. We discussed element-wise transformations on arrays and dug deep into multidimensional arrays to understand their structure and accessing methods. Finally, we touched on destructuring, demonstrating how it can be utilized to work with data in a more intuitive way. Understanding the various ways to manipulate arrays will empower you as a programmer, providing you with versatile tools to handle complex data structures effectively. The skills acquired in this lesson will not only improve your coding skills in Zig, but also enhance your overall problem-solving abilities in programming. Keep experimenting with these techniques, and in no time, you'll become adept at handling arrays like a pro. Zig programming language introduces a powerful and unique concept of pointers that significantly enhances the way we handle memory and data structures. In this session, we'll unpack what pointers are, diving deep into the two types Zig offers: single-item pointers and many-item pointers. These concepts will be illuminated through examples and detailed explanations, allowing you to grasp how to use pointers effectively. So far, we covered advanced array manipulation in Zig, enhancing your ability to manage complex data structures. Now we will talk about pointers, understanding their syntax, how to declare and dereference them, and the differences between single-item and many-item pointers. Now let's take a look at a simple example that illustrates how to declare and use a pointer in Zig. In this code, we start by defining an integer variable x and initialize it with the value 10. The key part of this example is the declaration of the pointer p, which is created to store the address of x. This is accomplished using the AND operator, which retrieves the memory address of the variable x. Now p holds this address, allowing us to manipulate the variable x indirectly. Next, the code demonstrates how to access the value of x through the pointer p. By using the asterisk operator, we can dereference p, which gives us the value stored at the address it points to. The program then prints out the value of x, its address, and the value accessed through the pointer, illustrating how pointers provide a way to reference and modify variables in memory effectively. This functionality is particularly useful in more complex structures where direct access may not be feasible. Now let's take a look at how we can work with optional pointers in Zig. In the following code, we define a nullable pointer x, which is initially set to null. This means that x does not point to a valid memory location at the start. Before we attempt to dereference x, we check if it holds any value using an if condition. If x is not null, we proceed to dereference it and print the value it points to. On the other hand, if x is null, we print a message indicating that there is no value to access. This checking mechanism helps prevent runtime errors linked to dereferencing null pointers, thus enhancing the robustness of our code. Next, we create an integer value and assign it the number 42. We then update the pointer x to hold the address of value using the address of operator, and after updating x, we perform the same check as before. If x points to a valid address, we print the value at that address. This code illustrates the importance of managing nullable pointers, as it emphasizes safe practices when working with memory in Zig. Now let's take a look at how we can use many-item pointers to manipulate an array in Zig. In this example, we define a static array called R that holds 5 integers. Next, we introduce a many-item pointer p, which points to the array by using the address of operator, and this pointer gives us the ability to manipulate the contents of the array directly. To demonstrate this, we first print out the original values of the array using a loop, showcasing the elements stored in R. This is essential to establish a baseline for what we will modify. The real power of pointers comes into play when we use p to change the first element of the array. By dereferencing the pointer with the asterisk operator, we access the array through the pointer, allowing us to set the first value to 10. Finally, we print the modified array to visually confirm the update. This example elegantly illustrates how pointers allow for efficient data manipulation, making it clear that they not only provide access to data but also enable direct modification, which is critical in performance-sensitive applications. Now let's see how we can implement dynamic memory allocation in Zig using the std mem allocator. In this example, we begin by obtaining an allocator instance, specifically the page allocator, which is responsible for managing memory allocation requests. We then define the size of the array we want to allocate, in this case, an array of integers with 10 elements. Next, we allocate space for the integers dynamically by calling allocator alloc i32 size, which returns a pointer to the allocated memory. This is where many item pointers come into play, allowing us to access and manipulate multiple items easily. We use a loop to initialize the allocated memory, where each element is set to its corresponding index +1, showcasing how pointers can be dereferenced and modified. After populating the array, we print the dynamically allocated array to confirm our values. Once the array is no longer needed, it's crucial to free the allocated memory using allocator free, rptr. This step prevents memory leaks and demonstrates proper memory management, emphasizing Zig's philosophy of mindful and efficient resource usage. Next, we will write the following code snippet to illustrate how to manage ownership through function calls using pointers in Zig. Here, we define a function named processArray that accepts a pointer to an array of 5 integers. This function allows us to directly modify the elements of the array passed to it, showcasing the efficiency of using pointers for array manipulation without creating unnecessary copies. Inside the processArray function, we leverage a for loop that iterates over the elements of the array via the pointer. By utilizing a dereference operation, we can modify each item by adding 5 to its value, demonstrating direct memory access and manipulation. This is an essential feature of pointers, as it enables efficient memory usage and reduces the overhead that would result from returning modified arrays. In the main function, we initialize an array of 5 integers and call processArray, passing the address of this array using the reference operator. After the array has been processed, we print the modified values. This example aptly conveys how Zig handles pointers and memory management, allowing for streamlined operations across function boundaries. In conclusion, mastering pointers in Zig is essential for efficient programming, especially as we dive deeper into the world of data structures and memory management. Today we have explored the fundamentals of pointers, delving into both single-item and many-item pointers, addressing their syntax, declaration, dereferencing, and memory management, including dynamic allocations. We also touched on safety and ownership principles, which are pivotal in avoiding common pitfalls with pointers. As you continue your journey with Zig, the integration of pointers into your toolkit will empower you to create more efficient and high-performing applications, reducing overhead and providing better control over resource usage. In our next session, we'll expand on these concepts further by exploring advanced pointer operations and how they can be leveraged in more complex data structure manipulations. Happy coding! In today's video, we're diving deep into advanced pointer techniques in Zig. We've already explored the powerful concept of pointers, including single-item and many-item pointers, along with their roles in memory management. Now we will cover how to manipulate pointer values directly and the practical applications of conversions between pointers and integer addresses. This session is going to be packed with examples, explanations, and some interesting use cases that will elevate your understanding of pointers in Zig. In this section, we'll see how to convert an integer address into a pointer using Zig's @ptr from int function. Now let's write the following code where we start by declaring a constant ADA that simulates a physical memory address. In this example, we use the value 0x1000. We then utilize @ptr from int ADA to convert this integer address to a pointer type, specifically a pointer to an i32. It's important to note that this technique allows us to interact with raw memory, but it comes with the critical responsibility of ensuring the address points to a valid memory location. Failing to do so could result in dereferencing an invalid pointer, leading to undefined behavior. The code concludes by printing the pointer's value to the debug output using std debug print. This not only demonstrates the conversion but also underscores the concept of pointer management in Zig, which is essential, especially in systems programming where performance and memory handling are paramount. Remember, handling pointers and their conversions involve careful consideration of memory validity to ensure safe and correct program execution. Now let's see how we can implement a function to convert a pointer back into an integer address. In this code, we begin by declaring an integer variable value and initializing it with the number 42. This variable will allow us to experiment with pointers. We then obtain a pointer to this variable using the addressive operator and value, effectively creating a pointer ptr that points to our integer. Next, we focus on converting this pointer back into an integer representation of its address using the @int from ptr function. This conversion is essential as it provides insights into memory management and debugging, allowing us to see the actual address of value in the memory. To display this integer address, we utilize std debug print, which will output the pointer's integer value to the console. This example showcases the dual capability of converting between pointers and integer addresses, empowering us with tools for deeper memory manipulation and debugging in Zig, particularly in scenarios involving low-level programming or hardware interactions. Now let's implement a code snippet that demonstrates how to utilize pointer arithmetic with an array in Zig. In this example, we define an integer array R with 5 elements. To manipulate this array using pointers, we declare a pointer ptr that points to the first element of the array. By leveraging pointer arithmetic, we can navigate through the elements of the array effectively. In the loop, we iterate from 0 to the length of the array using the index I. Within the loop, we perform pointer arithmetic by adding I to ptr, which shifts the pointer to the ith element of the array. The asterisk operator dereferences the resulting pointer, allowing us to access the value stored at that specific location. This technique provides a more efficient way to access array elements directly, making it especially useful in performance-critical applications where traditional index calculations could introduce overhead. Thus, mastery of pointer arithmetic can greatly enhance your capabilities in handling data structures effectively in Zig. Now let's take a look at how we can manipulate a structure's fields directly using pointers. In this example, we define a simple point structure that contains two fields, x and y, both of which are integers. We then create an instance of the point structure and obtain a pointer to that instance. With the pointer to the structure, we can conveniently access its fields without going through the instance itself. By dereferencing the pointer, we can read and modify both x and y directly. For example, we print the coordinates of the point before updating them. This demonstrates how effective pointer arithmetic is when managing data structures. By incrementing the x and y fields directly through the pointer, we showcase the flexibility and efficiency that pointers bring to the table. Finally, we print the updated coordinates, illustrating the changes made through the pointer. This example emphasizes the power of pointers in Zig, as they provide quick access to structure members and enable easy modifications without cumbersome syntax. This ease of manipulation can be particularly helpful when dealing with complex data types. Now let's take a look at how we can manipulate the value of a variable directly through pointers. In this example, we define a function called modifyValue, which takes a pointer to an i32 as its argument. This function dereferences the pointer and assigns a new value of 100 to the location it points to, effectively modifying the original variable. Next, we enter the main function, where we declare a variable value initialized to 42. We then create a pointer ptr that points to the address of value using the address of operator. By invoking the modifyValue function and passing ptr, we effectively transfer ownership of access to the integer it points to. When the function completes, the variable value has been updated, and we verify this change by printing the modified value to the console. This illustrates how pointers facilitate direct modifications to variable values and highlights the concept of pointer ownership, where altering the data through a pointer reflects changes in the original variable. Now let's take a look at how to manage dynamic memory allocations safely using Zig's allocator. In this example, we begin by importing the standard library and defining the main function. We use std heap page allocator to create an allocator for memory management and define the size of the array we want to allocate. Next, we dynamically allocate an array of integers with the specified size. This allocation is performed inside a try block, which ensures that if the allocation fails, it will handle the error gracefully. After the memory is successfully allocated, we populate the array with values by using a loop that iterates over the elements. Here, we utilize a pointer to access each item directly, leveraging Zig's ability to safely dereference pointers. After filling the array with data, we print the values to demonstrate the allocation's success. Finally, we ensure proper memory management by freeing the allocated memory using allocator free. This step is crucial as it prevents memory leaks, highlighting the importance of ownership in dynamic memory handling. Zig encourages programmers to be conscientious of memory usage, promoting safe practices when working with pointers. Now let's take a look at how pointer casting can help us work with different data types seamlessly. In this example, we first declare a byte buffer filled with 8 consecutive values from 0 to 7. This buffer is of type U8, meaning each element is an unsigned 8-bit integer. We then create a pointer ptr which points to the start of our buffer. Next, we implement pointer casting with @ptrcast, converting our U8 pointer to a U32 pointer. This allows us to interpret the first 4 bytes of the buffer as a single 32-bit integer. By dereferencing int ptr, we retrieve this value, effectively treating different types of data in memory flexibly. It's vital to keep in mind that pointers must satisfy alignment requirements. Failure to do so could lead to misaligned accesses, causing runtime errors. This powerful technique showcases how Zig enables developers to manipulate memory efficiently while also reminding us to handle pointer conversions cautiously. To sum it up, we've covered a range of advanced pointer techniques in Zig that equip you with the tools necessary for effective memory manipulation. We delved into converting between integer addresses and pointers, explored pointer arithmetic, and touched upon memory ownership and dynamic allocations. Through practical examples, we highlighted how pointers can be optimized for both safety and performance. Having a strong grasp of these concepts will set a solid foundation for more complex data structures and systems programming tasks. As you continue your journey with Zig, the mastery of advanced pointer techniques will significantly enhance your programming capabilities. Happy coding, and remember to treat pointers with care. A programming language is a formal system for instructing a computer. At its core, programming is about communicating with machines using languages designed to write down the steps necessary for accomplishing tasks. Just like any spoken or written language, each programming language has its own syntax, rules, and idioms, which enable us to express complex ideas in clear, executable terms. In this session, we'll dive into the foundational concepts of programming that will get you familiar with how programming works. So far, we learned about advanced pointer techniques in Zig, dynamic memory allocation, and safe memory management practices. Now we will talk about the basic elements of programming languages, including variables, data types, control structures, and functions. Now let's take a look at how we can define and utilize variables in Python. In our example, we start by defining a variable named age, where we assign the integer value of 25. This variable serves as a storage location for the age, which can be easily referenced throughout the program. Next, we introduce another variable called name, which holds a string value Alice. Here, we can see the difference between the two data types. Age is an integer, while name is a string, illustrating how variables can be used to store different kinds of data. Following the definitions, we use the print function to output the values stored in these variables. The print statements help us visually confirm that our variables hold the correct data. By labeling our variables meaningfully, like age and name, we make our code easier to read and maintain. This simple approach provides a valuable introduction to how we can dynamically work with data within our program, showing the significance of variables in storing and manipulating values as the program runs. Now let's see how we can implement different data types in JavaScript. First, we define an integer variable called apples and assign it the value of 5. This variable represents the number of apples we have and is stored as a whole number. Next, we introduce a floating point variable named price per apple, which holds the value 0.75. This data type is crucial for representing decimal values such as currency, which often requires precision with tenths and hundredths. To showcase the use of a character, we create a variable called firstLetter and assign it the letter A. Characters are used to store individual symbols or letters, which can be useful in various programming scenarios such as constructing strings or handling user input. Continuing with strings, we construct a variable named message, which combines text and variable values. This string incorporates the apples variable, enabling dynamic messaging based on its value. Finally, we output the message and price per apple to the console. This demonstrates how we can present information to the user and manipulate data types effectively in our JavaScript code, reinforcing the importance of understanding these fundamental concepts. Now let's see how we can implement a basic control structure using an if statement to determine voting eligibility based on age. In this example, we begin by checking if a variable named age meets the requirement for voting. We assign the value of 18 to this variable, which will serve as our threshold. The if statement then evaluates whether the age is greater than or equal to 18. If the condition is true, the program executes the next line where it outputs the message, "You can vote." This demonstrates how conditional logic can be applied to create responsive behavior in our programs. Conversely, if the condition is not met, the code inside the else block kicks in, displaying the message, "You cannot vote yet." This simple structure not only clarifies how conditional statements operate, but also showcases their critical role in introducing decision-making capabilities into our applications. By embedding such logic, we allow our programs to interact meaningfully with users, adapting to different scenarios based on the specified criteria. Now let's see how we can implement a basic for loop in Java. The loop starts by initializing a variable I to 0, which serves as our loop counter. The condition I5 checks whether I is less than 5 before each iteration. As long as this condition is true, the loop continues to run. After executing the block of code inside the loop, the I++ statement increments I by 1. This means that in each iteration, the current value of I will be printed to the console prefixed by the string number. Through this simple structure, we effectively create a sequence of numbers from 0 to 4 printed on separate lines. This demonstrates how loops allow for automation in code execution, eliminating redundancy that would arise from writing separate print statements for each number. In practical applications, such loops are invaluable for processing items in large datasets or performing repetitive tasks efficiently without the clutter of repetitive code. Next, we will write a simple function in Python to illustrate how we can encapsulate logic and promote code reuse. In this example, we define a function called greet, which takes one parameter named name. This function is designed to generate a personalized greeting message. When invoked, it concatenates the string hello with the value of the name parameter, followed by an exclamation mark. After defining the function, we will call it by passing in the string Alice as an argument. This invocation triggers the greet function to execute and return the greeting message, "Hello, Alice." The call to print then displays this returned message to the console. Using functions in this manner not only organizes our code, but also allows us to replicate the greeting behavior without rewriting the logic each time. This is particularly useful in larger programs, where you may need to greet multiple users or execute similar tasks. By breaking down our tasks into functions, we create cleaner, easier-to-understand code, which ultimately makes the debugging process much simpler. Now let's take a look at how we can utilize libraries in Python to perform operations efficiently. In this example, we will use NumPy, a powerful library designed for numerical computations. First, we start by importing the library using the import numpy as np statement, which allows us to access its functionalities through the alias np. Next, we create an array containing the numbers 1 to 4. The use of arrays facilitates handling collections of numbers and is integral for performing mathematical operations on them. Once we have our array, we proceed to calculate the mean or average of its elements. By calling the np mean function on our array, NumPy calculates the mean value in a single, efficient operation. Finally, we print the mean value, which provides insight into the central tendency of the numbers in our array. By leveraging libraries like NumPy, we not only enhance the performance of our code but also simplify our workflow, allowing us to focus more on building our solutions rather than reinventing the wheel. As we wrap up this introduction to programming concepts, it's essential to understand that these foundational elements, variables, data types, control structures, functions, and libraries, all work together to create robust applications. In future lessons, we'll delve deeper into more advanced topics like object-oriented programming, error handling, and working with databases. Each of these concepts builds upon our current understanding, enabling us to tackle complex problems and create efficient solutions. So far, we've covered the fundamental building blocks of programming languages, and in our next session, we will explore object-oriented programming principles that allow us to model real-world entities in our code effectively. By mastering these introductory concepts, you're laying the groundwork for a fulfilling journey into the world of programming. So stay curious, keep coding, and don't hesitate to experiment with what you've learned. Welcome back, everyone. Today we're diving into the exciting world of advanced programming techniques. This is where things get really interesting and where we can leverage the full power of programming to create efficient, scalable, and robust applications. So far, we explored the foundational concepts of programming, including variables, data types, control structures, functions, and libraries. We looked at how these concepts serve as the building blocks of our code. Now, we'll delve into object-oriented programming principles along with advanced techniques like design patterns, concurrency, and error handling. Now let's take a look at how we can implement a simple bank account class in Python, which encapsulates the concept of a bank account, including its owner and balance. This class begins with the init method, which serves as the constructor, initializing the account holder's name and setting a default balance of 0 if none is provided. This ensures that every bank account object is created with essential properties immediately available. Next, we have the deposit method, which allows users to increase their balance by a specified amount. It performs the operation safely, ensuring that the balance reflects the new total immediately while providing feedback to the user about the transaction. Conversely, the withdraw method provides a way to decrease the balance, incorporating a check for insufficient funds to prevent overdrafts, thus reinforcing the importance of account management rules. Finally, the getBalance method serves as a simple interface for users to access their current account balance, promoting a clear view of their finances. This structure exemplifies the principles of encapsulation, providing a well-organized and manageable way to handle bank account operations. Now let's see how we can implement a savings account class that extends from the previously defined bank account class. This subclass adds new functionality specifically for savings accounts, allowing us to manage interest in addition to regular banking operations. In our savings account class, we start by initializing its attributes through the init method. Here we call the super function to invoke the constructor of the parent class bank account, which ensures that the account holder and balance are properly set up. We also introduce an interest rate attribute with a default value, making it easy to define how much interest will be accrued over time. Next, we add the addInterest method, which calculates the interest based on the current balance and the defined interest rate. By multiplying the balance by the interest rate, we determine the amount of interest to be added to the account. The method further utilizes the deposit method inherited from the bank account class to increase the account balance by the calculated interest. This demonstrates how inheritance allows us to build upon existing code and enhance it with additional features tailored to specific use cases. Now let's see how we can implement a checking account class which extends the functionality of the previously defined bank account. This class introduces an additional feature, the ability to perform withdrawals with an overdraft limit. In the init method, we initialize the account holder and balance by calling the constructor of the parent class using super, while also setting the overdraft limit specific to checking accounts. This demonstrates the concept of inheritance, allowing checking account to utilize the existing structure of bank account while introducing its own unique features. The overriding of the withdraw method showcases polymorphism, an essential aspect of object-oriented programming. In this method, we check if the requested withdrawal amount exceeds the sum of the current balance and the overdraft limit. If it does, we alert the user that the overdraft limit is exceeded. Otherwise, we proceed with the withdrawal, updating the balance accordingly. This flexibility allows checking account to behave differently from a standard bank account, illustrating how polymorphism leads to tailored behaviors in classes that share a common interface. Now let's implement the singleton pattern, which ensures that a class has only one instance and provides a global point of access to it. In this code, we define a class named singleton, where a class variable instance is initialized to none to keep track of the single instance. Next, we override the new method, which is responsible for creating a new instance of the class. In our implementation, we first check if instance is already set. If it's none, it means no instance has been created yet, so we call the parent class's new method to create a new instance and assign it to instance. If an instance already exists, we simply return that existing instance. This approach guarantees that every time we attempt to create a singleton, we receive the same instance, effectively controlling access to it. To demonstrate its functionality, we create two instances of singleton, singleton1 and singleton2. When we check if these two variables point to the same object using the is operator, it returns true, confirming that both variables reference the same instance. This encapsulates the essence of the singleton pattern in a concise and effective manner. Now let's see how we can implement concurrency in Python using the threading module to execute tasks simultaneously. In this example, we start by defining two functions, print numbers and print letters. The print numbers function prints numbers from 0 to 4, pausing for 1 second between each print statement, which simulates a time-consuming operation. Similarly, the print letters function prints the letters from A to E with a 1 second delay between each letter. Next, we create two threads using the thread class, assigning each thread a target function print numbers for the first thread and print letters for the second. We initiate the execution of both threads by calling the start method on each one. This allows both functions to run concurrently, meaning they can perform their tasks simultaneously instead of sequentially. Finally, by using the join method on each thread, we ensure that the main program waits for both threads to complete their execution before moving on. This structure not only improves the application's responsiveness but also efficiently manages multiple operations by leveraging the power of concurrency, especially beneficial for tasks that may involve waiting, like I/O operations. Now let's take a look at how we can implement robust error handling in our applications using Python. The function divide numbers is designed to safely perform division between two numbers. Inside this function, we employ a try block to attempt the division operation, which is where an error might occur if the second number is 0. To handle this potential issue, we use an except block specifically targeting the 0 division error, which triggers when there is an attempt to divide by 0. By catching this exception, we can display a friendly error message indicating that division by 0 is not allowed, and we return none to signify that no valid result is produced. If the division is successful, the else block executes, returning the calculated result. This structure ensures that our program can continue running smoothly, even in the presence of unexpected inputs. We can see this error handling in action with two test calls to the function, one that produces a valid division result and another that gracefully manages the division by 0 scenario without crashing the application. This practice significantly enhances user experience and overall application reliability. As we wrap up today's lesson on advanced programming techniques, it's important to recap what we covered. We explored the core principles of object-oriented programming, including encapsulation, inheritance, and polymorphism, followed by a discussion on design patterns, concurrency, and error handling. Each of these techniques brings a wealth of benefits to the table, helping us to write clean, efficient, and maintainable code. These advanced techniques are not just theoretical, they have practical applications that can take your programming skills to new heights. Whether you're creating a simple application or building complex systems, mastering these principles will equip you with the tools you need for success in the software development world. If you found this information enlightening, stay tuned for our next session where we'll delve even deeper into the realms of advanced topics like networking, database interactions, and how to effectively manage memory in programs. Keep coding and remember that every line of code is a stepping stone on your journey to becoming a programming maestro. Until next time, happy coding. Structs play a fundamental role in programming, serving as a way to group related data under a single data structure. They allow us to define complex data types that can hold various types of data together, making our code more organized and manageable. Today, we'll dive into the world of structs, exploring how they can be declared, defined, and utilized in programming. So far, we have learned about advanced programming techniques, focusing on object-oriented programming, OOP principles such as encapsulation, inheritance, and polymorphism. We discussed how to implement these concepts using practical examples like a bank account class and design patterns, particularly the singleton pattern. Additionally, we explored concurrency with threading in Python and the importance of robust error handling using try-except blocks. These topics lay the groundwork for building efficient, scalable, and maintainable applications in software development. Now, we will cover structs, how they work, their advantages, and practical coding examples to illustrate their utility. Now let's see how we can declare a variable of our car struct type. In this line of code, we create a variable named myCar, which will allow us to store information about a specific car. By using the struct car type, we can access the various members we previously defined within the struct, such as make, model, year, and color. This setup means we can work with all these attributes as a cohesive unit rather than handling them as separate variables, thereby enhancing organization in our code. Next, we will assign values to the properties of myCar. We utilize the strcpy function to copy string literals into the make, model, and color members. For the year, we directly assign an integer value. This method not only encapsulates related data, but also makes it easier to manage and manipulate car details in one structure. Finally, we print out the car's attributes using printf, allowing us to observe the values we've assigned and confirm that our struct is functioning correctly. This usage demonstrates how structs streamline variable management and data display in programming. Now let's see how we can implement our struct variable using the code example provided. First, we include necessary libraries such as stdio, h for input-output operations, and string h for string manipulation. The struct car is defined to encapsulate the properties of a car, specifically the make, model, year, and color. This organization allows us to treat all related attributes as a single entity, which enhances code clarity. Next, we declare a variable myCar of type struct car within the main function. We then utilize the strcpy function to populate the string members, make, model, and color, ensuring that each string is copied into its respective attribute effectively. The year is directly assigned an integer value. This step illustrates how we can manipulate data within a struct, making it straightforward to initialize and assign values. After setting the details of myCar, we use printf statements to display the car's attributes, demonstrating how easily we can access and print struct members. This example succinctly showcases the power and convenience of structs in managing complex data in a cohesive manner. Now let's explore how to implement a linked list of car instances using structs and see the car struct is enhanced with a next pointer, which allows each car to point to the next car in the list, facilitating the creation of a linked list structure. To work with this linked list, we start by dynamically allocating memory for two car instances using malloc, ensuring we have sufficient memory to store their details. Next, we populate the attributes of each car, namely the make, model, and year, using the strcpy function to copy string data into the struct fields. After populating the first car, we link it to the second car by updating the next pointer of the first car to point to the second car, and setting the next pointer of the second car to null, indicating the end of the list. Now we implement a function called printCars, which takes the head of the linked list as an argument. This function traverses the linked list, printing out the details of each car until it reaches the end. Finally, to ensure proper memory management, we use free to deallocate the memory allocated for both car instances once we are done. This example showcases the power of structs in building complex data structures that can dynamically manage multiple instances effectively. Now let's see how we can implement a function to display the details of a car struct. The displayCar function takes a car struct as its parameter and prints out the car's make, model, and year. This showcases a clear advantage of using structs, the ability to pass a single cohesive unit of data rather than multiple individual variables. By encapsulating all related attributes within the car struct, we not only make our function calls cleaner but also enhance the readability and maintainability of our code. Inside the function, we use the print function to output each attribute of the car separately. The syntax clearly indicates how we access the structured data, providing a straightforward way of demonstrating the encapsulated information. This approach also minimizes the risk of errors that can occur from missorted arguments when calling a function with several parameters. With this structured approach to data handling, we can ensure that our function effectively communicates the essential details about a car in a concise manner. Now let's implement a more advanced example by introducing nested structs to enrich our car representation with owner details. We start by defining the owner struct, which contains two fields, name and address, enabling us to store descriptive information about the car's owner. Next, we embed this owner struct within the car struct, allowing each car instance to directly include data about its owner alongside its make, model, and year. This design encapsulates all relevant details into a single cohesive unit, making it easier to manage attributes related to both the car and its owner. To demonstrate how these structs work together, we create a function called displayCar. This function takes a car type argument and prints out all associated details, including not only the vehicle's specifications but also the owner's information. When we invoke this function in the main routine, we first populate the myCar instance with sample data for both the car and the owner. This relational struct approach is particularly powerful in modeling real-world entities, providing clarity and structure to our code while enhancing data handling. In conclusion, structs are a powerful feature of programming that allow for organized data management, improved code clarity, and efficient memory handling. They enable the creation of complex data types and structures that can be utilized across a myriad of applications, from basic data representation to sophisticated systems development. By mastering Structs, you equip yourself with a crucial toolset for writing clean, maintainable, and scalable code. Today, we've explored the basics of Structs, their declaration, advantages, and practical applications. Remember how we started with a simple definition of a struct and moved into practical examples, illustrating their utility and significance in programming. As you work on your programming journey, keep experimenting with structs and consider how they can simplify your code and enhance its structure. The more you practice using them, the better you will understand their power and versatility in software development. Happy coding! Each struct field may have an expression indicating the default field value. Such expressions are executed at compile time and allow the field to be omitted in a struct literal expression. This mechanism adds great flexibility and convenience in how we can define and use structs in programming. Today, we're going to delve into advanced struct usage and applications, and trust me, by the end of this session, you'll see just how powerful and efficient structs can be in your coding toolbox. So far, we've learned about structs as a fundamental data type used to group related data together in a structured manner, enhancing code organization and clarity. We explored how to define and declare structs, utilize them for creating complex data structures like linked lists, and pass them as single parameters to functions for improved code readability. Additionally, we discussed the benefits of structs in memory management and their ability to nest, allowing for detailed data storage such as combining car and owner information. Now, we will talk about advanced aspects of structs, such as default field values, nesting, and more interesting applications that can elevate your programming finesse. Now, let's implement a struct that represents user settings in our application. Here, we define a struct named user settings with 3 fields: theme, notifications, and language. These fields correspond to various user preferences, specifically the visual theme where the notifications are enabled and the default language for the application. Next, we will write a constructor function, newUserSettings, which initializes a new instance of user settings with default values. In this function, we create and return a user settings instance, setting the theme to light, notifications to true, and language to English. This means that when a new user is created, they will receive these preset values unless customized otherwise. This approach streamlines user creation by eliminating the need to specify every setting each time and helps avoid potential issues with uninitialized fields. By using this design pattern, we enhance the clarity of our codebase, making it easier for fellow developers to understand the default setup for new users, thereby contributing to better maintainability and user experience. Now let's take a look at an example of how we can manage optional fields in Rust struct using the option type. In this example, we define an app config struct with 3 fields: DB URL, API key, and timeout, where the timeout field is wrapped in an option type to signify that it is optional. This is significant because it allows us to avoid enforcing a value for timeout if it's not necessary, thereby granting greater flexibility to our configuration. When we instantiate the config variable, we provide specific values for DB URL and API key, while assigning none to the timeout field, intended to represent that no timeout has been set. This demonstrates how optional settings can cleanly be represented in code without cluttering logic with numerous checks for uninitialized or default values. The implementation of the option type encourages us to explicitly handle the presence or absence of a value, making our code more robust and expressive. Finally, by printing the config, we can observe how the struct encapsulates these values neatly, showcasing the intended structure and flexibility. Now let's take a look at how we can represent complex entities by defining nested structs in Go. In this example, we define 3 structs: author, publisher, and book. The author struct contains fields for the author's name and birth year, while the publisher struct holds information about the publisher's name and address. This clear separation allows us to encapsulate related data effectively. Next, we create the book struct that embeds both the author and publisher structs. This approach facilitates better organization and access to related information when we instantiate a book object. For instance, when we create a book instance with the title 1984, we also assign it an author and a publisher using the previously defined structs. This illustrates how embedding allows for a cohesive relationship between these entities. Finally, in the main function, we instantiate the author and publisher structs with concrete values, then create a book object that combines all this data. This design highlights the power of nested structs in Go, making it straightforward to manage and access complex relationships between data components in your applications. Now let's see how we can implement an interface along with structs to showcase polymorphism in Go. First, we define the shape interface, which includes a method area that returns a float64 value. This is the contract that our shapes will adhere to. Next, we create two structs, circle and rectangle, each representing different shapes with their own specific fields. The circle struct has a radius field, while the rectangle struct includes width and height. To define their behavior, we implement the area method for both structs. For circle, the area is calculated using the formula pi times the radius squared, while for rectangle, the area is simply the width multiplied by the height. This implementation effectively encapsulates the logic for area calculation within each shape. Now let's take a look at the main function where we create a slice of shape. This slice can hold any type that implements the shape interface, demonstrating the flexibility of our design. By iterating over this slice, we invoke the area method on each shape and print the calculated areas. This shows how our code can easily accommodate new shapes in the future without modifying existing logic, illustrating the power of interfaces and polymorphism in struct usage. Now let's take a look at a practical application of structs for error handling in Go. We begin by defining a struct called customError, which serves to encapsulate error information with two fields, code and message. This struct allows us to represent errors more clearly by associating a specific error code with a descriptive message, facilitating easier debugging and understanding of what went wrong. Next, we implement the error method for our customError struct, which is a requirement for any type that satisfies the error interface in Go. This method formats the error message as a string that includes both the error code and the message, thereby providing a consistent and informative output whenever an error occurs. Now let's see how we can implement a function named doSomething. This function simulates an operation that fails and returns a new instance of customError, specifying an error code of 404 and a relevant message indicating that a resource was not found. Finally, we approach the main function where we invoke doSomething and check if it returns an error. If an error is present, we simply print the formatted error message, showcasing how our custom error type can effectively convey information about failures in a user-friendly manner. Now let's explore how to define a struct that represents user profiles for use in an API. In the provided code, we first declare a user profile struct with three fields: ID, name, and email. Each field is associated with a JSON tag that specifies how the field name should appear when the struct is converted to JSON format. This is crucial for ensuring that the data transmitted over the web aligns with client expectations. Next, we see how to create an instance of the user profile struct in the main function. Here we instantiate a user with an ID of 1, a name of Alice, and an email address of alice@example.com. After setting up this user profile, we utilize the JSON Marshal function to convert the struct into JSON bytes. This conversion is key for APIs since JSON is a widely used data interchange format. Finally, we print the JSON representation of the user profile to the console. By structuring our data this way, we not only ensure clarity and organization but also facilitate efficient data transfer when communicating with clients or other services. This example highlights the importance of using structs in data serialization, particularly in API development. Through the course of this session, we've uncovered advanced struct usage, lifting the lid on default values, optional fields, nesting, embedding with interfaces, error handling, and data serialization. Each of these aspects provides a deeper insight into how powerful structs truly are and how mastering their use can significantly streamline your programming experience. Keep experimenting with these concepts and apply them to your projects. The more familiar you become with these advanced usages, the more proficient you'll be as a developer. Happy coding! The Zig programming language is designed for robust and optimal system-level programming. It aims to combine the efficiency of C with a more modern syntax and safety features that help developers write clearer and more maintainable code. In today's tutorial, we are going to dive deep into Zig, covering its core features, syntax, and how it can be applied in various programming scenarios. So far, we learned about structs as a fundamental data type that helps in organizing related data and improving code clarity. We discussed how to define structs, set default field values, handle optional fields using types like option, and embed structs to model complex relationships. Additionally, we explored using interfaces for polymorphism, error handling with custom error types, and data serialization for APIs. These advanced struct concepts enhance your programming capabilities and help manage complexity in your applications. Now we will cover the basics of Zig, including its syntax, key features, and practical examples to demonstrate its capabilities. Now let's take a look at how we can create a simple Hello World application in Zig. The first line imports the standard library, which provides the necessary functions for input and output operations. We define the main function with a return type of void, indicating that it can potentially return an error, a unique feature of Zig that encourages explicit error handling and enhances code reliability. Inside the main function, we use the std debug print function to output the string hello world to the console. The formatted string allows us to include any additional information if needed, though in this case we're simply printing a static message. This concise implementation showcases Zig's straightforward syntax and organized structure, demonstrating how easy it is to get started with programming in Zig. By focusing on readability and clarity, Zig helps you write code that is not only functional but also maintainable, setting the foundation for more complex programming concepts we'll explore in future sections. Now let's explore how we can implement compile-time execution in Zig through a simple example. We will define a recursive function called factorial that calculates the factorial of a given number. The function begins by checking if the input number n is 0. If it is, it returns 1 since the factorial of 0 is defined as 1. Otherwise, the function calls itself with the value n1 and multiplies the result by n. This recursive approach effectively computes the factorial of any non-negative integer. Next, we move to the main function, where we declare a constant num initialized to 5. This number will be passed to the factorial function to calculate its factorial at compile time. The result of this computation is stored in another constant called result. Finally, we utilize the std debug print function to output the result to the console, clearly indicating the factorial of 5. By leveraging compile-time execution, this entire operation is determined before the program is run, optimizing performance and ensuring the correctness of the value without runtime overhead. Now let's see how we can implement a function that demonstrates Zig's approach to error handling through its innovative return type system. In this example, we define a function called divide, which takes two floating-point numbers as parameters. The function checks if the second number is 0, as division by 0 is undefined. If it is, the function returns an error value, specifically error, division by 0, making the error handling explicit. In the main function, we attempt to perform a division operation by calling the divide function with two arguments, one of which is 0. Here we handle the result of the division using a switch statement, which allows us to manage different outcomes effectively. If a division by 0 error occurs, we print a message indicating the error. Conversely, if the division is successful, we print the computed result. This structured approach not only clarifies error management but also encourages developers to consider potential errors during coding, leading to higher code quality and better practices throughout the development process. Now let's take a look at how Zig's optional types can enhance our code safety and clarity. In the following example, we declare an optional variable called maybeValue, which is defined as a nullable U32 type and initialized to null. This means that maybeValue can either hold a valid unsigned 32-bit integer or indicate that no value is present. When we check for the presence of a value, we utilize an if statement, which allows us to safely access the contained value using a shorthand syntax. If maybeValue has a value, it is printed to the console. Otherwise, a message indicating that no value is present is displayed. This approach not only provides a clear way to handle scenarios where a variable may or may not contain data, but also minimizes potential runtime errors related to null dereferencing. By employing optional types in this manner, you can structure your code to be more robust and resilient against invalid state conditions, demonstrating one of the many safety features that Zig offers for system-level programming. Now let's take a look at how we can validate the functionality of our code using Zig's built-in testing feature. In this example, we define a simple function called add, which takes two unsigned 32-bit integers as parameters and returns their sum. The function is straightforward, demonstrating the clarity and simplicity of Zig's syntax. Next, we will write a test case using the test keyword, which allows us to create a specific scenario to validate our add function. Inside the test block, we call add23 and store the result in a variable named result. This checks if our implementation behaves as expected. To assert that the result is correct, we utilize std testing expect, which takes a condition that should evaluate to true. In this case, we are checking if result equals 5, the expected output of adding 2 and 3. This approach highlights the importance of testing within the same file as our implementation, ensuring both remain in sync and facilitating a robust software lifecycle. By integrating tests into our development process, we can maintain high-quality software and swiftly identify any issues that arise during changes or enhancements to our code. Now let's take a look at how we can manage memory explicitly in Zig, which is crucial for system-level programming. In this example, we first import the standard library to gain access to the necessary functions. We then establish a variable for the allocator, specifically using Zig's page allocator, which is designed to handle memory allocation efficiently. Next, we set a constant size for our buffer, in this case, 1024 bytes, reflecting how we can dynamically allocate memory based on our needs. The allocator alloc function is called to attempt the allocation, and it features error handling through the use of catch. This ensures that if the allocation fails for any reason, we can manage the situation gracefully by printing an error message and exiting the function early. To emphasize Zig's approach to resource management, we use the defer statement. This guarantees that once we finish using the allocated memory, it will be freed automatically, preventing memory leaks. Finally, we demonstrate the use of the allocated memory by storing a value in the first byte of the buffer and printing it. This compact yet effective example showcases Zig's explicit memory management capabilities, making the code clearer and easier to maintain. Now let's take a look at how to define a build script in Zig using a build.zig file. In this example, we begin by importing the standard library and the build system module, allowing us to leverage the necessary functionalities for managing our project's build process. Next, we define a public function named build, which will take a pointer to a build builder as its parameter. This function is crucial because it sets up our build configuration. Inside this function, we add an executable named hello that will be compiled from the source file located at src/main zig. The method addExecutable streamlines the process of specifying the target executable and its corresponding source file. Following that, we call setTarget and setBuildMode on our executable object to specify the target architecture and the build mode. By using bStandardReleaseTarget and bStandardReleaseMode, we can easily ensure that our project is being built correctly in both performance and optimization settings. This straightforward setup reflects Zig's emphasis on simplicity and efficiency, making it easier to manage your projects without complicated configurations. Zig's performance makes it a great choice for applications where speed and resource efficiency are paramount. Many programmers appreciate that it offers manual memory management similar to C, but comes with safety features that help avoid common pitfalls. The developers focusing on system-level programming can harness Zig's capabilities to write performant and maintainable code, helping them build cutting-edge applications. To wrap things up, Zig is not just a language, it's a tool for precise and powerful programming. You've seen how its modern features like compile-time execution, superior error handling, and explicit memory management position it as a viable alternative for developers wanting capacity, performance, and safety in their system-level applications. Congratulations, you've just taken a significant step toward mastering Zig. In this lesson, we covered the fundamentals of the Zig programming language, looked at its syntax, core features, and how they can be applied in practical scenarios, reinforcing the importance of error handling, memory management, and testing. In our next session, we will explore more advanced topics such as concurrency in Zig and how to manage tasks efficiently. So stay tuned as we continue this exciting journey into the world of Zig. Zig is not just another programming language. It's a powerful tool for developers who want to emphasize performance and safety in systems programming. Today, we're going to dive into the advanced features of Zig, such as compile-time code execution and optional memory safety, which set it apart from other programming languages. So far, we learned about the Zig programming language, focusing on its efficiency and safety for system-level programming. We covered fundamental concepts such as defining structs, error handling, compile-time execution, and memory management, highlighting Zig's distinct features that enhance code clarity and performance. Additionally, we explored testing capabilities and the simplicity of Zig's build system. Now we will talk about advanced topics including compile-time execution and memory safety, which can significantly elevate your code quality and performance. Now let's implement compile-time code execution through a function that calculates the factorial of a number. Here, we first define a constant n set to 10, which represents the number for which we want to calculate the factorial. Using the compute factorial function, which is declared to run at compile time, we take advantage of Zig's ability to execute code before the program runs. This recursive function checks if the input n is 0, returning 1, which is the base case for factorial. Otherwise, it recursively multiplies n by the factorial of n1. Now let's see how we can utilize this functionality in the main function. Here we print the result using std debug print, displaying the factorial of n. Since the factorial is computed at compile time, the runtime overhead is minimized, allowing for efficient execution. This technique is particularly useful in performance-critical applications where constant values can be pre-computed, further showcasing Zig's strength in systems programming by enabling developers to write optimized and clear code without sacrificing performance. Now let's see how we can implement optional memory safety in Zig through the use of the optional type. In the provided code, the function getValue is designed to simulate a scenario where it may or may not return a valid integer. The introduction of randomness via std_rand default PRNG next creates a 50-50 chance to either return a valid integer value or null, thus demonstrating the optional nature of the return type, represented as I32. Within the main function, we invoke getValue and use a switch statement to handle the return value safely. This structure enables the program to perform different actions depending on whether the value is null or holds a valid integer. If the value is null, the output will convey that no value is present, highlighting how optional types help in preventing null pointer exceptions. Conversely, if a valid integer is returned, it displays that value. This approach not only enhances code clarity but also explicitly communicates the programmer's intent, significantly reducing the likelihood of runtime errors related to null values. This example illustrates the power of Zig's optional types in writing safer and more reliable code. Now let's explore how Zig handles dynamic memory allocation by implementing a simple example to allocate and manage an array. We begin by utilizing Zig's standard library to access the page allocator, which is designed for allocating pages of memory efficiently. Next, we specify the size of our array, 5u32 integers, and use the allocator's alloc function to request this memory. If the allocation fails, Zig's error handling mechanism catches the error, allowing us to print a message and exit gracefully, ensuring our program doesn't crash unexpectedly. Now let's populate the allocated array with values. A loop iterates over the array, assigning each index a value that doubles its position. This demonstrates how you can manipulate allocated memory directly and clearly, adhering to Zig's explicit nature of memory management. Once the array is filled, we output its contents to the console, showcasing the values stored. Finally, to maintain good memory hygiene, we explicitly free the allocated memory using the allocator's free method, reinforcing the importance of manual memory management in Zig while ensuring that we do so safely and efficiently. Now let's see how we can implement a straightforward error handling mechanism using Zig's approach to division. In this example, we define an error type that includes a division by zero error to indicate the specific issue that can occur when dividing by zero. The function divide takes two floating point numbers, x and y, and if y is detected to be zero, it returns the division by zero error instead of allowing a runtime fault. This makes our function more predictable and easier to debug. In the main function, we call the divide function with a deliberate attempt to divide 10 by 0, which we know is invalid. The result from this function call is captured in a variable named result, and we utilize a switch statement to handle various outcomes. If the function returns the division by zero error, a clear error message is printed to the console, informing the user of the attempted illegal operation. Alternatively, if the division is successful, the result is printed. This method not only enhances the visibility of errors, but also improves maintainability within your code by clearly delineating paths for handling different scenarios. Now let's take a look at how we can implement compile-time testing in Zig, which enhances the reliability of our code. In this example, we define a simple function called add that takes two unsigned 32-bit integers as parameters and returns their sum. Next, we create a test case using the test keyword, which automatically runs during the compilation process. Inside this test case, we call the add function with the values 2 and 3. We then use Zig's built-in testing feature, std testing expect, to assert that the result equals 5, which is what we expect from adding those two numbers. If the result does not match the expected value, the Zig compiler will raise an error, informing us that something went wrong. This approach to testing is particularly beneficial because it allows developers to maintain code integrity without requiring a separate testing framework, thus streamlining the development process. By incorporating compile-time testing, we ensure that our functions behave as intended as we develop, contributing significantly to the overall safety and reliability of our code. The combination of compile-time constant evaluation, explicit memory management, and robust error handling makes Zig a unique and compelling choice for developers seeking to build software with fewer surprises. Isn't that right? It's like having a well-organized toolbox. You know exactly where everything is and how to use it without undue complexity or overhead. In conclusion, Zig provides powerful features that greatly enhance not only performance, but also the reliability of the code you develop. The compile-time execution enables you to compute values ahead of time, while optional memory safety allows for expressively safe programming without sacrificing performance. Zig's explicit memory management and its innovative error handling system encourage users to write clear, maintainable code. So, as we've seen in today's lesson, Zig combines safety with performance in a way that should excite any systems programmer. Next time, we will dive into concurrency and task management in Zig, exploring how to leverage these powerful tools to build efficient and responsive applications. Thank you for joining me, and I look forward to seeing you in the next lesson. Now let's take a look at how we can effectively use anonymous struct literals in Zig by implementing a simple test case. In this example, we first define a struct called point, which includes two fields, x and y, both of type I32. This struct represents a point in a 2D space. Next, we will write a test case that demonstrates the utility of anonymous struct literals. Instead of explicitly creating a point instance using a formal struct type definition, we can directly instantiate pt with an anonymous struct literal. This approach allows us to set values for x and y in a concise manner without needing to define a separate variable. In the test, we use Zig's testing features to verify that the values of ptx and pty are correctly initialized to 13 and 67 respectively. By utilizing anonymous structs, we enhance the cleanliness and efficiency of our code, reducing unnecessary boilerplate and potential errors. This not only makes our code more robust, but also aligns perfectly with Zig's philosophy of safety and performance in systems programming. Now let's see how we can implement a fully anonymous struct in Zig, which showcases the language's flexibility in accepting various data types. In this example, we define a test case that invokes the check function by passing an anonymous struct literal with multiple key-value pairs representing different types, such as an integer, a float, a boolean, and a string. The check function accepts an argument of type anytype, allowing it to adopt any struct that provides the specified fields. As we execute several assertions within the function, we verify that each field adheres to the expected values. For instance, we check that args int equals 1234 and that args float is 12.34, demonstrating Zig's capability to directly access fields by name without the need for explicit type declarations. This approach not only streamlines the code but also takes advantage of Zig's type inference, allowing us to handle varied data types dynamically and efficiently. Thus, using anonymous structs provides a powerful feature for writing succinct and expressive Zig code, particularly when designing functions that require versatility in argument types. Now let's take a look at how we can utilize tuples to group various types of values efficiently in Zig. In the first snippet, we define a tuple named values, which holds 4 elements of different types: an unsigned integer, a floating point number, a boolean, and a string. The elements of the tuple can be accessed using their numeric indices, similar to how we access array elements. This demonstrates the tuple's flexible structure while emphasizing the ease of retrieving values without needing to define field names explicitly. Next, we'll see how to verify the contents of our tuple using assertions. We check that the first element equals 1234 and verify the length of the tuple, ensuring that it contains 4 elements as expected. Notably, we can also access the string within the tuple and confirm that the first character is h, showcasing how tuples allow for mixed data types without sacrificing access simplicity. Furthermore, we can implement an inline for loop to iterate over the values in the tuple. This method highlights the succinctness of tuple manipulation, allowing us to perform operations on their elements in a straightforward manner while enhancing the expressiveness of our code. This flexibility is essential when managing diverse data types in a clean and efficient way. Now let's see how we can implement a compact solution to calculate the minimum and maximum values from a series of digits using Zig's destructuring feature. In this example, we start by defining an array of integers, digits, containing a set of numbers. To efficiently determine the minimum and maximum, we use a block denoted by BLK, where we can define local variables for min and max. Here we initialize min to the maximum possible I8 value and max to the minimum possible. The iteration happens through each element in the digits array using a for loop, where we evaluate if the current digit is less than min or greater than max, updating them as needed. Upon completion of the iteration, we return both values as a tuple by breaking out of the block. This is where destructuring shines. We can unpack the tuple directly into the min and max variables, enhancing code clarity and minimizing clutter. Finally, we display the results using the print function, showing how cohesively this approach allows for both readability and efficient data handling in Zig. Now, as we learn about anonymous structs and tuples, it's important to keep in mind the efficiency Zig provides in terms of memory management. When we omit the struct type of a literal, the struct literal directly instantiates the result location, which means no copying occurs when we're working with structures. This is particularly useful in systems programming, where efficiency is paramount. So, let's wrap up what we've covered. We've explored the foundational principles of handling anonymous structs and tuples in Zig. We have examined how these constructs can help us write cleaner, more efficient code while simultaneously maintaining readability. As we move forward in our exploration of Zig, we will now turn our attention to concurrency and task management. With Zig's focus on safety and performance, these features will significantly enhance application development, paving the way for building robust applications that efficiently utilize system resources. Stay tuned as we dive deeper into these advanced topics, because understanding concurrency can be the key that unlocks the full potential of your applications, allowing them to perform with speed and reliability. Now let's take a look at how to work with arrays and slices in Zig. In the code, we begin by declaring a fixed-size array, which is a fundamental data structure that holds a predetermined number of elements. Here, we've created an array of 3 unsigned integers initialized with the values 1, 2, and 3. Next, we create a slice that references the entire array. This slice is significant because it allows us to interact with a subset of the array's data without copying it, enhancing performance. Slices provide a flexible way to manipulate data, letting you work with portions as needed. After defining these structures, we utilize the std debug print function to output the contents of both the array and the slice. This visibility into data allows us to see how the slice behaves in relation to the original array. With these tools, you can efficiently manage and access data, which is central to programming in Zig. Now let's take a look at how we can efficiently use slices in Zig to work with portions of an array. In this example, we define an array called numbers that contains 5 unsigned integers. By specifying a range, we create a slice from the original array that includes the elements from index 1 to index 4, effectively extracting a subarray that includes the values 2, 3, and 4. Next, we iterate over this slice using a for loop, which allows us to access each item in the slice sequentially. This approach emphasizes Zig's clean and expressive syntax, enabling you to focus on your logic without becoming overwhelmed by complex syntax. As we print each item in the slice to the console, this demonstrates not only how to manipulate array segments, but also how slicing promotes memory safety by preventing out-of-bounds access. By utilizing slices this way, you can handle data more flexibly and efficiently in your applications, showcasing one of Zig's standout features, a strong emphasis on both performance and safety in memory management. Zig is much more than just a syntax and a set of rules. It's about building a robust solution with an eye on performance and safety. As you continue your journey in programming with Zig, remember that every feature you learn interlocks with the concepts of clarity, performance, and safety. I hope you're as excited as I am about the power of Zig programming and its clean approach to both documentation and the overall structural integrity of code. Embrace the intricacies, keep practicing, and soon enough, you'll be adept at crafting elegant programs in Zig that are not only efficient but are also a joy to read. Now let's implement a packed struct that efficiently represents GPIO registers. We define a GPIO register struct where various GPIO pins are represented as Boolean values packed into a single byte alongside reserved bits for alignment. This compact structure allows for streamlined memory usage while enabling direct manipulation of individual GPIO pins. Next, we will explore a function called write-to-GPIO, which demonstrates the proper way to update the GPIO register state. Instead of modifying the GPIO registers directly using field access, which could lead to inconsistencies due to potential race conditions, we create a new GPIO register instance named NewStates. This instance holds the intended GPIO state, and we then write this entire state to the volatile pointer representing the register. This encapsulation protects the integrity of the data by ensuring all changes occur simultaneously, preventing partial updates that could destabilize the system. By adhering to these practices, we gain not only performance efficiency but also reliability within our system's interactions with hardware components, key elements in systems programming. Now let's take a look at the packed struct we have defined named bit field. This structure showcases an efficient way to allocate bits in memory, allowing multiple fields to share the same memory locations. In this example, we have three fields, A, B, and C, each declared with varying bit widths. Particularly, A and B each occupy 3 bits, while C occupies 2 bits. The compact nature of packed structs allows us to conserve memory, but it also requires careful handling of each field's offset. Next, we will see how the initialization of these fields works. We create an instance of bit field named bit field, assigning values to each of these fields. The real intrigue comes in the test case named packed struct addresses, where we can explore the memory addresses of these fields directly. By using pointers to access their addresses, we can verify that A, B, and C overlap in memory, demonstrating the essence of packed memory representations. This overlapping is double-edged. Although it saves space, it necessitates a deep understanding of how the fields interact to avoid unexpected behavior. Understanding these nuances equips you with the knowledge to effectively utilize packed structs in real-world applications. Now let's see how we can implement dynamic memory allocation for structs in Zig. In this example, we utilize the page allocator provided by Zig's standard library to create an instance of a custom struct, myStruct. This allocator serves as a means to manage memory explicitly, which is crucial in systems programming where performance and memory efficiency are paramount. We begin by defining the allocator variable, linking it to the page allocator. This enables us to use dynamic memory management capabilities that Zig offers. The create method is called on the allocator to instantiate myStruct. If this operation fails, it will invoke the catch unreachable clause, terminating the program, which underscores the importance of error handling in memory management. Once the struct is created, we use the defer statement to ensure the memory allocated for myStruct is deallocated automatically when the function exits, even if it exits unexpectedly. This practice not only prevents memory leaks but also promotes safer programming habits. After allocation, we can initialize and utilize myStruct by assigning values to its fields, showcasing effective dynamic memory usage while adhering to Zig's principles of manual memory management. Now let's take a look at how we can manage struct alignment in Zig to enhance performance. In the example, we define a structure named myAlignedStruct that contains two fields, A and B, each with explicit alignment specifications. The field A is aligned to 4 bytes while field B is aligned to 64 bytes. This careful placement not only ensures that the data is accessed more efficiently by the CPU, but also helps avoid potential performance penalties that can result from misaligned data access. Next, we create an instance of myAlignedStruct, initializing its fields with specific values. To test our alignment setup, we run assertions that verify the alignment characteristics of the structure and its fields. We check that myAlignedStruct itself has an overall alignment of 64 bytes, reflecting the alignment of its highest aligned field. Additionally, we verify that the types of the individual fields, A and B, conform to their specified alignments. This code demonstrates how Zig allows developers to explicitly manage data alignment, which is crucial for optimizing performance in systems programming. Now let's delve into error handling within structs. In the following example, we introduce a config struct that includes a field named value of type U32. The key feature here is the setValue function, which allows for modifying the value while enforcing a validation rule. The new value must not exceed 100. This function returns an error if the input violates this condition, demonstrating Zig's robust error handling capabilities that help maintain data integrity. As we implement the setValue method, we use a conditional check to determine if the new value is valid. If it surpasses the specified limit, we return an invalid value, allowing the function to signal an error back to the caller without compromising the state of the config struct. This approach exemplifies Zig's emphasis on safety, giving developers control over the state of their data structures. In the test function, we instantiate a config instance and then attempt to set its value to 101, which triggers the error handling mechanism. This reinforces the importance of data validation in system programming, ensuring that your configurations remain within acceptable bounds and preventing potential issues down the line. Now let's see how we can implement a method to compute values using structs in Zig, particularly focusing on the concept of destructuring. The function computeValues is defined to return a struct that contains two fields, min and max, both of type i32. This structure simplifies the handling of multiple return values by allowing us to package the related data together, for instance, returning both the minimum and maximum values from a computation. Next, we have a test case that demonstrates how to utilize the computeValues function. Within this test, we call computeValues and use the try keyword, which conveniently handles the error if the function returns 1. Once we have the result, we destructure the returned struct into variables min and max, which simplifies our access to these values. Instead of referencing the fields with a cumbersome syntax, destructuring allows us to unpack the content directly and improves code readability. Finally, we verify that the values of min and max are as expected, ensuring both the functionality and the utility of our approach in maintaining clear and maintainable code. Now, as we begin wrapping up this comprehensive look into advanced struct and memory management, I want to emphasize that while Zig provides powerful tools for struct manipulation and memory control, the onus is on you as the developer to use these tools judiciously. Proper understanding of bit manipulation, memory alignment, error handling, and dynamic allocation is the backbone of writing efficient and safe systems programs. Being mindful of these practices will not only make you a better Zig programmer, but will also equip you with the skills needed to build robust applications that can handle the complexities of real-world systems programming without compromising performance. In our next lesson, we will transition our focus onto concurrency and task management, essential components that can unlock the full potential of your applications, helping them operate efficiently in multi-threaded environments. Keep honing your skills and get ready for the exciting challenges that lie ahead. Welcome to this tutorial on the best practices for working with tuples in the Zig programming language. Tuples are a powerful feature that allows you to group related data into a single data structure. Today, we'll dive deep into their characteristics, usage, and some best practices to consider while working with them. So far, we learned about advanced struct and memory management in the Zig programming language, emphasizing its performance and safety features. We covered topics such as field access, packed structs, and the critical importance of proper memory allocation and alignment. The lessons highlighted techniques to handle dynamic memory safely and emphasized the role of error handling to maintain data integrity. As we wrap up, we prepare to shift our focus to concurrency and task management in the next lesson. Now we'll talk about tuples and how to use them effectively in your Zig programs. Tuples can be seen as a list of values that can be of different types, making them quite flexible. Their structure is similar to that of arrays, but with a significant difference. Tuples can hold a mix of different data types, while arrays are limited to elements of the same type. Now let's see how we can implement a basic example of a tuple in Zig. In this code, we start by importing the standard library and defining the main function. We create a tuple containing 4 different types of values: a 32-bit unsigned integer, a double precision float, a boolean, and a string. This demonstrates tuples' capability to hold mixed data types, showcasing their versatility. Next, we access each element of the tuple using its index. The index for accessing tuple elements must be known at compile time, which ensures type safety and allows the compiler to perform checks. We then assign each value to a corresponding constant variable number, decimal, boolean, and text. Finally, we utilize the std debug print function to output these values in a formatted string. This highlights how easily we can print multiple data types from a single tuple, effectively managing diverse data in a simple structure. This example not only illustrates how to define and access a tuple, but also emphasizes the practical advantages of using tuples for organizing related data in your programs. Now let's see how to leverage the len property of tuples in a practical implementation. In the code, we begin by defining a tuple named myTuple containing 5 integer values. This illustrates the versatility of tuples to hold multiple elements of the same type. Next, we access the length of the tuple using the len property and print it to the console. This feature is particularly useful, as it enables us to understand the tuple's size before we begin iterating through its elements. Following this, we utilize a for loop to iterate over each item in the tuple. The for loop structure allows us to not only access each element but also its corresponding index, enhancing our ability to manage the data effectively. Within the loop, we print each value along with its index, showcasing a clean and efficient method for processing tuple data. This approach not only emphasizes the ease of tuple manipulation in Zig, but also exemplifies how tuples can streamline code while promoting clarity and functionality in handling collections of data. Now let's see how we can implement the ability to concatenate tuples and work with duplicates using the plus plus and asterisk operators. In this example, we start by defining two tuples. First tuple, which contains the integers 1, 2, and 3, and second tuple, consisting of 4 and 5. By utilizing the plus plus operator, we create a new tuple called combined tuple that merges the elements of both first tuple and second tuple. Furthermore, the asterisk operator allows us to duplicate the elements of second tuple, effectively repeating it twice within our new tuple. The result is a combined tuple that contains all elements from first tuple followed by two instances of second tuple, showcasing the flexibility of tuples. We can easily access the length of this resulting tuple using the len property, which provides an efficient means to understand its size. Additionally, we loop through combined tuple, printing each value alongside its index, which reinforces the tuple's ability to provide indexed access similar to arrays. This example effectively demonstrates how tuples in Zig can be leveraged for dynamic data manipulation. Next, we will write a function to demonstrate tuple destructuring in Zig. The function divmod takes two parameters, numerator and denominator, and returns a tuple containing the results of division and modulus operations. This design leverages Zig's ability to return multiple values through tuples, enhancing usability when functions are intended to yield more than one output. In the main function, we are going to see how destructuring can streamline our code. We call divmod with values 10 and 3, and by using destructuring, we unpack the return tuple directly into the variables div and mod. This means we can immediately use these values without the need for additional indexing, which can enhance readability and reduce potential errors. Moreover, with the exception handling via the catch keyword, we ensure that any issues during the division or modulus calculations are appropriately managed, displaying an error message without crashing the program. Finally, we print the results, showcasing both the quotient and remainder. This whole process exemplifies efficient code structuring when dealing with functions that require multiple return values. As we dive deeper into the best practices for tuples, it is essential to consider how to handle the possible errors that arise from operations involving them. Zig emphasizes safety, so proper error handling becomes critical when manipulating tuples. Utilizing error handling via the catch keyword helps manage situations in which tuple access might return an invalid outcome. In our previous destructuring example, we added exception handling to catch any potential errors from divmod, thus maintaining the integrity of our program. As you're embracing tuples in your coding journey, remember that tuples aren't always the best choice for every scenario. While they are extremely versatile for grouping related data, if you find yourself using tuples where the size and type of elements vary greatly or where you're frequently modifying contents, consider whether structs or arrays might be better suited for the job. For example, if you need to store user information such as a name and age, a struct might provide clearer field definitions, while tuples might suffice for quick data packing in smaller scopes. It's also crucial to understand that tuples in Zig are immutable by default. This means that once you've defined a tuple, you cannot change its values. This immutability feature aligns with Zig's goals for safety and performance, enabling the compiler more freedom to optimize. If future modifications might be necessary, consider whether the usage of a different data structure, such as a mutable array or struct, fits better. By determining where immutability makes sense, you maintain both integrity and efficiency in your code. In conclusion, tuples in Zig provide an excellent way to group different types of data into a singular manageable structure. We covered their key features such as indexing, len access, and the powerful plus plus and asterisk operators. Through examples, we demonstrated how to efficiently destructure tuples and handle potential errors properly. Keep in mind when tuples are the right choice versus other constructs, and embrace their immutability as a means to enhance your program's safety. In our next lesson, we will pivot toward concurrency and task management, an exciting frontier in programming that opens up possibilities for creating responsive and efficient applications. Thank you for joining this exploration into tuples, and I look forward to our next session. Now let's see how we can implement a simple enumeration in Zig to represent colors. In this code, we define an enum called color that maps specific colors to numerical values, enhancing code readability. Each color, red, green, and blue, is assigned an integer, allowing us to refer to these colors by name rather than arbitrary numbers. This approach significantly improves the clarity of our code. Next, we implement the main function, where we declare a variable myColor of type color and assign it the value color green. This directly demonstrates how to work with the enum we defined earlier. After selecting the color, we use std debug print to output the selected color. Zig makes it easy to print enum values, which are automatically converted to their underlying integer representation when required. However, for clarity and maintaining context, these enums foster better understanding by framing these integers with meaningful names. This simple yet powerful illustration shows how enums can make our codebase more understandable and maintainable, allowing us to avoid the confusion that comes with using plain integers. Now let's see how we can implement string representations for our enum values, which adds clarity when debugging or logging. In this code, we define an enum named color with 3 members, red, green, and blue. The purpose of this enum is to represent different colors in our application more effectively than using plain integers. Next, we create a function called colorToString, which takes a color enum value as an argument and utilizes a switch statement to return the corresponding string for each color. This translation between enum values and their string equivalents is crucial as it enhances the transparency of our code. When we print the selected color, we retrieve not just the numeric value but also its name, providing valuable context. In the main function, we declare a variable myColor, setting it to color green. We then call colorToString with myColor and handle any potential errors gracefully using the catch construct. Finally, we employ std debug print to display both the numeric value of myColor and its corresponding name, reinforcing the benefits of using enums for clarity and maintainability in our code. Now let's see how we can implement a secondary color enum that builds on our primary colors, ensuring we retain the original definitions. In this example, we first define an enum called primary color with 3 fundamental colors, red, green, and blue, each assigned a unique integer value. This foundational enum allows us to represent the 3 primary colors clearly. Next, we introduce a union enum named secondary color. Rather than creating separate constants for each secondary color, we derive them from combinations of the primary colors. For instance, yellow is created by adding green and red, cyan is produced from green and blue, and magenta is a result of blending red and blue. This approach cleverly keeps the original color values intact while extending the enum's functionality, demonstrating code reuse and clarity. Finally, the main function allows us to declare a variable of type secondary color and assigns it the value of yellow. The program then prints the resulting secondary color, illustrating how we can leverage enum features in Zig to create expressive and manageable code structures that represent color combinations effectively. Now let's see how we can implement methods within an enum to encapsulate related behaviors. In the code, we define an enum called color that includes 3 primary colors, red, green, and blue. What's interesting here is that we enhance the enum's functionality by adding a method named complementary. This method determines the complementary color based on the current color instance it operates on. It uses a switch statement to return the corresponding complementary color, enabling a direct mapping from each color to its opposite color. Red yields color, cyan color, green becomes color, magenta, and color blue corresponds to color yellow. Next, we demonstrate how to utilize this method in the main function. We create a variable of type color, assigning it the value color red. To find the complementary color, we invoke the complementary method directly on this color instance. The result is then printed using std debug print, showcasing how well-structured and modular the approach is. By linking colors and their complements directly in the enum, we create a clear association that enhances the maintainability and readability of our code, illustrating the power of enums in organizing related functionality effectively. Now let's see how we can implement an enumeration to handle operation outcomes in a clean and effective manner. In this example, we define an operation enum that represents 2 possible states, success and failure. This enum provides a clear and type-safe way to convey the result of an operation. The perform operation function takes a Boolean input that indicates whether the operation was successful or not. Based on this input, the function returns the corresponding enum variant, either operation success if the operation succeeds or operation failure if it does not. This encapsulation of the operations result enhances code readability and maintainability by clearly specifying what the expected outcomes are. Next, we use a switch statement to handle the result of the operation. Depending on whether the result is operation success or operation failure, we print an appropriate message to indicate the operation's status. This approach demonstrates how enums can improve error handling by allowing us to represent and manage various states in a straightforward manner, ultimately reducing ambiguity in our code execution flow. Now let's see how we can implement a combination of enums and tagged unions to represent different geometrical shapes. In this code, we define an enum called shapeType, which indicates the various types of shapes we can work with, specifically a circle, square, and triangle. This enum provides a clear and distinct designation for each shape type. Next, we create a shape union that utilizes the enum to define different structures, each representing a specific shape. For instance, the circle structure contains a radius, while the square has a side length and the triangle includes a base and height. This design encapsulates the properties relevant to each shape, allowing us to manage these different types coherently. We then implement the calculatoria function, which takes a shape as an argument and uses a switch statement to determine the area based on the actual type of shape provided. This demonstrates the flexibility of enums when they are combined with unions. Finally, in the main function, we instantiate a shape as a circle with a given radius, calculate its area, and print the result, showcasing how this structure simplifies working with different shape types while maintaining clarity in the code. Now let's explore how we can implement a finite state machine FSM using enums in Zig. We start by defining an enum called state, which represents the different states our system can be in: idle, running, and stopped. This clearly delineates the possible conditions that our program might encounter, enhancing the clarity of our code. Next, we create the handleState function, which takes the current state as an argument and employs a switch statement to determine the appropriate behavior for that state. Depending on whether the state is idle, running, or stopped, the function will print a corresponding message to the console, providing clear feedback on the system's status. Finally, in the main function, we loop through all the states defined in the state enum, passing each one to the handleState function. This simulates transitioning through the states and demonstrates how our system reacts to each distinct condition. By organizing our states into an enum and handling them through a dedicated function, we not only make the code more structured, but also facilitate easier modifications and scaling in the future. As we conclude this lesson on advanced techniques for enums, remember that these are just a few examples of how enums can enhance your code's readability, maintainability, and overall structure. Enums can keep your codebase organized while providing clarity through named constants, associated values, and methods. They allow you to handle complexity in a manageable way, especially when combined with other data structures like unions and structs. Now that you have a strong foundation with enums, the possibilities for clean and effective code are endless. Prepare to take your Zig programming to the next level as you build solutions that use these advanced enum features seamlessly. Our next lesson will delve into concurrency and task management, where you'll discover how to make your programs more responsive and capable of multitasking. Bare unions in programming languages are intriguing structures that allow for flexible data representation. A bare union defines a set of possible types that a value can take as a list of fields, but crucially, only one field can be active at a time. This unique feature of unions makes them valuable for managing memory efficiently and representing multiple types within the same data structure. So far, we learned about advanced techniques for enumerations in Zig, focusing on how they enhance code readability and maintainability. Now, we will dive into the union types, their operations, and practical use cases, demonstrating how they can enhance our coding practices with examples that will clarify this concept thoroughly. Now let's see how we can define a union in Zig that efficiently handles multiple data types. In our code, we declare a union called payload, which has 3 fields: an integer, a float, and a boolean. This structure allows us to use only one of these fields at any given time, thereby optimizing memory usage. For instance, we initialize our union with an integer value of 1234. This means at this moment, only the integer field is active. Next, we attempt to assign a value to the float field directly without changing the active state of our union. This action results in an error because the union allows access to only the currently active field. This design choice is instrumental in preventing accidental misuse of data types and reinforces the need for careful management of the union's state by the developer. Such precautions ensure that our program remains reliable and helps avoid bugs that might arise from type mismatches. This illustrates not only the versatility of unions but also the importance of understanding their operational intricacies. Now let's see how we can safely interact with unions in Zig by reassigning the entire union to change the active field. The first step involves initializing our union, payload, with an integer value assigned to payload, int. Here we use the expect function to verify that our union correctly reflects this active field by checking if payload, int equals 1234. Next, we can switch the active field from an integer to a float. We accomplish this by creating a new instance of the union with the float field, which we can do by writing payload equals payload, float equals 12.34. This reassignment is crucial because it ensures that the union is safe and maintains the integrity of its state. After reassigning, we again verify the active field by checking payload float, ensuring it equals 12.34. This pattern highlights how unions allow for easy transitions between types, making them flexible and efficient for scenarios where value types frequently change. This elegant method of switching states emphasizes the safety and clarity that unions provide in our programming practices. Now let's implement a tagged union in Zig to manage multiple states more effectively. In our code, we define an enumeration named complex type tag with two possible values, OK and not OK. This tag will help us identify which union field is currently active. We then declare the complex type union, which comprises different fields. OK, representing a successful state with an associated U8 value, and not OK, which has a void type indicating a failure state that requires no additional data. Next, we will create an instance of this union by initializing it with the successful state, setting it to a value of 42. With this setup, we can now utilize a switch statement to check the current state of our union. The switch provides a clear path for handling each case. If the state is complex type tag OK, we can retrieve the value and perform any necessary operations, such as ensuring it matches our expectation. Conversely, if the state is complex type tag not OK, we mark it as an unreachable case since we anticipate that it won't occur. This design enhances our code's robustness and readability, allowing us to manage different union states more effectively. Now let's see how we can modify the active value of a tagged union using a switch statement and pointers. In the provided test function, we create an instance of complex type with the tag set to OK, and we initialize it with a value of 42. This setup allows us to safely interact with the union's fields based on its current state. Next, we implement a switch statement to determine which tag is currently active in the union. In the case where the tag is OK, we use a pointer to directly access and modify the active value. This is done by dereferencing the pointer and incrementing the value by 1. Such direct manipulation is particularly advantageous since it ensures that we are modifying the right data type associated with the active tag. Finally, after the switch statement, we verify our modification by asserting that the value of COK has now been updated to 43. This example effectively illustrates how to safely alter the contents of a tagged union and highlights the usefulness of using pointers for in-place modification, which enhances state management in applications like finite state machines. Now let's take a look at how we can implement a union in Zig that includes a method for evaluating its active state. The union named variant is defined to hold one of three possible types, an integer, a boolean, or a special none state. What makes this union particularly interesting is the method truthy, which assesses the value of the currently active field. Within this method, we use a switch statement to evaluate the type stored in the union. For instance, if the active field is an integer, the method checks if it is not equal to 0, thus determining if it's a truthy value. If the active field is a boolean, it simply returns its value since in programming, true is typically considered truthy and false is falsy. The none state, on the other hand, is explicitly treated as falsy. Next, we will write a test that demonstrates how this method can be utilized. In the test, we create instances of the variant union for different scenarios, one holding an integer that evaluates to truthy, one holding a boolean that is falsy, and one representing the none state. By executing this test, we can see how the truthy method effectively determines the truthiness of each active field, illustrating the power of combining data and behavior within our union. Now let's see how we can dynamically access the names of union fields at compile time using the @tagname function. In this example, we define a union called small2 with three fields, a B and C, representing different data types. The key feature here is the ability to retrieve the name of the currently active field using @tagname. This function allows us to obtain the field's name as a compile-time constant, which can serve various purposes, including debugging and creating more adaptable code. In this specific test, we check the dynamic name of the field A by calling at tag name small2a. The expectation set by try_expect std mem equal u8 at tag name small2a ensures that the retrieved name matches the string a. This capability is incredibly useful in scenarios where you may want to log or handle fields based on their names, providing greater context sensitivity in your applications. Thus, by leveraging at tag name, you enhance your union's functionality and increase code robustness, offering a solid tool for addressing dynamic behaviors in your Zig applications. As we can see, unions in Zig provide a powerful method for managing multiple types in memory while ensuring safety and preventing type mishaps. They are not just containers, they are dynamic structures that can evolve with your code, improving readability and maintainability. So far, we have explored unions extensively, looking at how to define them, the safety mechanisms in place like error handling, and effective ways to switch between types. In our upcoming discussions, we'll apply what we've learned to real-world examples in concurrency and task management. Now let's see how we can implement a union that utilizes an enum tag to manage multiple user statuses efficiently. In this code, we start by defining a status tag enum that describes 3 potential states for a user profile: active, inactive, and deleted. This enum serves as a clear identifier for the state of the union, enhancing code readability. Next, we create the user status union, which leverages the status tag enum as its tag. Here we specify that when the user is active, a Boolean value is stored. When inactive, a floating point number representing the duration of inactivity is held, and for deleted users there is no value at all, void. This structure promotes clarity. By looking at the user status union, developers can immediately understand what each state represents. Another invaluable aspect of our implementation is the method encapsulation within the union. By integrating behavior directly into the union, we promote a cohesive structure where data and its associated operations are bundled together. This not only organizes our code, but also prevents potential errors by ensuring that state management occurs within defined methods. Now let's take a look at how we can implement user status management using the checkUserStatus function, which effectively utilizes a tagged union. This function takes a user status union as input and employs a switch statement to evaluate the active state of the user. Depending on the user's status, active, inactive, or deleted, the function executes different behaviors. For active users, it displays a simple message confirming their status. In the case of inactive users, the function prints out the number of days they have been inactive, enhancing user engagement by providing context. Lastly, for deleted users, the function outputs a message indicating that the account has been removed. This approach not only maintains code clarity by leveraging the enum tags for state management, but also strengthens type safety. By conducting a thorough evaluation of the union's value, the compiler ensures that you are accessing valid fields associated with each state, which minimizes the risk of errors. With this structure, each branch clearly represents its logic, making it easier to understand and maintain as your application evolves. Now let's take a look at how to integrate methods directly into our user union. This is where the power of encapsulation truly comes to life as we create an update method that modifies the internal state of the union based on incoming parameters. We define a function called update, which accepts a mutable reference to the user union and a new status, allowing it to update the user's state seamlessly. Inside the update method, we use a switch statement to determine the type of the new status. Depending on whether it is active, inactive, or deleted, we appropriately assign the new state to the union's active field. This structure ensures that we can manage user states in a clean and organized way, centralizing state transition logic within the method rather than scattering it throughout the codebase. By leveraging this method, we simplify the process of state updates, making it clear how transitions occur. This approach not only keeps the code modular but also adheres to object-oriented principles, enhancing readability and maintainability. The encapsulation of behavior within the union aligns data closely with its functionality, which is a cornerstone of effective programming practice. Now let's implement an example that demonstrates the practical usage of our update method to manage a user's status. In this test scenario, we initiate a variable userStatus set to user active, indicating that the user is currently active. This structure allows us to hold different data types based on the user's status, ensuring type safety through the use of our defined union. Next, we invoke the update method to change the user's status to user inactive, passing a floating point value representing the duration of inactivity. This showcases how the method smoothly transitions the user's state while keeping the code clear and organized. Following this update, we utilize the checkUserStatus function to verify that the status change has taken effect, displaying relevant information about the user's current status. Finally, we demonstrate another status transition by marking the user as user deleted. Again, we call checkUserStatus to confirm that the status update was successful, which should yield a message indicating that the user account has been deleted. Through this process, we can see how the update function effectively manages transitions between various user states, enhancing maintainability and comprehension in our codebase. Now let's take a look at how we can implement a method within our tagged union, user, to provide dynamic status messages based on the current state of a user. The status message method is defined as a member of the user union, enabling it to return a descriptive message depending on whether the user is active, inactive, or deleted. When the method is called, it employs a switch statement to evaluate the current status of the union. If the user is marked as active, the method returns a string indicating that the user is active. Similarly, if the user is inactive, the message reflects that status, providing clarity about the user's inactivity. Lastly, when the user account is marked as deleted, the method returns a specific message signifying that the account has been removed. This encapsulation of behavior allows methods to leverage the underlying data in a structured way, enhancing the readability and maintainability of the code. By consolidating status-related logic within the union, we create a cohesive structure that simplifies user state management while providing meaningful feedback to the program's users. Now let's take a look at how we can implement a test to retrieve user status messages using our user union. The test begins by initializing user status to the active state, signified by user, active true. This sets the user status to active and allows us to call the status message method, which provides a human-readable message reflecting the current status. By utilizing the std-debug print function, we output this message, which informs us that the user is active. Next, we simulate a status update by changing the user state to inactive with a duration of 3 days using the update method. Again, we call status message to display the updated message, which indicates the user has been inactive for a specified duration. Finally, we transition the user's status to deleted by invoking userStatus. Update user deleted void. The last call to status message confirms that the user account has been marked as deleted. Through this code, we can see how the dynamic nature of the union's methods can provide meaningful feedback based on the user's current state, showcasing the seamless integration of enums and methods for effective state management. Creating unions that can infer enum tag types and contain methods enables a level of elegance and simplicity in how you manage states and behaviors in your code. By adopting these practices, you not only maintain memory efficiency, but also enhance the readability and maintainability of your codebase. Incorporating enums as tags and methods within unions allows you to encapsulate logic neatly and fosters an object-oriented approach in a procedural programming context. This synergy of methods and data structures creates more intuitive interfaces, making it easier for others who come across your code to understand its intention and functionality. In summary, we've explored the advanced features of unions, such as inferring enum tag types for state management and encapsulating methods for behavior. By adopting these techniques, you can create flexible, clear, and maintainable code that adapts easily to changing requirements while maximizing efficiency. Union types allow you to design complex systems without sacrificing code quality, making your programming endeavors not just productive but enjoyable as well. Switching is an essential programming concept that allows developers to control the flow of execution based on the values of variables. In this session, we are focusing on using enum literals with switch statements. By the end of this tutorial, you will understand how to enhance your code structure using enums in various programming scenarios. So far, we've covered the advanced usage of unions in programming, specifically how they can infer enum tag types and encapsulate methods. We've discussed managing multiple data types effectively using enum tags for clearer state management, in addition to integrating methods within unions to improve organization and functionality. These techniques promote an object-oriented approach in procedural contexts, making code more intuitive and adaptable. Now, we will talk about how we can implement switching using enum literals to streamline our flow control and enhance code readability. Now let's see how we can implement a switch statement using our defined day of week enum to determine activities based on the current day. In this example, we first assign the value for today to be day of week, Wednesday. Following that, we use a switch statement to evaluate the value of today. Each case of the switch corresponds to a different day of the week, and we provide an activity for each day. For instance, if today is Sunday, the assigned activity will be relaxing. On a Friday, it will be potty. This use of shorthand notation with before each case improves readability, allowing us to focus on the values rather than the enum type itself. The selected activity is then printed with a debug statement, clearly indicating what we plan to do today. This method enhances organization by associating specific behaviors with clearly defined states, which not only makes the code easier to read, but also improves maintainability by ensuring you can effortlessly adapt or update activities in the future. Now let's see how we can implement a switch statement using enums to manage actions based on the days of the week. In the code, we start by defining an enum called day of week, which includes named constants representing each day. This approach not only makes our values more readable, but also prevents mistakes that could arise from using plain integers. We specify today as day of week, Wednesday indicating the current day. Next, we create a switch statement that evaluates the value of today. Instead of using the full enum type in each case, we can leverage the shorthand to express our case values, making the syntax cleaner and easier to read. Each case corresponds to a different activity, relaxing on Sunday, working on weekdays, and various weekend activities like pottying and hiking. Finally, the selected activity is printed using the standard debug print functionality. This method of using enums with switch statements offers a structured and intuitive way to manage flow control in our application, enhancing both clarity and maintainability of the code. Now let's take a look at how we can expand our enum to include additional values and enhance our switch statements functionality. In the updated code, we introduce a new value, holiday, to our day of week enum, which represents a special day. This change emphasizes the importance of exhaustive switching, a feature that mandates coverage of every possible enum case in a switch statement. In the main function, we set today to day of week holiday. The corresponding switch statement aims to assign an activity based on the value of today. However, we notice that the case for holiday is intentionally left out. This omission is crucial for demonstrating the exhaustive switching feature. Since we haven't accounted for holiday, the compiler will raise an error, prompting us to address the missing case. This mechanism fosters discipline in coding by ensuring that developers consider all potential states. Thus, as we manage states through enums, we encourage thoroughness and attention to detail, which ultimately leads to more robust and maintainable code. Now let's delve into an example of using labeled switch statements in our code. This structure allows us to improve flow control by utilizing a label for the switch statement, which can be particularly helpful when managing multiple states within a program. In this instance, we define an enum called command, which encompasses various states: start, stop, pause, and resume. We set an initial state with the variable current state starting at command start. The switch statement is then labeled as command, allowing us to jump back to this point based on the current state. Within the switch cases, we implement specific behaviors associated with each command. For instance, when current state is command start, the program prints a starting message and transitions to the command pause state using the continue command statement. This continues the execution flow in a clear manner, reflecting the ongoing state transitions. Conversely, other cases such as command pause and command stop either end execution via break or manage state appropriately, demonstrating how labeled switches can aid in organizing complex logic while maintaining code readability. Now let's implement the following example using inline switches to determine the RGB values for different colors efficiently. In this code, we define a color enum with 4 possible values: red, green, blue, and yellow. This establishes a clear and descriptive way to represent colors in our program. Next, we select a color by assigning color, green, to the variable chosen color. Instead of using a traditional switch statement with potentially multiple lines of branching logic, we use an inline switch. Here, each case is prefixed with the inline keyword, allowing the compiler to generate separate branches for each color in a single expression, thus optimizing performance. As we process the chosen color through the inline switch, the The corresponding RGB value is assigned to the variable color value based on the chosen color. Finally, we print the resulting RGB value to the console, displaying it in hexadecimal format. This approach not only simplifies the code but also enhances its efficiency, showing how inline switches can streamline flow control while handling enums in a clean, readable manner. Now let's take a look at how we can use ranges within switch statements to classify age categories effectively. In this example, we start by defining a variable age with a value of 20. The core of our implementation is a switch statement that evaluates the age variable against several defined ranges. Each case corresponds to a specific age group, such as 0 to 12 for child, 13 to 19 for teenager, and 20 to 64 for adult. By utilizing ranges, we can neatly encapsulate these conditions without needing multiple individual comparisons. To handle cases that don't fall within the specified ranges, we use an underscore as a catch-all, which in this case categorizes anyone aged 65 and older as senior. This structure not only optimizes the code but also enhances its readability, making it easier for developers to understand and maintain. Finally, we utilize a debugging print statement to output the determined age category, showcasing how the switch statement simplifies classification based on the value of the age variable. This approach is beneficial when dealing with numeric data or categories, making your code more readable and maintainable. Now let's implement a function to handle responses using enums and switch statements. We begin by defining an enum called status, which represents three possible outcomes: success, error, and unexpected. This structure provides better clarity compared to using raw integer values. Next, we create a function named handleResponse, which takes a parameter of type status. Inside this function, we utilize a switch statement to manage different response cases effectively. As we examine the switch statement, we can see that each case corresponds to a specific enum value. When the response is success, it prints a message indicating that the request succeeded. Similarly, if the response is error, it communicates that an error occurred during the request. When the response is unexpected, it notifies the user of an unexpected response. Importantly, we've included an else case that employs unreachable to signify that any other responses should not occur, reinforcing safety by catching unforeseen outcomes. Lastly, we set up a test to validate our handling of each possible response by calling the handleResponse function with all enum values. This ensures comprehensive testing of the function and guarantees that every path is correctly executed, ultimately leading to a more robust application. Switching is a fundamental concept in programming that allows us to control the flow of execution within our applications based on varying conditions. Today, we'll dive deeper into advanced topics surrounding switching, focusing particularly on exhaustive switching and its powerful implications in code clarity and safety. So far, we learned about the essential programming concept of switching and its application with enum literals. We explored how enums improve code clarity by providing named values and managing different states effectively. Additionally, we discussed advanced techniques such as exhaustive and labeled switches, inline switches, and using ranges to enhance code organization and readability. The importance of thorough testing to ensure robustness in switch statement implementations was also emphasized. Now we will cover exhaustive switching in detail and discuss its benefits, coding techniques, and practical uses in various scenarios. Now let's take a look at how we can implement the traffic light enum and utilize a switch statement to control the flow based on its state. We begin by defining the traffic light enum, which includes three named constants: red, yellow, and green. Each of these constants represents a specific state of the traffic light, enhancing the clarity and readability of our code. Next, we set up the main function, where we initialize a variable light with the value traffic light yellow. This variable determines the current state of our traffic light system. We then implement the switch statement that evaluates the light variable. Each case of the switch corresponds to a different state of the traffic light, specifying the appropriate action. If the light is red, the action is to stop. If it is yellow, it prompts prepare to stop. And for green, it indicates go. To ensure we cover all possible scenarios, we include an else equals unreachable clause. This clause acts as a safeguard, triggering a compile time error if an unexpected value is encountered, thus maintaining the reliability and safety of the program. Finally, we print the determined action, demonstrating how the system responds to the current light state effectively. Now let's implement an exhaustive switch statement to handle all possible values of our traffic light enum. In this switch statement, we account for each defined state by providing a corresponding action for each light signal. For the red state, the action is to stop, while the yellow light tells the driver to prepare to stop, and the green light indicates to go. The final clause, else equals unreachable, serves a crucial role. It addresses any potential conditions that fall outside the enumerated types. If an unexpected value were to reach this point, it would trigger a compile time error, ensuring our program's integrity and protecting against unexpected behavior. Next, we will update our enum to introduce a new state, flashing, which requires us to revisit our switch statement to handle this additional scenario. By explicitly defining the action for flashing, which might be to yield, we make it clear that every state is addressed, thus reinforcing code clarity and maintainability. This practice encapsulates the essence of exhaustive switching, establishing a robust control flow in our traffic light system. Now let's take a look at how we can implement user role management using enums and exhaustive switching in our application. We define an enum called user role that categorizes different roles such as admin, user, and guest. This structured representation not only enhances code clarity, but also clarifies the relationships between different roles. Next, we implement a main function, where we initialize a variable role to represent the current user's role, in this case, guest. To determine the access permissions associated with this role, we utilize an exhaustive switch statement. Each case handles a specific role, providing the corresponding permission string: full access for admin, limited access for user, and read-only access for guest. The key feature here is the use of the else equals unreachable clause, which acts as a safeguard. If a new role is introduced in the future, the compiler will alert the developer to handle it, ensuring that all scenarios are addressed. Finally, the permissions are printed to the console, providing a straightforward output of the user's access rights, effectively demonstrating the utility and safety provided by exhaustive switching. Now let's implement a system that utilizes labeled switches alongside exhaustive switching to handle user roles in an application context. In this example, we define an enumeration called user role, which includes 3 roles: admin, user, and guest. These roles will dictate the access level within the application. Next, we set up a labeled switch statement called action, where we evaluate the current user role. Each case in the switch corresponds to a specific role. For the admin and user roles, we print a message confirming access and use the continue keyword. This allows us to revisit the action switch in case we need to handle further navigation options. Conversely, for the guest role, we print a message and use break, indicating that no further navigation is needed. The inclusion of the else equals unreachable clause serves as a safeguard, ensuring all possible cases are accounted for, thereby reinforcing the principle of exhaustive switching. By seamlessly integrating labeled switches, we establish a clearer and more organized flow of logic in our application, enhancing both readability and control. Now let's see how we can implement a test case to validate user role permissions effectively. In this code, we define a structured type, test cases, which holds each role from the user role enum alongside their expected permissions. By using a slice of structs, we can easily iterate through this collection, facilitating a clear and organized way to test each scenario. Next, we loop through each test case, employing a switch statement to determine the correct permissions based on the user role. Each case within the switch explicitly matches a specific role, yielding a corresponding access level. The inclusion of the else equals unreachable clause is vital, as it acts as a safety mechanism, ensuring that we cover all enum possibilities and prompt compile time errors if new roles are added without corresponding tests. Finally, we utilize an assertion to confirm that the outcome generated by the switch matches the expected result. By adopting this approach, we not only enhance the clarity of our tests but also encourage a proactive testing culture, minimizing the risk of future bugs and solidifying the robustness of our application. As we wrap up our discussion on exhaustive switching, keep in mind that code clarity, maintainability, and safety are paramount. The techniques we've explored today will undoubtedly enhance your programming skills and quality of output. Enums allow for a structured and understandable representation of values, while exhaustive switches secure your code against unwanted scenarios and drive more efficient tests. In conclusion, as you move forward in your journey of software development, embrace exhaustive switching not merely as a technique, but as a cornerstone of clean, reliable, and maintainable codebases. Thanks for joining me in this exploration, and as always, happy coding. A while loop is a fundamental concept in programming that allows you to repetitively execute a block of code as long as a specified condition remains true. This offers a powerful way to automate tasks, perform calculations, or iterate through data until you reach a stopping point. Today we'll delve into the world of while loops, examining their structure, purpose, and practical applications through engaging examples. So far, we learned about the concept of exhaustive switching in programming, highlighting its role in enhancing code clarity and safety. We discussed how using enums in switch statements ensures that all possible cases are handled, preventing unexpected behavior. The importance of thorough testing and maintainability was emphasized, illustrating how exhaustive switching encourages developers to revisit their code with any changes to enumerations, improving code reliability while fostering a proactive testing culture. Now we will cover while loops, how they work, their syntax, and how they can be leveraged to enhance our programming efficiency. Now let's see how we can implement a simple counting mechanism using a while loop. In this example, we start by initializing a variable called count to 1, which serves as our starting point for the counting operation. We then set up a while loop with the condition that count must be less than or equal to 5. This ensures that as long as count holds a value within this range, the loop will execute its block of code. Within the loop, the first action is to print the current value of count, allowing us to observe the output in each iteration. Following this, we increment count by 1, effectively moving to the next number in our count sequence. This process continues with the loop checking the condition after every execution of the block. Once count exceeds 5, the condition evaluates to false, causing the loop to terminate and allowing the program to move on. This straightforward implementation showcases the basic structure and functionality of a while loop, demonstrating how iteration can be used to perform repetitive tasks based on specified conditions. Now let's take a look at implementing a simple guessing game using a while loop. This code begins by defining a secret number which the user has to guess. We start with a guess variable initialized to 0 to ensure the loop condition is met at the start. The while loop here is a crucial component as it continuously prompts the user for their guess until they correctly identify the secret number. Within the loop, we use the input function to obtain the user's guess, converting the input to an integer. This interaction is vital as it allows for real-time user input, creating a dynamic experience. The conditional statements inside the loop offer guiding feedback. If the guess is lower than the secret number, the program informs the user that their guess is too low, whereas guesses that are too high receive a corresponding message. This feedback mechanism not only enhances interactivity, but also keeps the user engaged in the game. Once the correct number is finally guessed, a congratulatory message appears, signaling the end of the game. This straightforward implementation effectively demonstrates how while loops can manage repeated input and provide immediate responses based on user interaction. Now let's take a look at how we can sum numbers from a list using a while loop while placing constraints on our total. In this example, we begin by defining a list of numbers that will be processing and initializing a variable total to hold our cumulative sum, starting from 0. We also introduce an index variable to track our position in the list as we iterate through it. The while loop checks two conditions, whether there are still numbers to process and whether the current total is less than or equal to 20. This dual condition allows us to control the flow of the loop effectively. Inside the loop, we add the current number from the list to total and then increment the index to move to the next number. This continues until we either reach the end of the list or our total exceeds 20. Once one of the conditions is no longer met, the loop terminates and we print the final total. This implementation illustrates the flexibility of while loops in handling both the flow of data and the criteria for processing, emphasizing their utility in managing collections dynamically. Now let's take a look at a common scenario where we need the program to continue running until a specific user input is received. In this code, we utilize a while loop that is designed to run indefinitely by using the condition true, which ensures that the loop does not have a natural exit point on its own. Inside the loop, the program prompts the user to enter a response. Specifically, it asks the user to type Q if they wish to quit the program. The input from the user is stored in the variable response. We then check the value of response to determine if it matches Q. If it does, the break statement is invoked, which exits the loop and allows the program to continue beyond this point. This implementation demonstrates an effective use of an infinite loop for scenarios such as monitoring user input continuously until a specific command is issued. It's crucial to incorporate checks like this to ensure that the loop can be exited gracefully, preventing the program from hanging or running endlessly without user intervention. Now let's take a look at how we can use the continue statement within a while loop to selectively process numbers. In this example, we initialize a variable num to 0 and set up a while loop that continues as long as num is less than 10. Each iteration starts by incrementing num by 1. To demonstrate the continue statement in action, we include a condition that checks if num is even by using the modulus operator. If num is even, the continue statement is executed, which skips the subsequent print statement for that iteration. This means that only odd numbers are printed during the execution of the loop. This design effectively demonstrates how the continue statement provides finer control over which iterations of the loop are executed completely. Instead of terminating the loop when a certain condition is met, it allows for skipping specific iterations, preserving the overall structure and efficiency of the loop. Hence, the loop prints only the odd numbers between 1 and 9, showcasing the flexibility and practicality of while loops in managing flow and enhancing code efficiency. Now let's take a look at a practical example of nested while loops which allow us to manage multiple conditions simultaneously. In this code we begin with two counters, outer count and inner count. The outer loop is designed to execute 3 times, and during each iteration we reset inner count back to 0. This ensures that for each outer loop cycle we start counting the inner loop from the beginning. Within the outer loop, we have an inner loop that runs 5 times for each cycle of the outer loop. This effectively shows how nested structures can be utilized to monitor different conditions. Each time the inner loop iterates, it prints out the current values of both counters, displaying which iteration of the outer loop we are in alongside the current inner loop count. After completing the inner loop, the outer counter increments by 1, moving on to the next iteration. This structure allows us to manage 2 separate loops cleanly, demonstrating the flexibility of while loops in handling complex logic and conditions. Now let's take a look at an interesting feature of while loops, the optional else block. In our example, we initialize a counter variable starting at 0 and create a while loop that runs as long as the counter is less than 5. This loop executes its body, which prints the current value of the counter and increments it by 1 each time. The loop continues to iterate until the counter reaches 5, at which point the loop condition becomes false. What's notable here is the else block that follows the while loop. Once the loop completes its iterations and exits, the code within the else block executes automatically. In this instance, when the counter reaches 5, the loop concludes and the else block prints exited loop. This feature allows us to manage post-loop logic seamlessly, eliminating the need for additional conditional statements to check the loop's completion status. By utilizing the else block, we enhance the readability and cleanliness of our code, highlighting the loop's intent and its final state without complicating the logic with flags or extra checks. In summary, we've journeyed through the vibrant world of while loops. We've covered their syntax, basic implementation, user interactions, and advanced features like the continue statement and nested loops. Alongside practical examples, we've seen how these loops enhance the efficiency and power of our programming. Be it through simple counting exercises, user-driven games, or processing lists, while loops provide a versatile tool for developers. So as you go forth on your programming adventures, embrace the power of while loops and let them boost your code's dynamism and interactivity. Happy coding! Today, we're going to delve into some advanced techniques for while loops that will elevate your programming skills. While loops are fantastic tools for repetitive tasks, but did you know they can handle error conditions elegantly as well? This lesson builds upon our previous discussions about while loops, where we covered their structure, syntax, and practical applications. So far, we learned about while loops, a key programming concept that enables repetitive execution of code as long as a specified condition is true. We explored their structure and syntax, along with practical applications such as user interactions and processing collections. Additionally, we discussed advanced features like infinite loops, the continue statement, and optional else blocks. Overall, while loops enhance programming efficiency and interactivity, making them a vital tool for developers. Now, we will explore how while loops can leverage error unions, incorporate error handling, and enhance control flow in your code. Now let's take a look at how we can effectively gather user input using a while loop that handles potential errors gracefully. In this code, we begin by defining a custom function called getInput that attempts to read a number from the user. If the input is valid, it converts it to an integer and returns it. However, if the user enters something invalid, such as a letter, it catches the value error and returns an error message instead. Next, we create an infinite while loop that repeatedly calls this getInput function. The result of the input is stored in the result variable, which we then check to determine its type. If the user input is indeed a valid integer, the program confirms the input by printing it out and, if applicable, comments on the size of the number. Conversely, if an error message is returned, the program acknowledges this error by displaying the message and breaking out of the loop, thus exiting gracefully. This approach ensures a clean control flow and handles user input without cluttering the logic with additional complexity. Now let's see how we can implement a while loop with effective error handling through a user-friendly interface. This code establishes a loop controlled by the continue loop flag, allowing users to enter a positive number or to exit by typing -1. Upon initiating the loop, the program prompts the user to provide input while ensuring robust error management through a try-except block. If the user inputs -1, the flag is set to false, exiting the loop gracefully. For any negative input, a gentle reminder instructs the user to enter a positive number, facilitating an ongoing interaction rather than terminating the loop abruptly. This design enhances the application's responsiveness and user experience. In situations where the input cannot be converted into an integer, the code captures this with a value error exception, displaying a clear message stating that the input is invalid. This structure not only creates a more engaging interaction but also reinforces the importance of error handling, making the code efficient, intuitive, and user-friendly. Now let's take a look at how we can use nested while loops to validate multiple user inputs effectively. In this example, we first define a variable, numEntries, to specify how many valid entries we want to collect from the user. We initialize a counter, entry count, to keep track of the number of valid entries received. We begin an outer while loop that continues until we've collected the required number of entries. Inside this loop, we initialize an empty string entry that will hold the user's input. Next, we implement an inner while loop that checks whether the input is numeric using the isDigit method. This inner loop keeps prompting the user for input until a valid number is entered. When a valid entry is detected, the program acknowledges the valid input and increments our entry counter. If the input is invalid, an error message is displayed, urging the user to try again. This dual loop structure not only reinforces the concept of nesting loops but also enhances the program's interactivity, guiding the user until all required, valid inputs are successfully collected. Lastly, a confirmation message is printed to indicate that all entries have been collected successfully. Now let's see how we can implement a while loop that efficiently validates user input for numerical values within a specified range. In this example, we start by initializing a flag called inputValid to false. This flag allows the loop to determine whether the input meets the required criteria. The loop runs as long as inputValid is false, prompting the user to enter a number between 1 and 100. As the user enters a value, we attempt to convert it to an integer within a try-except block. If the conversion is successful, the program checks whether the number lies within the specified bounds. If it does, the flag is set to true, and a message confirming the valid input is displayed. If the user's input is outside of the range, a prompt encourages them to try again. In case of a value error, caught when non-numeric input is provided, the program informs the user about the invalid entry and requests a numeric value. This implementation enhances user experience by ensuring that the application remains operational and responsive until valid input is received, demonstrating the loop's ability to handle errors gracefully and maintain control flow effectively. Now let's see how we can implement a practical application using while loops to manage customer orders. In this example, we create a function called getOrderDetails, which prompts the user to enter an order ID and an amount. The function returns these details as a tuple, allowing us to efficiently gather multiple data points at once. Next, we introduce a while loop that will run indefinitely until the user decides to stop adding orders. Inside this loop, we call our getOrderDetails function and append the return details to a list called orders. This allows us to maintain a structured collection of order entries. After gathering the necessary order details, we ask the user if they would like to add another order by allowing them to input Y for yes or any other character to stop. If they respond with anything other than Y, the loop gracefully exits. Finally, we print a summary of all collected orders, showcasing the order ID alongside the formatted order amount. This structured approach highlights the utility of while loops for dynamic user input and data management, making it easy to track and process multiple entries efficiently. Now let's see how we can implement a user-friendly grading system using a while loop that effectively captures valid inputs. In this code, we initiate an empty list called grades to store the valid grades entered by the user. The while loop is set to run indefinitely, allowing it to continuously prompt the user for input until a specific exit condition is met. As the user inputs grades, they can type done to terminate the process. If they provide a numeric value, we attempt to convert it to a float. Here, the code employs a conditional check to ensure that grades fall within an acceptable range of 0 to 100. If a value is invalid, the program gives immediate feedback, informing the user of the error, and uses the continue statement to skip that iteration of the loop, prompting them for a new input instead. This use of break and continue not only enhances the control flow but also ensures the collection of only valid data, resulting in a clean list of entered grades that can be displayed at the end of the process. The overall design reflects strong error handling and user interactivity, crucial features for effective programming. Now let's take a look at how we can implement an optional else block in the context of a while loop. This code snippet demonstrates a straightforward use of the else clause to provide clarity about the loop's execution. Here, we initialize a counter at 0 and set a while loop to continue iterating as long as the counter is less than 5. Inside the loop, we simply increment the counter by 1 in each iteration. Once the counter reaches 5, the loop exits normally, allowing the else block to execute. This block outputs a confirmation message stating, "Successfully completed 5 iterations without interruption." This functionality is particularly useful as it clearly distinguishes a successful completion from an early exit due to an error or interruption. By using the else block, we avoid cluttering the loop with additional checks or flags, providing a clean and elegant solution to verify the loop's successful execution. This technique enhances control flow within your code, leading to more readable and maintainable programs. By now, we've unveiled advanced techniques for working with while loops, including error unions, state flags, nesting, and structured data management. Embracing these methods will not only improve your code's performance but also enhance its readability and maintenance. Remember, it's about writing clean, efficient, and user-friendly applications that anticipate problems and guide users gracefully. With this knowledge, you're well equipped to tackle more complex scenarios and keep refining your craft. So go ahead, experiment with these techniques and watch your proficiency soar in the world of programming. Happy coding! When learning to code, understanding the fundamental concepts is essential. In this lesson, we'll delve into the foundational ideas that underpin programming, giving you the tools you need to write effective code. These concepts will act as a solid base as we explore specific programming languages and techniques in future lessons. Now let's take a look at how we can define variables in Python. In this example, we create 3 variables: age, name, and is student. The variable age is assigned the integer value of 25, representing a person's age. Next, we have the name variable, which holds a string value Alice, reflecting a person's name. Strings are useful for representing text, and in this case, the use of quotation marks clearly indicates that the data is textual. Finally, the isStudent variable is assigned a Boolean value of true, which indicates whether the person is a student or not. The beauty of this setup is that variables are flexible and allow for updating their values at any point during the program's execution. For example, the age variable could later be modified to reflect a birthday. Understanding how to utilize variables effectively is crucial, as they serve as fundamental building blocks in programming, enabling you to store and manipulate data throughout your code. Next, we'll explore how we can perform basic arithmetic operations using variables in Python. Let's consider 2 variables, x and y, where we've assigned the values 10 and 3, respectively. These variables serve as our data points to demonstrate various arithmetic operators. Now let's implement the following calculations. First, we'll execute addition by summing x and y, which gives us a result of 13. This demonstrates how to combine values easily within a variable. Moving on, we can also perform subtraction by deducting y from x, yielding 7 as the result. This showcases how operators allow us to manipulate numerical values efficiently. Moreover, we'll see multiplication in action, where x multiplied by y results in 30. This operation emphasizes the power of operators in scaling values. Finally, we'll divide x by y, resulting in approximately 3.33. This operation introduces the concept of division and its ability to give us fractional results. By utilizing these arithmetic operations, you gain the ability to calculate and manipulate data dynamically in your programs. Now let's see how we can implement control flow using the if, elif, and else statements. In this example, we start by defining a variable called temperature and assigning it a value of 30. The next step involves checking the value of temperature using a series of conditional statements. The first condition evaluates whether the temperature is greater than 25 degrees. If this condition is true, the program executes the associated block, printing out a message indicating that it's a hot day. However, if the temperature is not greater than 25, the program then checks the next condition with a if, which examines if the temperature is less than 15 degrees. Should this condition hold true, it will print a message stating that it's a cold day. If neither condition is met, in other words, if the temperature falls between the two ranges, the else clause activates and provides a default message, indicating that it's a pleasant day. This structure allows the program to make decisions based on the temperature input, showcasing how control flow empowers the code to respond dynamically to varying data. Now let's see how we can implement a for loop in Python to sum up the elements in a list. In this code, we first define a list called numbers, which contains a series of integers from 1 to 5. We also initialize a variable named total to 0, which will be used to accumulate the sum of these numbers as we iterate through the list. Next, we utilize a for loop to go through each number in the numbers list. The syntax for number in numbers allows us to take each element of the list one by one, assigning it to the variable number during each iteration. Inside the loop, we add the current number to total using the plus equals operator, which adds the right-hand operand to the left-hand operand and updates the left operand with the new value. Finally, after the loop completes its 5 iterations, we print the result to the console with a formatted message that reveals the total sum. By using a loop, we efficiently process the entire list of numbers without writing repetitive code, showcasing the power of iteration in programming. Next, we will write a simple function to calculate the square of a number, illustrating how functions work to organize and reuse code. In our code, we define a function named square, which takes a single parameter called num. This parameter acts as a placeholder for whatever number we pass when we call the function. Inside the function, we perform a straightforward operation, multiplying num by itself to compute the square. Once the function is defined, we can use it at any point in our code. For instance, we call square 5 to calculate the square of 5, and the result is stored in the variable result. Functions not only help us keep our code clean and reduce repetition, but also enhance readability, making it clear what our intentions are. Finally, we print the outcome, which confirms that the square of 5 is 25. This example emphasizes the key benefits of functions: effective organization of code and ease of use across different parts of a program. Now let's see how we can implement a dictionary in Python to manage contact information efficiently. In this example, we create a dictionary called contacts, where each key corresponds to a person's name and each value is their phone number. This structure allows for quick access. For instance, when we need to find Alice's phone number, we can simply use her name as a key. Dictionaries in Python are incredibly useful because they allow us to store data in a way that is easy to retrieve and modify. In our case, the names serve as identifiers that link directly to the respective phone numbers. After defining the dictionary, we demonstrate its functionality by printing a formatted message that reveals Alice's phone number using the syntax contacts Alice. This line of code effectively retrieves the value associated with the key Alice and displays it on the screen. By using a dictionary, we not only enhance the readability of our code, but also ensure that managing contact information becomes straightforward and intuitive. Understanding how to manipulate such data structures is crucial for building more complex applications as your coding journey continues. Now that we've covered these essential coding concepts, let's recap what we've discussed. So far, we learned about variables and data types, operators, control flow with conditions, loops for iteration, functions for code reuse, and data structures for organization. These foundational elements create the framework for everything you'll do in programming. In our next lesson, we will dive deeper into applying these concepts through coding exercises and real-world examples. We will start writing small programs to reinforce these ideas and explore the exciting, vast world of coding in more detail. I hope you're as excited as I am for what's to come. Let's keep pushing forward, and soon you'll be writing code like a pro. Happy coding. Now let's take a look at how we can utilize list comprehensions to create concise and efficient code. The first example demonstrates how to generate a list of squares for numbers ranging from 0 to 9 using list comprehension. This technique allows us to create the squares list in a single line, replacing the more tedious traditional for loop. At first glance, you can see how this more streamlined approach not only reduces the amount of code but also enhances readability, making it easier to understand at a glance. Next, we will write the following code to generate only the squares of even numbers. This is achieved by adding a condition within the list comprehension. By including the if x%2 = 0 condition, we filter the results to include only even numbers, showcasing the power of list comprehensions to integrate logic succinctly alongside list creation. This approach not only keeps our code clean but also minimizes boilerplate code, demonstrating how elegant Python can be when leveraging advanced coding techniques. Next, we will write a decorator to log the execution time of a function, which illustrates an effective way to enhance the functionality of existing code without directly modifying it. The timelogger function is defined to accept another function as an argument. Inside, we create a nested function called wrapper, which will wrap the original function. This wrapper function records the start time before calling the original function and the end time once it is completed. The difference between these two timestamps gives us the execution duration, which we print in a readable format, indicating how long the function took to run. To demonstrate this, we use the @timelogger syntax above the sumHeavyComputation function, effectively applying our decorator to it. This means that every time sumHeavyComputation is called, it now also logs its execution time without needing to clutter the function's implementation with timing code. Finally, when we call the sumHeavyComputation with an argument to perform a significant calculation, the decorator automatically handles the timing and displays it, showcasing decorator's utility in simplifying code while enhancing its capabilities. Now let's see how we can implement context managers using the with statement to handle file operations seamlessly. When using the with statement, we start by opening a file, in this case, example.txt for writing. This operation ensures that the file is properly opened and assigned to a variable file, allowing us to perform write operations within the block. The beauty of using a context manager here is that the file will automatically close once the block is exited, even if an error occurs. This eliminates the need for a separate close statement, reducing the risk of resource leaks. Next, we'll explore creating a custom context manager by defining a class custom context. This class implements two special methods, enter and exit. When we enter the context defined by the with custom context statement, the enter method is invoked, allowing us to execute any setup code, in this case printing a message. Once we exit the block, the exit method executes, ensuring that any necessary cleanup occurs. This structure highlights how context managers can help maintain resource integrity and simplify code by managing lifecycle events elegantly. Now let's implement a generator function to illustrate the power of generators. In our example, the countant function takes a positive integer n as an argument and yields a sequence of numbers starting from n and counting down to 1. The key feature of a generator is how it handles memory. Instead of generating all the values at once, it yields one value at a time, which is particularly beneficial when dealing with large datasets or streams of data. When the function is called for iteration, it does not return a complete list of numbers but instead provides the next number in the countdown each time it is iterated over. This lazy evaluation not only conserves memory but also allows for performance gains, especially when the sequence is long or potentially infinite. In the following loop, we will actually see the generator in action. As we iterate through the countdown 5, the function will yield the numbers 5, 4, 3, 2, and 1 sequentially. This approach highlights the efficiency of using generators, demonstrating how they can simplify code that would otherwise require more complex data structures. Next, we will write the following code to demonstrate error handling through custom exceptions. In this example, we create a custom exception called negative number error that inherits from Python's built-in exception class. This custom exception will enable us to provide clearer error messaging when invalid inputs are given. Now let's implement a function called factorial, which calculates the factorial of a given number. Inside this function, we first check if the input is a negative number. If it is, we raise our negative number error, passing an informative message that specifies that factorials are undefined for negative values. This ensures that users know exactly what went wrong when they pass inappropriate inputs. If the input is valid, the function proceeds to calculate the factorial by multiplying all integers from 1 up to the given number. To illustrate the usage of this function, we wrap the call to factorial in a try-except block. When we attempt to calculate the factorial of -5, the custom exception gets triggered, and the except block captures it, printing out a clear error message. This technique not only enhances code readability but also allows for specific error management, making your program seamless and user-friendly. Now let's take a look at how we can improve our code by breaking a complex function into simpler components. Initially, we have a single function that computes the squares of even numbers up to a given limit and returns the first 5 of those squares. While this one-liner is concise, it sacrifices clarity, making it difficult for someone else to understand its purpose at a glance. To enhance readability, we can break this functionality into 2 distinct functions: compute even squares and first 5. The compute even squares function is responsible for generating the list of squares for even numbers, maintaining a clear single responsibility which aligns with clean code principles. Meanwhile, the first 5 function simply slices the list to retrieve just the first 5 elements. By modularizing the code, we promote easy maintenance and greater flexibility. We can modify or reuse individual components without affecting the entire codebase. As a result, the final implementation enhances comprehension, making the logic straightforward and approachable, exemplifying the best practices of clean code. In conclusion, mastering advanced techniques such as list comprehensions, decorators, context managers, generators, custom exceptions, and clean code practices will take your programming skills to new heights. As you explore these concepts, remember that clarity, efficiency, and organization are crucial for writing high-quality code. By incorporating these techniques into your coding toolbox, you'll not only enhance your projects but also prepare yourself for more complex coding challenges ahead. Next time, we will dive deeper into applying these advanced techniques with practical exercises. Keep honing your skills and continue this exciting journey into the world of coding. Happy coding! The Zig programming language is a general-purpose programming language designed for robustness, optimality, and clarity. Today, we will dive deeper into the world of Zig programming, exploring its features and demonstrating how it stands out in the landscape of programming languages. Now let's see how we can implement a simple file reading function in Zig. The function readFile takes a file name as input and returns either an array of bytes or an error, as denoted by the U8 return type. This showcases Zig's explicit error handling mechanism, where it indicates the potential for an error to arise during execution. Within the function, we utilize the try keyword to attempt to read the file using the standard library's file system capabilities. If the file read is successful, the contents are returned as an array of bytes. However, if an error occurs, it is propagated back to the caller without ambiguity. This approach emphasizes clarity in error management, making the code easier to troubleshoot. By directly handling file operations in this manner, we gain both performance and safety, key principles of the Zig programming language. The straightforwardness of error handling in Zig helps prevent common pitfalls associated with exceptions, enhancing overall code reliability. Now let's see how we can implement a simple Zig program using the standard library for output. The main function serves as the entry point of our Zig application. Within this function, we first import the standard library, which gives us access to essential functionalities. Next, we utilize the getStdout method from the standard library's I/O module to obtain a writer instance for standard output. This allows us to send output directly to the console. The line that follows demonstrates how to print a string, "Hello, Zig," to the standard output. The underscore before the print function call indicates that we are intentionally ignoring the return value, which can be useful when we are confident that the operation will succeed and we don't need to handle any potential errors in this context. This simple program showcases Zig's clarity and ease of use, making it straightforward to handle typical output operations. As you expand your program, you can incorporate additional functionality, such as managing external dependencies through the build.zig file, enriching your projects with more complex features while maintaining a clear structure. Now let's take a look at how Zig handles memory allocation safely and efficiently. In this snippet, we first import the standard library, which gives us access to various functionalities, including memory allocation features. We then define the entry point of our program with the main function, while also indicating that it can return an error through the void notation. Next, we set up a memory allocator using std, heap page allocator, which is a built-in allocator capable of managing memory effectively. The line where we attempt to allocate 1024 bytes of memory using allocator, alloc U8 1024, is crucial. It will either give us a buffer of that size or return an error if allocation fails. By employing the try keyword, we can handle any potential errors up front, enabling us to write safer code. To ensure that we don't leak memory, we use the defer keyword, which guarantees that allocate a free buffer will execute just before the function exits, no matter how the function terminates. This structure not only enhances safety by preventing memory leaks but also improves code clarity, providing a clear and structured way to manage resources effectively. Now let's take a look at a function that utilizes compile time evaluation to generate an array filled with a specific sequence of values. We begin by defining a function named generateArray, which accepts a single parameter, size, representing how many elements we want in our array. Inside this function, an array R is declared with a fixed size of 10, though we will return only the first size elements based on the input. Next, we use a for loop iterating over a range from 0 to size 1, which helps to fill the array with values. The @intCast function is employed to ensure that the index I is converted to a U32 type before being assigned to the array. This not only ensures type safety but also makes the intent clear. Now let's implement the main function to see this in action. Here we call generateArray with an argument of 5, which generates an array containing the values 0, 1, 2, 3, and 4. Finally, we traverse this array, printing each value using std debug print. This example illustrates how compile time evaluation in Zig can effectively streamline and minimize repetitive code, ultimately making our development process more efficient. Now let's take a look at how we can implement conditional logic in Zig using a practical example. In the provided code, we define a function named testCondition that accepts an unsigned 32-bit integer x as its parameter. This function utilizes an if-else control flow to evaluate the value of x and print a corresponding message based on the conditions specified. If x is equal to 0, it prints 0, indicating that the input is 0. The next condition checks if x is less than 10. If true, it prints less than 10. For all other values of x, the final else clause triggers, displaying 10 or more. This clear structure showcases how Zig's syntax facilitates understanding through straightforward decision-making constructs. Following the function declaration, we invoke testCondition 3 times in the main function, passing different values 5, 0, and 15. Each call demonstrates how the function accurately handles various inputs, leading to appropriate outputs. Such clarity in control flows allows for easier debugging and maintenance, aligning with Zig's goals of robustness and readability. Now let's see how we can implement a simple C function in Zig to demonstrate interoperability. The code begins with the declaration of a C function named add, which takes two U32 integer parameters and returns their sum as a U32. This is done using the extend C keyword, which indicates that this function is defined in C and can be called directly within Zig. In the main function, we utilize the add function by passing the values 3 and 4 as arguments. The result of this addition is stored in a constant variable named result. Following that, we output the value of result using the std debug print function, which prints formatted strings to the console. The placeholder in the string is replaced by the value of result, producing a clear output of the calculation performed. This showcases how easily Zig can interface with existing C code, enabling developers to leverage established libraries and functionalities without rewriting them, thus enhancing productivity and efficiency in the development process. In conclusion, Zig stands out as a programming language that prioritizes clarity, performance, and safety. Its combination of low-level control pad with high-level simplifications creates a unique environment for developers. The way Zig handles errors, its straightforward memory management techniques, compile time evaluations, and easy interoperability with C, all contribute to making it an excellent choice for modern software development. As we wrap up, remember that mastering a new language like Zig is about practice, exploration, and building real projects. I encourage you to delve into Zig's functionalities and create projects that challenge your understanding. Next, we will dive into specific use cases of Zig, exploring how to implement practical applications. So stay tuned and let's get coding. Zig is much more than just a syntax and a set of rules. It's about building a robust solution with an eye on performance and safety. As you continue your journey in programming with Zig, remember that every feature you learn interlocks with the concepts of clarity, performance, and safety. I hope you're as excited as I am about the power of Zig programming and its clean approach to both documentation and the overall structural integrity of code. Embrace the intricacies, keep practicing, and soon enough, you'll be adept at crafting elegant programs in Zig that are not only efficient but are also a joy to read. Now let's explore how we can use Zig's compile time capabilities to compute the factorial of a number. In the following code, we define a recursive function named factorial, which calculates the factorial of a given number n. If n is 0, the function returns 1, as the factorial of 0 is defined to be 1. For any other positive integer, the function calls itself with the argument n1, multiplying n by the result of this recursive call. What's particularly interesting here is how we can leverage Zig's compile time features. The line that defines const result equals factorial 5 computes the factorial of 5 during compilation instead of at runtime, allowing the final binary to include this result directly. This leads to performance improvements and insights into compilation optimizations. Moving on to the main function, we utilize Zig's std debug print to output the computed result. The final output will show factorial of 5 is 120, reflecting the efficiency of compile time execution. This approach illustrates how Zig not only enables clear and concise code but also enhances performance significantly through compile time evaluations. Now let's see how we can implement a flexible function using Zig's generics. We will create a print value function that accepts a type t as a compile time parameter. This function is designed to print any value passed to it, demonstrating Zig's ability to handle different data types effectively through generics while maintaining type safety. The use of comptime here ensures that the type is determined at compile time, allowing us to call print value with various types such as integers, floating point numbers, and strings. In the main function, we can see 3 different calls to print value, passing a U32, a F64, and a string slice as arguments. This showcases the flexibility of the function each time it is invoked. Zig generates the necessary code for the specific type provided, eliminating the need for type-specific implementations. This not only enhances code reuse, but also keeps the implementation clean and organized. By leveraging this powerful feature, developers can create reusable components and algorithms that adapt to different data types seamlessly, all while ensuring type safety. Now let's take a look at implementing a simple asynchronous function that simulates network requests in Zig. We start by defining the simulate network request function, marked as asynchronous. Within this function, we utilize std debug print to output messages indicating the start and completion of the simulated network request. To mimic a network delay, we use std time sleep, allowing us to pause execution for a specified duration, 1000 milliseconds in this case. Next, we shift our focus to the main function, where the magic of concurrency comes into play. Here we initiate the asynchronous function by calling async simulate network request, which starts the request without blocking the main thread. We then use the await keyword to indicate that we want to pause execution until the simulate network request completes. This approach allows us to manage multiple tasks concurrently, ensuring that our application remains responsive. Finally, after waiting for the completion of the network request, we notify the user by printing a message that indicates the main function has finished executing. This clean and efficient handling of asynchronous programming highlights Zig's strengths in managing concurrent tasks. Next, we will explore Zig's approach to error handling by implementing a division function that safely checks for division by 0. In our code, we define a function named safeDivide, which takes 2 integers, a numerator and a denominator. The function uses Zig's result type, indicated by the symbol, to either return the result of the division as a float or an error if the denominator is 0. This explicit checking enhances clarity and maintains robustness in our code, allowing us to anticipate and manage potential errors seamlessly. Now let's see how we can implement this in the main function. We call safeDivide with a numerator of 10 and a denominator of 0, which triggers the error case. Using a switch statement, we handle the different outcomes. If the result is an error indicating division by 0, we print an error message. Otherwise, we display the successfully computed result. This structured method for error handling not only simplifies the flow of our code but also promotes predictable behaviors, ensuring we can handle failures gracefully while maintaining readability. Now let's take a look at how we can implement testing for our safeDivide function in Zig. Testing is crucial in ensuring that our code behaves as expected, and Zig provides a straightforward way to do this. We begin by defining a test function using the test keyword, which precedes our test case description. In the body of this test, we call safeDivide with valid parameters, specifically dividing 10 by 2, and use the std testing expect function to assert that the result is indeed 5. This ensures that our function performs correctly for valid inputs. Next, we also need to verify the error handling when the denominator is 0. To test this, we call safeDivide with 10 and 0, which should trigger an error. We handle the expected error using a switch statement, checking that we receive the error division by 0. If our function runs into any unexpected results, it hits an unreachable case, which will help catch any bugs. By writing these tests, we confirm that our safe-divide function works as intended, providing confidence in its reliability within our codebase. Now let's see how we can implement the interoperability feature in Zig by using a C library for calling an external function. In this example, we have a simple C header file, myMathH, which declares a function that calculates the square root of a given number. This function can be seamlessly integrated into our Zig program, allowing us to leverage established C functionality without sacrificing Zig's safety and clarity. To use this C function, we first declare it in our Zig code using the extern keyword, specifying that this function is defined externally in C, which allows Zig to properly interface with it. We define the mySqrt function with the appropriate signature to match the C function's parameters and return type. Next, within the main function, we assign a value to a variable number which we intend to find the square root of, in this case 16. We then call the mySqrt function, passing in number as an argument, and store the result. Finally, we use the standard debugging print functionality in Zig to display the original number and its corresponding square root. This example illustrates how easily Zig can incorporate C libraries, showcasing its powerful interoperability capabilities and enabling developers to build upon existing C code. In conclusion, Zig presents a wealth of advanced features that cater to both performance and developer productivity. From compile-time code execution to seamless interoperability with C, and from effective error handling to robust testing frameworks, Zig proves itself as a versatile language suited for modern software development. I encourage you to explore these features, experiment with the code provided, and discover how they can enhance your own projects. The best way to learn is by doing, so get out there, play with Zig, and elevate your programming skills to the next level. Happy coding! Now let's take a look at a function that pauses a string into a 64-bit unsigned integer while effectively handling potential errors. This function, named pauseU64, is designed to process an array of bytes, taking care of both valid input pausing and error management. First, we initialize a variable x to accumulate the resulting number. As we iterate over each character in the input buffer, we convert it to a digit using the helper function chartAdigit. If the converted digit exceeds the specified radix, we return an error indicating an invalid character. One notable feature of this function is its checks for overflow during multiplication and addition, using Zig's built-in methods @mul with overflow and @add with overflow. If any overflow occurs during these operations, the function immediately returns the appropriate error. This approach ensures that the function maintains type safety while allowing developers to handle errors gracefully. Ultimately, if all characters are valid and no overflow occurs, the function returns the successfully paused U64 value. This clear integration of error handling within the logic showcases Zig's elegant approach to managing errors directly within the flow of functional logic. Now let's take a look at how we can handle the result of the pauseU64 function in different ways, demonstrating Zig's error management capabilities. In the first code snippet, we define a function called doAthing that attempts to pause a string as a 64-bit unsigned integer. Here, we utilize the catch statement to gracefully handle any potential errors that arise during pausing. If pauseU64 executes successfully, the paused value is assigned to the variable number. However, if an error occurs, number will default to 13. This approach ensures that the program continues to operate smoothly without crashing due to unexpected input. In the second snippet, we explore a different way to manage errors by propagating them up to the caller. By using the catch clause to catch the error explicitly, the function directly returns the error if it exists. This method provides more flexibility for the caller to handle the situation as they see fit, allowing for clearer intention in error handling and keeping the codebase clean. Overall, these two approaches showcase the elegance of error handling in Zig, giving developers the tools needed to create robust applications. Now let's explore how we can effectively handle errors in our functions using Zig's unique syntax. We start with a function called doAthing, which takes a byte array as input and attempts to pause it into a 64-bit unsigned integer using the previously defined pauseU64 function. By employing the try expression, if pauseU64 encounters an error, the doAthing function will immediately exit, propagating that error upwards. This approach not only simplifies the syntax, but also clearly communicates the intention to handle errors gracefully. Next, let's see how we can handle error scenarios when we're confident that a particular function call won't fail. Instead of using the try keyword which propagates errors, we use the catch unreachable statement with pause U64. This allows us to assume that the call should succeed, and if it fails, the program will crash in debug mode. This feature is useful during development, as it helps identify unexpected failures and improves code resilience. Thus, Zig provides robust error handling techniques, allowing developers to create cleaner, more maintainable code while ensuring application stability. Now let's take a look at how we can merge error sets in Zig to create a comprehensive error handling structure. In this example, we define two distinct error sets, A, which includes not dia and path not found errors, and B, which has an out-of-memory error. By using the operator, we merge these two sets into a new set, C. This ability to combine error sets is particularly advantageous when different parts of your application might encounter different errors that you want to manage uniformly. Next, we define a function called foo that returns a type of our newly created error set C. The function implementation exemplifies how you can return a specific error, in this case, error not dia. This structure allows for a streamlined error management system where handling multiple error conditions becomes seamless, enhancing the overall robustness of your code. Through this approach, you can handle various error conditions without complicating your function signatures or error handling logic. Now let's take a look at how Zig allows for efficient error handling through the use of error sets and coercion. In our example, we've defined two distinct error sets: file open error, which encompasses various file-related errors such as access denied, out of memory, and file not found, and a more specific allocation error that includes only the out of memory error. Next, we will write a function, foo, that accepts an argument of type allocation error but can return a file open error. This demonstrates the concept of coercion, where a subset of errors can be treated as a broader category, allowing for type-safe error handling without loss of information. It's crucial to understand that while we can easily convert an allocation error to a file open error, the reverse is not permissible. For instance, trying to return a file open error as an allocation error would result in a compile time error. This constraint ensures that developers remain aware of their error contexts, promoting safer and more predictable code outcomes. In summary, this code illustrates how using error sets and their relationships can lead to robust error management strategies in Zig. Now let's take a look at a practical example of how error handling works in Zig. In this code, we start with the main function that tries to call another function, foo, passing the integer 12 as an argument. The foo function has a significant role. It checks the value of the input parameter to decide the execution path. If the input is greater than or equal to 5, it attempts to call the bar function, which may potentially produce an error. If the input is less than 5, it redirects the flow to call the bang function instead. By using the try keyword before these function calls, Zig allows us to automatically handle any errors that might arise. If bar or bang returns an error, the try statement quickly exits the foo function, propagating the error back to the caller. This structure is efficient for error tracing, ensuring developers maintain a clear reflection of where errors originate in a multi-layered context. Such an organization not only simplifies debugging, but also reinforces the robust error management features Zig offers, showcasing how maintaining clean and manageable error flows can greatly enhance code quality. Error management is a crucial aspect of programming, especially when it comes to languages like Zig, where handling errors efficiently can greatly enhance the user experience and code maintainability. In this session, we will dive deep into advanced error management techniques, specifically focusing on the URDEFA statement. We will explore how it allows for more sophisticated error handling, the advantages of utilizing it, and how to implement it effectively in your code. So far, we learned that error handling is a vital aspect of programming in Zig, where it is treated as a first-class citizen. We explored error sets, which define possible errors in a type-safe manner, and how to return values alongside errors using union types with the operator. The tutorial also covered various strategies for managing errors using catch and try expressions, as well as merging error sets for more refined error handling. Overall, Zig provides a robust framework for maintaining clear and maintainable error management in applications. Now we will cover advanced error management techniques, including the use of the URDEFA statement and the associated best practices for capturing and handling errors effectively. Now let's take a look at how we can implement error management using the URDEFA statement in Zig while handling file operations. In this example, we define a function called processFile that takes a file path as an argument. The first step inside this function is to attempt opening the specified file using the std-fs openFile method. The use of the try statement here elegantly handles any potential error that arises from file opening, allowing us to proceed only if the operation is successful. Next, we utilize the defer statement to ensure that the file will be closed when we exit the function, regardless of whether an error occurs or the function returns successfully. This is crucial for resource management as it prevents resource leaks. We also introduce a simulated error condition, where we return a specific error if a certain condition fails. This demonstrates how even if an error occurs later in the function, the cleanup operation, closing the file, will still take place as specified by the defer statement. This structure not only simplifies error management, but also reinforces good coding practices by ensuring resources are appropriately released. Now let's see how we can implement error capturing with the URIDEFA statement in our processFile function. In this code, we start by attempting to open a file using the provided file path. The try keyword is employed to handle any potential errors that arise during this process, ensuring that if the file cannot be opened, the error is propagated back to the caller. This is an essential part of robust error management. Next, we utilize a defer block to ensure that the file will be closed when the function exits, regardless of whether it executed successfully or encountered an error. Within this defer statement, we capture any errors that occur while closing the file, allowing us to log them using Zig's std debug print functionality. This systematic error logging not only keeps our primary logic clean, but also guarantees that we document every failure point, enhancing our debugging capabilities. By incorporating this structured approach, our code remains readable and maintainable while efficiently managing resources. Therefore, even if our operations throughout the function generate errors, we have a reliable mechanism in place to ensure that all errors are captured and logged appropriately during cleanup. Now let's implement the following code to demonstrate how we can manage resources and log errors effectively within a server request processing function. In this code, we start by creating a temporary file that will store incoming request data. We use the std-fs create temp file function to ensure that this operation is safe and can return an error if it fails. The defer statement is crucial here, as it ensures that the temporary file is deleted when the function exits, regardless of whether an error occurs later in the process. Next, we process the data read from the temporary file using the processData function. This is again wrapped with a try to catch any errors that may arise during the data processing. Following this, we utilize another defer statement to log the result of the processing operation. This approach keeps our logging operations streamlined and ensures that all pertinent information is captured, aiding in debugging and monitoring. Finally, we simulate a scenario where a response might fail, showcasing how error handling is integrated into the function, thereby maintaining clarity in resource management without cluttering the main logic of the request processing. Now let's take a look at how error propagation can be effectively handled using the URIDEFA statement in Zig. In the code, we define a function called processRequest that begins by attempting to reserve resources, leveraging the try expression to capture any potential errors during this acquisition. This mechanism ensures that if something goes wrong while reserving resources, the error is immediately returned to the caller. Next, a defer block is introduced to manage cleanup tasks. Here we are tasked with freeing the resources that were previously allocated. If an error occurs during this cleanup, a scenario we anticipate and account for the deferred block captures that error. Instead of ignoring it, the code propagates the error back to the caller through a return statement, ensuring that the calling function is informed of the failure. By implementing such error handling, not only do we maintain a clean flow of resource management, but we also enhance the robustness of our application by ensuring that error states are communicated effectively. This approach embodies the Zig philosophy of proactive error management, reinforcing the importance of awareness and responsibility in error handling throughout the application. Now let's take a look at a practical implementation of the URIDEFA statement in Zig for handling connections. In the handleConnection function, we first attempt to accept a connection, leveraging Zig's try keyword to ensure that any errors in this process are appropriately handled. This sets the stage for robust error management. Next, we utilize the defer statement to ensure that the connection gets closed once we exit the function, regardless of whether an error occurs during processing. Inside the deferred block, we include error handling for the connection closure by logging if an error arises when closing the connection. This illustrates the benefit of using URDEFA, as it allows for automatic resource cleanup while also providing a way to manage errors that might occur during disposal. The clear comments within the deferred block serve not only to document the intention behind the code, but also to guide future maintainers in understanding the error handling strategy employed. By prioritizing clean coding practices and thorough documentation, this approach ultimately enhances maintainability, ensuring that complex scenarios are easier to navigate for anyone working on the code in the future. In summary, we've explored advanced error management techniques utilizing the URDEFA statement in Zig. This technique allows you to perform cleanup operations seamlessly, capture and log errors effectively, and propagate errors back to calling functions. We've looked at a range of code examples that demonstrated how to use URDEFA to maintain clarity and efficiency while managing resources and errors throughout your application. Incorporating URDEFA into your programming practice not only enhances the capabilities of your error management strategy, but also contributes to making your code more robust, maintainable, and ultimately user-friendly. Implementing these techniques will certainly align your projects with best practices and allow you to handle errors more adeptly as you continue your journey programming in Zig. Thank you for your attention and happy coding. Dive into the world of Zig programming where safety meets efficiency. Today, we're introducing you to a powerful feature in Zig, the optional type. This elegant tool allows developers to manage the uncertain nature of whether a value exists, all while keeping the code clean and readable. Now let's implement the following code to illustrate the use of optional types in Zig with a practical example. In this snippet, we first declare a normal integer called normalInt and set it to a value of 1234. Following that, we define an optional integer, optionalInt, initialized to null. This setup highlights the flexibility of optional types, allowing optionalInt to either hold a valid integer or be devoid of a value. Next, we assign a new integer value, 5678, to optionalInt. This transition demonstrates how easy it is to manipulate optionals in Zig without risking null reference errors. We then check if optionalInt contains a value using the conditional statement if optionalInt. If it does, we enter the block where we print the contained value safely as a non-null integer. Conversely, if optionalInt is still null, we output a message indicating its absence. This clear distinction helps to avoid confusion between existing and non-existing values, enhancing the overall code safety and readability, which are key principles in Zig programming. Now let's see how we can implement optional pointers using a struct in Zig. We start by defining a simple struct named foo, which contains an integer member. Then, we create a function called doSomethingWithFoo that takes a pointer to foo as its parameter. This function simply prints the value of the integer member from the foo instance. Next, we define another function, doAthing, which is key to our optional handling. It takes an optional pointer to foo. Inside this function, we perform a check to see if the optional foo contains a value. If it does, we can safely dereference it and pass it to doSomethingWithFoo, demonstrating Zig's robust null handling. If optional foo is null, the function prints a message indicating that no foo instance was provided, showcasing how optional types help in managing potential null values without runtime errors. Finally, in the main function, we create an instance of foo, passing it to doAthing. We also call doAthing with null, which effectively demonstrates the safe handling of optional pointers throughout the code. This pattern enhances the clarity and safety of our programs. Next, we will explore how to effectively use type coercion with Zig's optional types. In this example, we begin by declaring an optional variable, foo, initialized to null. This signifies that foo has no value at the start. As we move forward, we can assign a valid integer to foo, demonstrating how easy it is to coerce a value into an optional type. After assigning foo a value of 1234, we use compile-time reflection to examine the underlying type of the optional variable. The code includes a check that verifies whether the child type of foo is indeed I32. This powerful feature of compile-time reflection not only ensures type integrity, but also aids significantly in debugging processes, by allowing developers to ascertain the exact nature of the variables they are working with. This approach demonstrates how Zig's design enhances code clarity and safety while managing optional types, affirming that such checks are an essential practice for maintaining robustness in our programs. Now let's implement a practical scenario where optionals can significantly enhance our code's clarity and reliability. In this example, the fetchData function is designed to simulate interaction with an external API. It takes a Boolean parameter, success, to determine whether the data fetch was successful. If the operation succeeds, the function returns a valid integer, mimicking a successful response from the API. However, if the fetch fails, it returns null, indicating that no data was found. This use of optional types allows the function to clearly communicate whether a value is available or not, avoiding the pitfalls of traditional null references. In the main function, we call fetchData with a success condition and star its result in the data variable. We then utilize the optional pattern we've learned to check if data contains a value. If it does, we proceed to print the fetched data. If not, we inform the user that no data was available. This approach exemplifies how Zig's optional types not only streamline our code, but also enhance its readability and robustness by handling uncertain outcomes with confidence. Now let's see how we can implement memory allocation in a safe and concise manner using Zig's optional types. In the provided Zig code, we demonstrate how to utilize the malloc function to allocate memory for a struct type called foo. The malloc function is declared to return an optional pointer type, which signifies that the allocation may either succeed, yielding a valid pointer, or fail, resulting in a null value. Next, we define the allocate function, which is responsible for performing the memory allocation. Within this function, we invoke malloc with a specified size. By using the als operator, we elegantly handle the case of a failed allocation. If malloc returns null, we immediately return from the function, ensuring no further operations occur on a potentially invalid pointer. This integration of error handling directly within the allocation logic enhances code clarity and avoids potential runtime errors, serving as a clear distinction from conventional C code, where manual null checks are necessary. In this way, Zig's optional types offer streamlined safety and reduce boilerplate, making memory management both easier and more reliable. In summary, as we've ventured into Zig's optional types, we've uncovered how they offer safety, eliminate null reference errors, and enhance code readability. From transforming a simple type into an optional, managing pointers, leveraging compile time reflection, to optimizing external data fetches, optionals significantly contribute to safer programming practices. As we explore further in future lessons, we will delve into more advanced features of Zig, ensuring you continue on your journey toward becoming a proficient Zig programmer. Today, we will dive into the intricacies of advanced error handling in Zig programming. Error handling is a critical component of software development, ensuring that our applications behave reliably and gracefully handle unexpected situations. So far, we learned that Zig programming enhances safety and efficiency through the use of optional types and how they prevent null reference errors. Now we will cover advanced error handling techniques, enabling you to build robust and maintainable Zig applications. Now let's explore the implementation of error handling in Zig through file operations. First, we define a function called openFile, which takes a file name as an argument. This function utilizes the operator to indicate that it may return an error. Inside the function, we attempt to open the specified file using std, fs, fileOpenRead, employing the try expression to catch any errors that may arise during the file opening process. If an error occurs, it will propagate to the caller rather than crashing the application, allowing a more graceful management of failure. In the main function, we invoke openFile and again use try to handle potential errors effectively. If the file opens successfully, we defer the closing of the file to ensure that resources are properly managed and freed when they are no longer needed. The debug print statement at the end confirms that the file has been successfully opened, showcasing Zig's robust error handling capabilities while keeping the code clean and maintainable. This structure not only makes error propagation straightforward, but also enhances the overall safety of your application. Now let's implement a custom error type for our file operations in Zig. Here, we define a fileError set that includes specific errors such as not found, permissioned anyed, and read error. This structured approach allows developers to provide more descriptive feedback during error handling, which is crucial for debugging. Next, we create the openFile function, which attempts to open a specified file for reading. If an error occurs, we catch it using a catch clause and map the error to our defined custom errors. The use of a switch statement allows us to clearly outline different error scenarios, such as returning file error, not found when a file cannot be found, enhancing the clarity of the error handling process. In the main function, we then utilize the try keyword to call openFile, propagating any errors that may arise. The defer statement ensures that the file is closed properly once it is no longer needed, reinforcing resource management in the presence of errors. This strategy not only helps clarify the types of errors that can occur, but also maintains code cleanliness and safety in our error handling practices. Now let's take a look at how we can effectively manage multiple error types in Zig. In the code, we define a custom error type called AppError, which includes two categories of errors, file error and processing error. This approach allows us to clearly distinguish between different failure scenarios, promoting better error handling. Next, we implement the readData function, which attempts to read data from a specified file. If an error occurs during the file opening or reading processes, that error will automatically be propagated thanks to the use of the try keyword. This means that the caller of readData will be informed of any issues without crashing the application. Following that, we introduce the processData function, responsible for processing the data read from the file. If the data is empty, it returns a specific processing error, allowing us to handle this situation distinctly. Finally, in the main function, we bring these components together. We call readData and then processData, leveraging defer to ensure allocated resources are properly freed. This structure not only makes our error management seamless but also enhances code readability and maintenance. Now let's implement the following example that showcases advanced error handling along with resource management in Zig. In the main function, we start by attempting to read data from a file using the readData function. This function is designed to safely open the file and read its contents. The use of the try keyword here is crucial. It allows any errors that arise during the file reading process to be propagated up the call stack, making error management more intuitive. Once we successfully read the data, we use the defer keyword to ensure that the allocated memory is freed when the function exits, regardless of whether it completes successfully or an error occurs later. This cleanup strategy prevents memory leaks and maintains system stability. Additionally, by deferring the call to free the data, we ensure that resources are managed correctly, even when unexpected conditions arise during program execution. This approach demonstrates the power of deferred cleanup to handle errors gracefully and emphasize the robustness of our application's resource management practices. Thus, maintaining both functionality and memory safety becomes seamless and efficient in our Zig application. Now let's take a look at the implementation of readData, a powerful feature in Zig for cleanup in case of errors. In this snippet, we begin by attempting to open a file named example.txt using the openFile function. If this operation fails, an error is automatically propagated up the call stack due to the use of the try keyword. After successfully opening the file, the readData statement is employed with file close. This ensures that the file will be closed not only once we are done with it, but also if an error occurs later in the block, effectively establishing a safety net. This specific cleanup logic will only execute if the function exits due to an error, allowing developers to clearly separate normal flow from error flow. After the file handling, we see a debug print statement indicating successful processing, which would only execute if no errors were encountered. This pattern of using readData enhances code clarity and reliability, allowing for effective error management while maintaining resource integrity. Overall, this approach contributes significantly to writing robust applications in Zig. Now let's explore a logging strategy that assists in debugging and understanding errors in our Zig code. In the example given, we utilize Zig's std debug module to enhance error reporting. The main function attempts to read data from a file named example.txt using the readData function we defined earlier. Here we apply the try expression to initiate the data reading process, which will either return the data or propagate an error if one occurs. In the event of an error while trying to read the data, we catch the error using the catch construct. This allows us to log a detailed message immediately, specifying that an error occurred while reading from the file along with the specific error itself. The inclusion of relevant error contexts, such as the file operation that failed, significantly improves our ability to troubleshoot issues. This logging mechanism is crucial in a production environment, as it not only aids developers in understanding what went wrong, but also allows anyone maintaining the code to have insight into the failures that may occur during execution. Implementing thoughtful logging practices like this elevates the overall reliability and maintainability of your Zig applications. To wrap up this discussion of advanced error handling in Zig, we've journeyed through many essential practices you can implement in your applications. We explored error propagation using creating custom errors that make failures more understandable, dealing with various potential error scenarios cohesively, and employing both defer and readData for robust resource management. Lastly, we touched upon logging strategies to assist in debugging. By implementing these techniques, you're setting a solid foundation for building robust, error-resilient applications in Zig. Remember, error handling isn't just about error detection, it's about giving your application the ability to respond gracefully to unforeseen circumstances. Now that you're equipped with these advanced error handling tools, go ahead and apply them as you continue your journey in mastering Zig programming. Type coercion is an essential concept in programming languages that allows developers to convert one data type into another. It enables smooth and flexible code development by automating some of the tedious type conversions, ensuring that operations between different types can be performed seamlessly. In the Zig programming language, type coercion is particularly interesting as it encompasses both automatic and explicit casting under specific conditions. Now let's delve into a practical example that demonstrates type coercion in Zig. In this program, we define two constants, integer as an I32 type and floating as an F64 type. When we perform the addition of these two variables, Zig automatically converts the integer into a floating point number to carry out the operation seamlessly. This implicit conversion showcases Zig's ability to promote types without additional syntax, enhancing code readability and maintainability. Following the addition, we store the result in a constant named result. To display the output, we use the std debug print function which prints the result to the console. This example illustrates how type coercion allows developers to write clear and concise code without the burden of manual type management. Instead of worrying about manually casting types, you can focus on the call logic of your application, knowing that Zig handles the necessary conversions safely and effectively. Such features make Zig an efficient choice for developers seeking to streamline their workflows while maintaining code clarity. Now let's see how we can implement an explicit cast in Zig to convert a floating point number into an integer. In this example, we declare a constant floating of type F64 and assign it the value 9. When we want to convert this floating point number into an integer, we utilize the @intCast function. This function makes it clear that we are deliberately converting the type, which is necessary when we know there is a risk of data loss. In this case, truncating the decimal part to arrive at an integer value. After the explicit cast, we store the resulting integer in a constant named integer. It's important to note that Zig truncates the decimal portion during this conversion, resulting in 2 from 2.9. This highlights the importance of understanding how type conversions work in Zig and underlines the necessity of being cautious with explicit casts, especially when they can lead to unintended consequences, such as losing important data. Finally, the program outputs the integer value through standard debugging print functionality, solidifying our understanding of the type casting process in Zig. Now let's see how we can implement type coercion in the context of an array containing float values. In this example, we define an array of 3 floating point numbers, 1.5, 2.5, and 3.5. The goal here is to calculate the total sum of these elements. To achieve this, we first declare a variable total to hold the accumulated result. Next, we create a function called sumArray, which will take our array as an argument and return the sum as a floating point number. Inside this function, we initialize total to 0, representing the starting point of our summation. Using a for loop, we iterate through each value in the array. During each iteration, we perform an addition operation between total and the current value. It's important to note that Zig handles the type coercion implicitly here, allowing for seamless addition of the float values without requiring any manual conversions. Finally, the function returns the calculated total, which we then print to the console, demonstrating the efficiency and clarity that type coercion brings to arithmetic operations in Zig. Now let's implement the following example to illustrate type inference and coercion in Zig. We define two constants, 1 and 2, with types I32 and F64 respectively. The sum constant is calculated by adding these two values together. Because one of the operands is a floating point number, Zig automatically promotes the integer 1 to a float for the addition. This process showcases Zig's type coercion, where the compiler handles type compatibility seamlessly, allowing for clean and concise code. When we print the result using std debug print, we can observe the final output reflecting the sum of these two numbers. This code highlights how Zig effectively infers the type of sum as F64 without the need for explicit type declarations, resulting in improved readability and maintainability. Such features of type inference and coercion not only streamline our code structure, but also enable us to focus on the logic rather than the complexities of type management. This automatic handling of different types demonstrates the power of Zig, ensuring that our calculations remain safe and clear throughout. Now let's implement a union type in Zig to manage different numeric types effectively. Here we define a number union that can hold either an integer or a floating point number. In the main function we create two variables, A which holds an integer value of 10 and B which contains a floating point number 7.5. This flexibility allows us to work with both types under a single variable structure. Next, we will add these two numbers together using the addNumbers function. Inside this function, we need to handle the union type correctly, so we explicitly cast both A and B to F64 before performing the addition. This explicit casting ensures that the addition is conducted safely, eliminating any risks of type conflicts at runtime. Finally, we output the result with a debug print statement, confirming that the types have been successfully managed while highlighting the seamless integration of various data types in our calculations. This pattern demonstrates how union types and type coercion work in concert to produce robust and efficient code, a hallmark of Zig's design philosophy. To wrap up our discussion on type coercion, let's reflect on a few best practices to keep in mind while working with this concept in Zig or any other programming language. First, be aware of the types you're working with and how automatic coercions might affect your calculations. Second, always use explicit casts when you suspect there may be a risk associated with a conversion, such as truncating a float to an integer. Moreover, documenting your code becomes even more critical when dealing with type coercion. By clarifying your intent through comments or naming conventions, you ensure that both you and others who read your code understand why a particular conversion was done. In summary, understanding type coercion is essential to harnessing the full power of Zig. From automatic conversions that simplify arithmetic expressions to explicit casts that provide safety and clarity, type coercion enhances code robustness and ensures efficient operations. It certainly paves the way for you to create advanced, efficient programs with fewer bugs, thus enhancing your overall programming experience. As we move forward, we will continue to unlock the potential of Zig by exploring its other powerful features and constructs, ensuring that you are well equipped to tackle any programming challenge that comes your way. An optional in Zig offers a powerful way to handle nullable values and represent the absence of a value without resorting to cumbersome patterns. Unlike traditional error handling or null checks, an optional encapsulates a value that might or might not exist, offering a clear and concise way to express potential absence. Today, we're diving into advanced type operations in Zig, including how to leverage optionals effectively, alongside compile-time reflection, to work with types in new and exciting ways. So far, we learned about type coercion in programming, specifically in the Zig language, where it automates the conversion between different data types, enhancing code readability and maintainability. We discussed automatic coercion through examples, as well as the importance of explicit casts to prevent unwanted conversions and data loss. Additionally, we explored how type coercion interacts with union types and type inference, simplifying operations and ensuring safety in code execution. Overall, understanding type coercion is crucial for effective programming in Zig, allowing for robust and efficient code development. Now we will cover how to effectively use optionals and compile-time reflection to enhance your code's functionality and expressiveness. Now let's see how we can implement a function that accepts an optional value and uses compile-time reflection to gain insights about the stored type. In this example, we define a function called getOptionalTypeValue, which takes an optional U32 value as its parameter. Inside the function, we check if the optional has a value using an if condition. If the value exists, we bind it to a variable v and use Zig's reflection capability with @typeOfv to determine the type of v. This not only retrieves the actual value but also confirms its type at compile time, enhancing type safety. Next, we will use this function in the main function by creating an optional variable optionalValue, initialized with the integer 42. We then call getOptionalTypeValue, passing in the optional value. If there is a valid U32, the output will display both the value and its type, demonstrating the practicality of reflection. If the optional is empty, it will indicate that there is no value present. This approach emphasizes the seamless integration of optionals with advanced type features in Zig. Now let's see how we can implement a function that utilizes compile-time reflection to work with optional types in Zig. The function getOptionalTypeValue is designed to accept an optional U32 value. Within this function, a check is performed to determine if a value is present. If so, it reflects on the variable v, the value contained within the optional, using @typeOfv. This allows us to retrieve the type of the value at compile time, demonstrating Zig's capability for type introspection. Next, the function prints both the value and its corresponding type using std debug print, which showcases the flexibility of working with optionals in Zig. Should the optional value not contain anything, i.e., it's null, the function outputs a message indicating that no value is present, ensuring clear communication of the current state to the user. Finally, in the main function, we illustrate the usage of getOptionalTypeValue by creating an optional variable optionalValue initialized to 42. By calling the function with this optional, we demonstrate how compile-time reflection enhances type safety and clarity when handling potentially absent values. Now let's see how we can implement a configuration loader using optionals in Zig. In our passConfig function, we define a parameter that accepts an optional slice of bytes, which represents potential configuration data. This allows the function to gracefully handle cases where the configuration might be missing by checking if the provided data exists. If the data is present, we proceed to parse it as an integer using Zig's built-in parsing functions. Notably, if the parsing fails, we return null, which effectively communicates that the value could not be parsed instead of throwing an error. In the main function, we simulate a scenario where the configuration is absent by initializing it as null. The function then calls passConfig, and we utilize a pattern matching approach to check whether the parsing was successful. If we successfully retrieve an age, it is printed out. Otherwise, we provide feedback indicating that the parsing failed. This elegant handling of optional values significantly simplifies error management in our code, showing how optionals can enhance both clarity and functionality when managing potentially absent data. Now let's take a look at how we can incorporate optionals with union types to effectively manage success and error states in our code. In this example, we define a result type using a union enumeration, which allows us to represent either a successful outcome containing a U32 value or an error message as a string. The function getValue takes a Boolean condition and returns an optional result. If the condition is true, it returns a success with the value 42. Otherwise, it returns an error message, demonstrating how we can represent different states of operation succinctly. Next, we implement the main function to demonstrate how to handle the result from getValue. Here, an optional result is assessed using an if statement, and we employ a switch statement to differentiate between the success and error cases. This structure not only clarifies the outcome but also modularizes error handling within our code. By using this pattern, we enhance the clarity of our logic and ensure that each case, be it success or error, is explicitly addressed, promoting better maintainability and readability. Now let's take a look at how to manage collections of optionals, specifically in the context of handling user ages that may be missing. In this example, we define a function called printAges, which accepts an array of optional U32 values representing ages. The function iterates through the array, examining each age using a for loop. Within the loop, we check whether an age is present. If the value exists, we access it and print the corresponding age to the output using std debug print. However, if the value is null, indicating that the age is unknown, we print a message stating that the age is unknown instead. This approach demonstrates an efficient way to deal with optional values within collections, providing clarity and a structured output. Next, we set up our main function, where we initialize an array containing a mix of known and unknown ages, represented as optional values. By calling printAges with this array, we can effectively observe how the function processes each element, showcasing the power of optionals in handling real-world data scenarios where some values may be absent. This method not only enhances readability, but also simplifies error handling in applications. As we delve deeper into working with optionals, it becomes essential to discuss best practices for utilizing them effectively. While optionals provide simplicity in expressing nullable values, they can introduce complexity if used carelessly. One common pitfall involves excessive use of optionals, leading to nested optionals, which can obscure the code's intent. Instead, strive for clarity and simplicity. Use optionals when a value may genuinely not exist, but consider alternative patterns if it leads to deeply nested checks. Remember, the goal is to enhance code clarity rather than complicate it. Another best practice is to document the use of optionals. Make it clear in your function signatures whether a function may return an optional value and under which conditions. This helps other developers or your future self to understand how to use your code effectively without second-guessing your design choices. In conclusion, harnessing the power of optionals along with compile-time reflection in Zig offers a robust toolkit for handling nullable types efficiently and clearly. By using optionals, you're able to articulate your code's intent and design around the possibility of absence, leading to cleaner and more maintainable applications. Coupling this with Zig's compile-time reflection features empowers you to write highly adaptable and safe code that can react to varying types dynamically. So, as you move forward in your Zig programming journey, keep in mind the importance of a thoughtful approach to optionals. Their use can simplify error handling, streamline function signatures, and provide a clearer indication of program state without the usual pitfalls of null checks. Embrace these advanced type operations, and you'll find yourself crafting better structured and more resilient applications. Remember, in programming, clarity is key, especially when there's a possibility that something might be absent. Thanks for joining me today, and I look forward to seeing what incredible things you'll build with your newfound knowledge on advanced type operations in Zig. Text-based embeddings are powerful structures used to convert text into numerical vectors. This transformation is at the heart of many advances in natural language processing and machine learning. In today's lesson, we will delve deep into what text-based embeddings are, why they are important, and how to create and utilize them effectively in various applications. So far, we've learned about the use of optionals in Zig, which enhances error handling and encapsulates values that may or may not exist. We also covered compile-time reflection, enabling type introspection, which boosts code safety and flexibility. Now, we will talk about how embeddings transform textual information and make it consumable by machine learning algorithms. We'll explore different types of embeddings, showcase some foundational techniques, and run through examples that will clarify how they are put into practice. Text embeddings serve as a bridge between human language and computer understanding. The fundamental idea is to represent words, phrases, or entire documents as vectors in a continuous vector space. This representation allows computers to inherently grasp semantic meanings through geometry. Simply put, words that are similar or related in meaning tend to be located closer together in this vector space. For example, asterisk king asterisk and asterisk queen may exist closer to each other than asterisk asterisk king asterisk and asterisk car. This property is pivotal for tasks like sentiment analysis, translation, and information retrieval. The fascinating part about embeddings is how they can encapsulate not just individual word meanings, but also relationships and contexts. For instance, you can capture the concept of gender through the difference between vectors. The relation asterisk asterisk king, man plus woman asterisk gives a vector that approximates to asterisk queen. This linguistic manipulation showcases the power of embeddings and their representation capabilities. Next, let's see how we can create our text embeddings using Python and libraries like TensorFlow or PyTorch, both of which are invaluable tools in modern machine learning. Now let's see how we can implement the Word2Vec model to create text embeddings using the Gensim library. First, we need to install Gensim through pip, which allows us to utilize its capabilities for training embedding models. Once the library is installed, we can import the Word2Vec class from Gensim models, which is essential for building our model. Next, we will define a simple corpus composed of a few sentences. This corpus serves as the training data that the model will learn from. The vector size parameter specifies the dimensionality of the word vectors we will create, while the window parameter defines the maximum distance between the current word and the predicted word in a context. After defining the corpus, we train the Word2Vec model using these sentences, allowing it to learn how words relate to one another based on their context in the text. Finally, we will retrieve and print the vector associated with the word cat. This vector is a 10-dimensional representation that captures the contextual meaning of cat relative to other words in the training data, showcasing how the model abstracts and learns from the language. Now let's implement fast text to generate word embeddings for our text data. First, we import the fast text model from the Gensim models library, which we'll use for training our word embeddings. Similar to our previous Word2Vec example, we define a small sample dataset consisting of several sentences. This will serve as our training corpus, which fast text will process to understand the relationships between words. Next, we train the fast text model using the defined sentences. In this instance, we specify parameters such as vector size, which determines the dimensionality of the vectors for each word, window, indicating the maximum distance between the current word and predicted words, min count, which defines the minimum number of occurrences for a word to be considered, and workers, which sets the number of CPU cores to use during training. Once the model is trained, we can easily retrieve the vector representation for any word in our vocabulary by accessing the model's WV attribute. For instance, we've illustrated how to get the vector for the word cat. This vector captures semantic information about the word, allowing for advanced processing and analysis in various natural language processing tasks. Fast text's unique feature allows it to handle out-of-vocabulary words effectively, making it a robust choice for applications dealing with diverse language inputs. Now let's implement a simple text classification model using a logistic regression approach. We begin by importing necessary libraries and preparing a small labeled dataset, which includes sentences annotated with either a positive or negative sentiment. This data serves as the foundation for our model's training. Next, we set up our input and output variables. For each sentence, we convert it to lowercase and split it into individual words. Using our previously trained word-to-vec model, we retrieve the corresponding word vectors for each word in the sentence. It's crucial to ensure that we only consider words that exist in the model's vocabulary. Thus, we check for valid word vectors. After gathering the vectors, we compute the average of these word vectors to create a single vector representation for the entire sentence. This averaged vector captures the sentiment more succinctly. Once our feature set is prepared, we divide the data into training and test sets, allowing us to evaluate the model's performance. Finally, we train the logistic regression classifier on the training data and make predictions on the test set. By utilizing the accuracy metric, we can gauge how well our model performs in distinguishing between positive and negative sentiments, showcasing the effectiveness of word embeddings in sentiment analysis. As we wrap up this discussion, it's important to highlight that text-based embeddings have redefined how we approach language comprehension in machines. With their ability to transform complex linguistic features into manageable numerical formats, they have paved the way for innovations in various fields such as sentiment analysis, information retrieval, and even conversational agents. So far, we've covered the foundations of text embeddings through techniques like word-to-vec and fast text, explored how to generate these embeddings, and implemented a basic text classification model utilizing them. In our next lesson, we will delve deeper into advanced topics like transfer learning and how models such as BERT and GPT leverage the power of embeddings to achieve state-of-the-art performance in language tasks. Through every step, keep in mind the significance of embeddings in distinguishing meaning, understanding context, and revealing relationships between words. The journey into the world of embeddings is just beginning, and the potential applications are as vast as human language itself. Thank you for joining me today, and until next time, keep exploring the linguistic dimensions of data. The world of text embeddings is a vast landscape filled with powerful techniques that can transform our understanding of human language. Today, we're diving into advanced methods for generating and applying these text embeddings, exploring the depths of modern machine learning techniques that harness their potential for various applications. So far, we learned about the significance of text embeddings in converting human language into numerical vectors, facilitating machine understanding. We explored foundational techniques such as word-to-vec and fast text for generating these embeddings. Additionally, we implemented a simple text classification model to demonstrate how embeddings can be utilized for sentiment analysis. Now, we will cover more sophisticated techniques, including transfer learning, contextual embeddings, and how state-of-the-art models like BERT and GPT leverage these concepts to achieve remarkable performance. Next, we will write the code to install the necessary libraries, which are crucial for utilizing BERT for our movie review classification task. By using the command pip install transformers torch, we ensure that the required Hugging Face Transformers library and PyTorch framework are included in our environment, enabling us to work with pre-trained models and perform deep learning tasks effectively. Now let's implement the main components of our model. We start by importing the necessary modules, including BERT tokenizer and BERT far sequence classification from the transformers library, as well as essential tools like data loader and dataset from PyTorch. We then define a custom dataset class named movieReviewDataset, inheriting from PyTorch's dataset class. This custom class is designed to handle our reviews and labels, incorporating the BERT tokenizer for tokenization and preprocessing. Within the getItem method, we utilize the encodePlus function to prepare our reviews by adding special tokens, padding them to a fixed length, and creating attention masks that help the model focus on the relevant parts of the input. Once our dataset class is ready, we split our dataset into training and test sets using train-test-split, ensuring we have a portion of the data reserved for evaluation. We then initialize the BERT tokenizer with the specific pre-trained model and create a training dataset instance to facilitate batching and shuffling of our training data. Finally, we set up a data loader to streamline the input process for model training. Now let's implement the training loop for fine-tuning our BERT model on the movie review classification task. First, we initialize the BERT far sequence classification model using pre-trained weights from BERT base uncased, specifying that we have 2 labels for our classification task. We also set up the AdamW optimizer, which is well suited for training deep learning models like BERT, allowing us to adjust the learning rate effectively. Next, we enter training mode by calling model train, which prepares the model for updating its weights. We'll train the model over 3 epochs, iterating through our training dataset in batches. In each batch, we begin by resetting the gradients with optimizer 0 grad, ensuring that previous iterations do not affect our current calculations. We then retrieve the input IDs and attention masks from the batch, followed by the true labels for our reviews. The model processes the input data to produce outputs, from which we calculate the loss by comparing the predictions with the true labels. After backpropagating the errors with loss backward, we update the model's parameters using optimizer step. Finally, we print out the epoch number and the current loss, which is helpful for tracking the model's learning progress throughout the training phase. This structured approach optimizes the model's ability to classify movie reviews effectively. Now that we have trained our BERT model, let's implement a method to evaluate its performance using the test dataset. First, we switch the model to evaluation mode with model eval, which is essential as it disables dropout layers and ensures consistency during inference. We then create the test dataset by using the movieReviewDataset class, providing the tokenizer and a maximum sequence length to ensure proper formatting of inputs. Next, we load the test data into a data loader, allowing us to efficiently iterate over the test dataset in batches. We initialize an empty list to store predictions, which we will populate as we process each batch. Using a with TorchNoGrad context, we avoid calculating gradients, improving efficiency during inference. In a loop, each batch's input IDs and attention masks are passed through the model to generate outputs. The torch argmax function is utilized to extract the predicted class with the highest probability for each instance. Finally, we extend our predictions list with these results, allowing us to later assess the model's accuracy against the true labels. This structured approach is key to systematically evaluating our model's performance on unseen data. Now let's see how we can implement BERT to generate contextual embeddings for the word bank in 2 different sentences. We start by importing the necessary libraries from the transformers package, BERT tokenizer for tokenization and BERT model to access the pre-trained BERT model. Next, we load the BERT tokenizer and model using the pre-trained weights, which provide us with the capabilities that BERT has learned from extensive data. Then we define 2 sentences, each containing the word bank in distinct contexts. To process these sentences, we utilize the tokenizer to convert them into a format suitable for BERT, specified by return tenses equals PT, to indicate that we want PyTorch tenses as output. With the sentences tokenized and prepared, we use the model to obtain the outputs for both sentences. By disabling gradient calculations using touch-no-grad, we can efficiently fetch the outputs without storing gradients unnecessarily. Finally, we extract the embeddings for the token corresponding to bank in each output. By indexing into the lost hidden state with the appropriate position, we retrieve the contextual embeddings for bank. This provides a tangible demonstration of how BERT captures the nuanced meanings of words depending on their sentence context, showcasing the power of contextual embeddings in natural language processing. Now let's implement the following code to fine-tune a GPT model for text generation. We begin by importing the necessary components from the Hugging Face Transformers library, specifically the GPT-to-tokenizer and GPT-LM head model. The GPT-to-tokenizer is used to convert our text input into a format recognizable by the model, handling tasks such as tokenization and encoding special tokens. Next, we initialize the tokenizer and model using the pre-trained GPT-2 variant. This allows us to leverage the extensive language knowledge it has already acquired through pre-training on a diverse dataset. We then prepare an input text which acts as a prompt for the model to generate continuations. This input is encoded into tensors, structured numerical representations that the model can process. Following this setup, we utilize the model's generate function to produce new text, specifying parameters such as the maximum length for the output and the number of different sequences we want to retrieve. Finally, the generated text outputs are decoded back into human-readable format and printed, showcasing GPT's ability to create contextually relevant and coherent text based on our initial prompt. To wrap up, the advanced techniques we've discussed today, including transfer learning, contextual embeddings, and the advanced architectures utilized by models like BERT and GPT, depict a new era of natural language processing. With these technologies at our disposal, we can tackle increasingly complex problems, from sentiment analysis to machine translation, with remarkable accuracy and efficiency. Embracing these sophisticated methodologies equips us with the tools necessary to refine our language models and develop applications that can engage more thoughtfully with human language. The realm of text-based embeddings is continually evolving, and as you embark on further experimentation, keep pushing the boundaries of what these models can achieve. Thank you for joining me on this deep dive into the advanced techniques in text-based embeddings. Remember, the journey into understanding language through machine learning is as vast as language itself, and every exploration enriches our grasp of both technologies and linguistic intricacies. Until next time, keep experimenting and learning. Type coercion is a critical concept in programming languages that deal with variables and data types. In this segment, we will delve into the fundamentals of type coercion, especially focusing on compile-time known numbers. You may think of this as a way that programming languages handle the tricky business of converting data types under certain circumstances, ensuring that operations go smoothly without running into errors. So far, we covered advancements in text embeddings and how they enhance our interaction with language through contextual representations. Now, we will talk about type coercion, particularly how it applies to compile-time known numbers and what implications this has for type safety and error reduction in programming. Now let's see how we can implement type coercion in the Zig programming language with a practical example. In this code snippet, we start by defining a variable x of type U64, which stands for a 64-bit unsigned integer. We assign it the value 255, a number that we know can fit into a smaller 8-bit unsigned integer type, U8. Next, we introduce another variable, y, which is of type U8, and we assign it the value of x. Here, Zig's compiler automatically coerces the value of x into y without any explicit instructions from us. This is possible because 255 is well within the range that an 8-bit integer can handle. To verify that the coercion worked correctly, we perform a test using a function from the standard library to assert that y is indeed equal to 255. This showcases not just the convenience of type coercion, but also the language's emphasis on safety, as it allows for automatic conversion when it's safe to do so, ensuring that we can confidently use smaller types without fear of losing precision. Next, we will explore how to implement unions and enums in Zig and leverage their type coercion capabilities. In our code snippet, we start by defining an enum called e that consists of 3 named values, 1, 2, and 3. This enum allows us to refer to these values by name, enhancing code readability and maintainability. Next, we define a union, u, associated with the enum e. The union specifies that it can hold an integer corresponding to 1, a float for 2, and an unspecified value for 3. This allows for flexibility, as the union can store different types while ensuring only one is active at any time. Now let's see how we can create a union instance by initializing u with the value 2 and a corresponding float. The significant step here is the coercion process, where we assign the union instance u to a variable e of type e. Zig's type system permits this conversion since the compiler can determine that u indeed contains a value that matches one of the enums fields, ensuring there's no type ambiguity. Finally, we verify that our coercion works as intended through a simple test, asserting that e equals e2. This demonstrates the seamless interaction between unions and enums, enhancing our type management toolkit. Now let's take a look at an important example of coercion in the Zig language. In this code, we define a variable x as a nullable integer, which is indicated by the type i32. This means that x can hold either an integer value or null, representing an undefined state. We then create another variable y of type i32 and directly assign x to it. What's crucial here is that x is coerced from its nullable type to a concrete integer type. The Zig language handles this coercion by converting the undefined state, or null, to a default integer value of 0. To verify this behavior, we use a testing assertion that checks whether y equals 0 after the conversion. This illustrates how Zig's type system allows for flexible handling of undefined types, streamlining error management and enhancing type safety without requiring extra boilerplate code. Such features enable developers to write more concise applications while maintaining strict type integrity, a vital aspect of robust programming practices. Now let's examine a practical example of how to coerce tuples into arrays, focusing on the implications of type consistency. We begin by defining a struct named tuple, which contains two fields of type u8. This struct serves as our tuple representation, encapsulating two 8-bit unsigned integers. Next, we write a test case to demonstrate the coercion process. We create an instance of tuple, initializing it with two specific u8 values, 5 and 6. This is significant because it highlights that both elements share the same type, which is a prerequisite for the coercion to be successful. We then take this tuple and directly assign it to an array of type 2u8. Here Zig's type coercion feature shines, as it automatically converts the tuple into an array format without explicit instruction from the programmer. Lastly, we use the array in an operation to verify that the coercion has been carried out successfully. This showcases the efficiency of type coercion in managing collections, allowing for clean and flexible code while maintaining type safety. Now let's take a look at an example of explicit casting in Zig, which is essential when dealing with different numeric types. In this code, we define a constant x with a value of 10 and a type of u32, which is a 32-bit unsigned integer. To demonstrate explicit casting, we will convert this u32 type into a u8 type using the built-in function at intcast. This function is specifically designed for safe type conversions and ensures that we are intentionally converting the type based on our needs. It's important to note that when casting from a larger type like u32 to a smaller type like u8, we must be cautious, as there is a possibility of truncating the value if it exceeds the maximum limit of the smaller type. In this case, since 10 easily fits within the range of a u8, we expect the casted result to be successful. We then use a test statement to verify that the value of casted is indeed 10, confirming that our explicit conversion has been executed correctly. This example illustrates not only how to perform explicit casting, but also highlights the importance of understanding type constraints to avoid unexpected behaviors in your programs. Now let's take a look at how peer type resolution works in the context of type coercion. In this example, we define two variables, a and b, with different integral types, i8 and i16 respectively. When we perform the addition of these two variables, the Zig compiler automatically widens the type of a from i8 to i16 to match b. This process underscores the importance of type safety, as it ensures that operations involving multiple data types can be performed without resulting in errors. By allowing a to be coerced into a compatible type, the compiler ensures that the resulting value stored in C maintains the expected integrity and behavior. We then conduct a check using the expect function to verify that the sum is indeed equal to 46, as well as to confirm that the type of C is I16. This example illustrates how Zig's handling of type coercion not only avoids potential type-related bugs, but also enhances the robustness of your applications when integrating various data types. In summary, we have explored the fascinating world of type coercion, honing in on compile-time known numbers. We covered how automatic coercion works, illustrated with examples involving integers, unions, enums, tuples, and explicit casts. Understanding these nuances equips you as a programmer to write cleaner, more efficient code while harnessing the inherent safety that type management provides. Remember, while type coercion can simplify many operations, awareness of how and when types can be coerced minimizes the risk of unexpected behaviors in your code. In subsequent segments, we will dive deeper into more advanced topics and scenarios involving type manipulation, paving the way for greater fluency in programming languages. In today's lesson, we're diving into the fascinating world of advanced type coercion techniques, ensuring that you leave with a deeper understanding of how to manipulate types effectively in programming. So far, we learned about type coercion, focusing on its automatic or implicit conversion of values among data types, especially with compile-time known numbers. We explored examples in Zig illustrating how coercion works with integers, unions, enums, tuples, and explicit casting, highlighting its importance in achieving type safety and reducing errors. This foundational understanding aids programmers in writing efficient code while managing data types effectively. Next, we'll explore advanced topics related to type manipulation. Understanding PIA type resolution is crucial for advanced type coercion techniques. PIA type resolution occurs when several variables involved in an operation need to share compatible types. This process is particularly important in scenarios like switch expressions, if statements, and loops. The main idea is that the compiler must determine a common type, enabling all expressions to be safely coerced into this type. Let's illustrate this with a code snippet. Now let's see how we can exemplify PIA type resolution with an arithmetic operation in Zig. In this test, we start by defining two constants, A of type I16 and B of type U32. When we perform the addition operation, the Zig compiler automatically widens A to match the type of B, ensuring that both operands are compatible. This type resolution is crucial for preventing any errors that might arise due to type mismatches during execution. The result of this operation is stored in the variable result, which is now of type U32. To confirm the correctness of our operation, we use the expect function from Zig's testing library to assert that result equals the expected value of 20. Furthermore, we check the type of result using @typeOf, ensuring that it is indeed a U32. This example not only highlights the automatic type coercion provided by Zig, but also emphasizes the importance of ensuring type safety and compatibility in operations, thus allowing us to write robust and error-free code. Now let's implement the following function to demonstrate type coercion in function parameters. In this code, we define a function called add, which takes two parameters of type U32 and returns their sum as a U32. This setup highlights how Zig allows for the flexibility of accepting different integer types. When we write the test function for add, we specify two variables, x of type I16 and y of type U8. As we call the add function using these variables, the Zig compiler automatically applies type coercion, converting both x and y to U32 before performing the addition operation. This implicit coercion lets us pass integers of different types without needing explicit casts, simplifying our code and enhancing its readability. The result of the addition is stored in the sum variable, which we then verify with an assertion to check if it equals 25. This example emphasizes the convenience of function parameter coercion in maintaining type safety while enabling flexible code, allowing developers to work seamlessly with different integer types in their functions. Now let's see how we can implement type coercion between arrays and slices in Zig. In this example, we define a function called operateOnArray that takes a slice of type U8. This allows flexibility in processing collections of bytes. Inside the function, we return the sum of the first two elements of the passed slice. Next, we write a test case named coercion between array and slice. Here we declare a fixed size array named array composed of three elements, 1, 2, and 3. When we call the operateOnArray function and pass in array, the Zig compiler automatically coerces the array into a slice. This implicit coercion demonstrates Zig's ability to handle different but compatible types seamlessly. As a result of this conversion, the addition of the first two elements of the array occurs correctly, yielding a total of 3, which we verify using the expect function. This effortless interaction between arrays and slices underscores the simplicity and power of Zig's type coercion system, enabling developers to work with collections without excessive type management. Now let's see how we can implement a protocol using union types that allows for seamless type coercion in Zig. We begin by defining a union called protocol that can represent either an integer, i32, or a floating point number, f32. This flexibility is crucial as it enables the function processValue to accept values of different types and handle them accordingly. Within processValue, we utilize a switch statement to determine the type of the incoming value. If the type is i32, we coerce it into a f32 using a straightforward type conversion. This is an essential technique because it allows for consistent processing of numerical values regardless of their initial type. If the incoming value is already a f32, we simply return it without alteration. Next, we create a test to validate our implementation. In this test, we define instances of protocol for both i32 and f32, demonstrating how the processValue function handles them. We then assert that the results match our expected outcomes, confirming that our type coercion works as intended while enhancing type safety and code flexibility. This example exemplifies the strength of using protocols and unions in type manipulation. Now let's take a look at how type coercion applies to structured types such as structs. In this example, we define two structs: point, which has f32 floating point fields for x and y, and point int, which uses i32 fields instead. The from point to point int function demonstrates the conversion process, taking a point as an argument and explicitly casting its x and y values to i32 using the @intCast function. This explicit coercion is essential for accurately converting the float values while avoiding potential pitfalls associated with type mismatches. Next, we proceed to test this function in the test block. Here, we create a point instance with floating point values and then invoke the from point to point int function to obtain an equivalent point int instance. The testing assertions check that the truncated conversions yield the expected values, demonstrating how cleanly our coercion works and reinforcing the importance of handling such conversions carefully. This example encapsulates how coercion can promote type safety and maintain the integrity of data within structured types. Now let's implement a function that showcases the use of generics alongside type coercion. In this snippet, we define a generic function called addNumbers, which takes two parameters of type t. The flexibility of generics allows this function to accept various data types, enabling code reuse without the need for redundant implementations. Specifically, addNumbers returns the sum of the two parameters, leveraging Zig's type coercion capabilities. Next, let's take a look at how we can test this function utilizing different types. In the test block, we call addNumbers twice, first with integers, then with floating point numbers. The function's design ensures that if the types can be widened appropriately, the addition operation behaves correctly across both data types. In the first case, we pass two integers and expect the sum to be 30. In the second, we pass two floating point numbers, with an expected result of 3.5. This code demonstrates the power of type coercion within generics, promoting a more dynamic and versatile approach to handling arithmetic operations in Zig. Now let's implement a testing function to validate our coercion operations. This function is designed to check if our implicit and explicit type conversions align with our expectations. Here, we will start by defining the expected integer value of 10, which we can use as a benchmark for our tests. Next, we introduce a float variable set to 10, which we expect to be implicitly converted to an integer. In addition, we also define an integer variable with the same value of 10. The crucial part of the function involves performing the coercion. We use the @intCast function to convert the float to an integer. This allows us to capture the result of this conversion into a variable. For the integer variable, no coercion is necessary since it already matches the expected type. Finally, we employ the expect function to assert that both results from our coercion operations equal the expected integer value. This structure bolsters our confidence in the correctness of our coercion practices, enabling us to catch any discrepancies early in the development process. Thus, this testing function solidifies the reliability of handling type coercions in our code. With all these nuances explored, we've covered advanced coercion techniques extensively. Understanding and mastering these elements, PIA type resolution, function parameter coercion, array and slice types, protocols, structs, generics, and effective testing methods, truly equips you to navigate complex type manipulations within your programming endeavors. This knowledge dramatically enriches your coding capabilities, allowing for the creation of clean, efficient, and flexible code solutions tailored to your project's needs. So, as you continue your coding journey, remember these concepts as vital tools when dealing with type coercion. Embrace the challenges and complexities as they provide valuable learning experiences. Thanks for tuning in, and I look forward to seeing you in our next lesson, where we'll continue to explore exciting programming topics and deepen your coding skills. In today's tutorial, we are diving into the fascinating world of compile time functions in Zig. We'll explore how leveraging the comptime keyword enables developers to perform computations at compile time, enhancing efficiency and safety in programming. So far, we learned about advanced type coercion techniques in programming, focusing on how implicit and explicit conversions of types can improve code efficiency and reduce errors. We covered examples in Zig illustrating peer type resolution, coercion in function parameters, and automatic coercion with arrays and slices. We also explored the use of protocols, structs, and generics in relation to type coercion, highlighting their significance in creating flexible and robust code. Our journey emphasized the importance of testing to ensure proper coercion behavior in various scenarios. Now we will talk about compile time functions and we'll discover how they can help you write more efficient and safe Zig code. Now let's take a look at a practical implementation of the comptime keyword in Zig by writing a factorial function. In this code, we define a function named factorial that takes a non-negative integer n as input. The striking feature here is the comptime modifier applied to the function, which instructs the compiler to evaluate the factorial value during compile time, ensuring that the result is computed before the program runs. This recursive function follows the standard definition of a factorial where it multiplies n by the factorial of n1 until it reaches 0, at which point it returns 1. Next, we proceed to the main function where we call factorial 5. Since the computation of this factorial occurs at compile time, the output is determined before execution, allowing us to directly print the result. The use of std debug print here demonstrates how we can print the computed factorial value, which in this instance is 15. This approach not only highlights the efficiency gained from compile time calculations, but also emphasizes the power of Zig's comptime functionality in enhancing program performance and minimizing runtime overhead. Next, we will write the following code to demonstrate how to create an array with a constant length using the comptime keyword in Zig. The createArray function is defined to take a length parameter, which is marked as comptime u32. This indicates that the length must be determined at compile time, allowing the Zig compiler to allocate the exact amount of memory needed for the array efficiently. Within the function, we return an array initialized with zeros, where the size is specified by the compile time constant length. This enables Zig to optimize memory usage since the size is known ahead of execution. In the main function, we call createArray5, and as a result, the compiler creates an array of 5 integers. The use of len allows us to fetch the length of the array easily, demonstrating how compile time values can enforce safer and more efficient memory management. This code snippet illustrates the power of compile time function execution, enhancing performance by reducing runtime overhead. The explicit definition aids in type safety, ensuring that the developer has declared the array's size clearly and avoids potential runtime errors. Now let's see how we can implement a fixed array struct that leverages compile time capabilities in Zig. This struct contains a fixed size array of i32 integers where the array's size is determined at compile time. The primary function within this struct, initialize, takes an integer value and populates the array with that value. By creating an instance of fixed array, we gain a clear and strict interface regarding what can be parsed and stored, ultimately minimizing potential runtime errors. The initialize function begins by creating an instance of fixed array and initializing the data field to an array of zeros. It then uses a loop to iterate through each element in the array, assigning the specified value to each element. This approach not only highlights the flexibility of struct definitions in Zig, but also demonstrates how compile time functions can enhance safety by ensuring that the array's size and contents are predetermined during compilation. In the main function, we call initialize with the value 42, and as we print each element of the array, we see that the array is effectively filled with this value, emphasizing the importance of compile time structure in both performance and clarity. Now let's take a look at the implementation of a compile time generated lookup table in Zig. This code defines a lookup table struct that leverages the comptime feature to generate an array of squared values. The generate function initializes a lookup table instance, where an array data of 10 unsigned 32-bit integers is created. During the execution of this function, a loop iterates over the data array, squaring each index and assigning it to the corresponding element. This computation occurs entirely at compile time, which means that by the time our main function runs, the lookup table is already populated with its final values, 0, 1, 4, 9, 16, 25, 36, 49, 64, and 81. This implementation not only avoids runtime computation, enhancing performance, but it also showcases the advantages of using compile-time functions for generating static data structures efficiently. Finally, the main function iterates through the lookup array to print out each squared value, demonstrating how this pre-computed table can be accessed at runtime without costly calculations. Now let's take a look at how to implement a generic max function that effectively demonstrates Zig's compile-time type capabilities. In this example, we define the max function, which takes a type parameter t specified with the comptime keyword. By declaring t as a type, we inform the compiler that it will be a fixed type when the code is compiled. This allows the function to work seamlessly with any comparable type, showcasing the flexibility that generics provide. The max function accepts two parameters of type t, and utilizes a basic conditional statement to determine which value is larger. This simple yet powerful design not only adheres to type safety, but also ensures that the correct implementation is generated at compile time for the given types. Next, we call the max function in the main function with both u32 and f32. The results reveal the correct maximum value for each data type. This approach exemplifies how Zig's generic programming features enable the creation of reusable components while optimizing performance through compile-time calculations. In summary, using compile-time functions in Zig can completely change the efficiency and safety of your code. By declaring variables and functions with comptime, the compiler can execute certain computations during compilation rather than at runtime. This not only enhances performance but also allows for greater type safety and more flexible programming paradigms. Zig's compile-time capabilities give programmers the tools to define complex types, generate arrays, create lookup tables, and build generic functions, powerful features in the toolbox of any developer. So we've covered a lot today about how the comptime keyword in Zig enables compile-time execution, allows for the creation of flexible and efficient code, and dramatically improves performance by shifting work from runtime to compile time. Now as you continue exploring Zig programming, keep in mind how you can maximize the use of comptime to write cleaner, faster, and more efficient code. Happy coding! Today, we're diving into the world of advanced compile-time expressions in Zig. This topic is vital for understanding how to optimize your code even further, leveraging powerful compile-time capabilities to produce efficient, safe, and flexible programs. So far, we covered the fundamentals of compile-time functions in Zig, focusing on how they allow computations to be performed during compilation rather than at runtime. This ability enhances performance and safety by enabling more efficient code generation, enforcing type safety, and showcasing techniques like calculating factorials and generating lookup tables. Now, we will talk about advanced compile-time expressions and explore their nuanced applications, showcasing how they can make your code even more powerful and expressive. Now let's take a look at how we can implement a rectangle struct in Zig that utilizes compile-time expressions for calculating both area and perimeter. In our code, we define the rectangle struct with two fields, width and height, both of type U32. This structure not only provides a clean way to represent a rectangle's dimensions, but also encapsulates methods for computing its area and perimeter. Next, we create an instance of the rectangle struct called rect1, where we set the width to 10 and height to 5. By calling the methods area and perimeter, we compute the rectangle's area and perimeter at compile time, and these computed values are stored in area 1 and perimeter 1. This optimization minimizes runtime overhead since the calculations are resolved during compilation, ensuring that we only deal with fixed values during execution. Finally, in the main function, we utilize std debug print to display the results, showcasing the effectiveness of using compile-time expressions in optimizing performance and enhancing code clarity. This approach not only makes the logic straightforward but also emphasizes the benefits of compile-time calculations in practical applications. Now let's implement the following code to illustrate a simple logging mechanism utilizing compile-time conditional expressions. In this example, we define a constant enable logging that determines whether logging will take place. The log function takes a message as input and checks the value of enable logging before printing the log to the debug output. If logging is enabled, it outputs the message using the std debug print function. This setup allows us to enable or disable logging easily by changing the value of enable logging. For instance, setting it to true includes the logging code in the compilation, while setting it to false excludes it, streamlining the program and ensuring that unnecessary logging code does not bloat the final output in release builds. In the main function, we use the log function to display messages indicating the program's progression, demonstrating how conditional compilation can keep logging tidy and efficient during development. This technique enhances code configurability and promotes a clean separation between debug information and production code. Now let's take a look at an example that demonstrates how to create a flexible data structure using compile-time type generation in Zig. We'll define a function, createVector, which takes two parameters, a type t and a size n. This function generates an array of type t with a length of n during compile time, thereby ensuring type safety while maximizing flexibility. Next, we implement the main function where we call createVector twice, once with the type u32 for an integer vector and once with f32 for a floating point vector, both of size 5. This showcases the versatility of our createVector function in producing multiple types of vectors efficiently. Finally, we utilize the standard library's debugging function to print out each vector, demonstrating how both vectors are successfully created and can be manipulated as expected. This highlights Zig's capability to handle different data types through compile-time evaluation, leading to safer and more reusable code structures. Now let's take a look at an advanced technique for optimizing performance in loops through manual loop unrolling. In this example, we define a function called sum that accepts an array of unsigned 32-bit integers and computes the sum of its elements. Instead of iterating through the array one element at a time, we improve efficiency by processing 4 elements simultaneously. Inside the loop, we check if the current index, I, is divisible by 4, indicating the start of a new group of 4 elements. If so, we add the current value to the total sum and also include the subsequent 3 elements if they exist within the array's bounds. This method reduces the total number of iterations and operations needed, allowing the compiler to better optimize the execution of the array accesses. Finally, in the main function, we declare a constant array of integers and pass it to the sum function. The computed result is then printed to the debug output. This approach showcases how compile-time evaluations and loop unrolling can significantly enhance performance in scenarios where the array size is predictable and known in advance. Now let's implement the following code that introduces static assertions to validate conditions at compile time. We begin by defining a static assert function, which takes a Boolean condition as an argument. If the condition evaluates to false, an error is triggered using the @CompileError directive, effectively halting the compilation process. This mechanism helps to catch discrepancies early, ensuring our code adheres to the expected contracts. Next, in the main function, we are asserting 2 conditions. First, that the size of u32 is exactly 4 bytes, which is critical for compatibility in many applications. And second, we check that u32 is indeed classified as an integer type. These assertions serve both as documentation of our assumptions and as safety nets against unforeseen errors that could arise from type misuse. If either assertion fails, the compilation will stop, and a meaningful error message will be presented, allowing developers to quickly identify and rectify issues before reaching runtime, ultimately enhancing reliability in our codebase. If both assertions pass, we print a message indicating success, assuring us that the expectations set in the code are met. Now let's see how we can implement a macro to streamline the creation of getter and setter functions for struct fields in Zig. In the code, we define a macro called getSet, which takes a field name as an argument. This macro generates 2 functions, a getter that retrieves the value of the specified field and a setter that allows us to update that field. Internally, we have a struct named myStruct, which contains a single field called value. By invoking the getSet macro with value as the argument, we effectively generate the get and set functions for this field. This leads to cleaner, more maintainable code by abstracting away the repetitive boilerplate typically associated with defining accessor methods. In the main function, we create an instance of myStruct, initializing value to 0. We then invoke the set method to assign a new value of 42 to our field. Finally, we use the get method to retrieve and print this value, demonstrating how the macro ensures that our struct's data is accessed consistently and efficiently. This approach not only enhances code readability, but also minimizes the likelihood of errors in managing field access. In conclusion, mastering advanced compile time expressions in Zig opens up many opportunities for optimization, error catching, and cleaner code. By utilizing compile time computations, conditionals, and assertions, you can produce efficient and safe programs that capitalize on Zig's strengths. The exercises we've explored showcase the language's versatility and highlight how compile time expressions can redefine your approach to writing robust applications. As you continue your journey, remember that harnessing these capabilities can lead to cleaner patterns, faster execution times, and an overall more pleasant programming experience. Happy coding! When discussing image processing, it's essential to understand that this field deals with the acquisition, manipulation, and analysis of images. The rise of digital image processing transformed various sectors, making image data easier to modify and analyze than ever before. So far, we learned about advanced compile time expressions in Zig, focusing on their ability to optimize code by performing computations at compile time, enhancing performance and safety. We explored how to create constants, implement conditional compilations, generate custom types, and utilize static assertions to validate type characteristics. Techniques such as loop unrolling and macros were also discussed to improve code reusability and clarity. Overall, mastering these concepts enables the development of efficient and flexible programs while minimizing runtime processing. Now we will cover the fundamental concepts of image processing, including how to manipulate images using various techniques and the algorithms involved. Now let's see how we can implement the conversion of a color image to grayscale using a simple function. We begin by defining the RGB to grayscale function, which takes in three parameters representing the red, green, and blue components of a pixel. Inside this function, we apply a weighted sum to these RGB values, with coefficients reflecting human perception, to compute the equivalent grayscale value. This formula allows us to convert the pixel's color information into a single intensity value that represents brightness. Next, we'll apply this function to a hypothetical image structured as a list of RGB tuples. The image in our example is a 1x3 matrix containing 3 pixel values, each represented as a tuple of RGB colors. To create the grayscale representation, we iterate through each row of the image and apply the RGB to grayscale function to each pixel. The result is a new matrix, grayscale image, which contains the grayscale values instead of the original RGB tuples. This fundamental transformation prepares our images for further processing tasks such as edge detection and segmentation, setting a solid foundation for more advanced image processing techniques. Now let's implement a function that performs two-dimensional convolution, which is essential for applying filters such as a Gaussian blur to an image. We begin by defining the convolved function, which takes in an image and a kernel. The dimensions of the kernel and the image are obtained so we can effectively pad the image for border handling. Padding is crucial because it allows us to maintain the original image size after the convolution operation. Once the padded image is created, we initialize an output array filled with zeros, which will store the convolution results. Next, we loop through each pixel of the original image. For each pixel, we extract the relevant portion from the padded image that corresponds to the kernel size and perform element-wise multiplication with the kernel, summing the results to get the new pixel value. This process enhances or suppresses features in the image based on the kernel's coefficients. After defining the function, we set up a Gaussian kernel used for blurring, where the values are normalized to ensure the output image maintains similar intensity levels. Finally, we apply the convolved function to a sample image, resulting in a blurred image that effectively reduces noise and detail, illustrating basic image filtering techniques. Now let's implement a simple canny edge detection algorithm using OpenCV, which will allow us to extract significant edges from an image. The first step in our canny detection function is to read the image in grayscale format, which simplifies the subsequent processing by working with a single channel. We then apply Gaussian blur to the image to reduce noise, yielding a smoother image that aids in precise edge detection. The kernel size of 5.5 and a standard deviation of 1.5 help customize the level of blurring needed. Next, we perform the actual edge detection using OpenCV's canny function. This function requires two threshold values which dictate the minimum and maximum intensity gradients that will be considered as edges. Setting these thresholds appropriately is crucial. In this case, we use 50 and 150 to effectively identify strong edges while minimizing noise. The resulting output is a binary image where the detected edges are highlighted against a black background, making it easier to view and analyze the structural features of the image. This process of edge detection is foundational for multiple higher-level image processing tasks such as object recognition and segmentation. Now let's see how we can implement k-means segmentation to simplify the analysis of an image. First, we import the necessary libraries, NumPy for array manipulation and OpenCV for image processing. We define a function called k-means segmentation, which takes the path to the image and the number of clusters k as inputs. Within this function, we start by loading the image using OpenCV's mRead function, then reshape the image into a two-dimensional array where each row corresponds to a pixel's RGB triplet. To prepare the data for k-means clustering, we convert the pixel values from integers to floats, which is a required format for the OpenCV k-means function. We then define the criteria for the algorithm to decide when to stop iterating, which combines the maximum iterations with an epsilon value. Using OpenCV's k-means function, we apply clustering on the pixel data. This function returns labels for each pixel indicating which cluster it belongs to and the cluster centers. Finally, we use these labels to create a segmented image, where each pixel is assigned the color of its corresponding cluster center. The resultant segmented image can be returned from the function, providing valuable insights into the image's color structure while allowing for further analysis or processing. Now let's implement the following function to compute and display a color histogram for any given image. This function, plotColorHistogram, takes an image path as input, allowing us to read and analyze the image using OpenCV, a powerful library for image processing. First, we load the image with the specified path simultaneously reading its pixel data. Since OpenCV operates in BGR blue, green, red format, we define a tuple containing the order of the color channels. In the subsequent part of the function, we create a new figure for plotting the histograms. For each color channel, we use the calcHist function to calculate the histogram, which quantifies the distribution of pixel values across the channel. The histogram is then plotted using the corresponding color for each channel. By adjusting the x-axis limits, we ensure the histogram fits nicely within the plot. Finally, we add a title to the graph and display it, providing a visual representation of the color distribution in the image. This histogram is invaluable for understanding the image's overall color composition and can aid in tasks like image enhancement or analysis. As we conclude this introduction to image processing, we have covered a range of topics, from the fundamental concepts of pixel manipulation to advanced techniques like feature extraction and segmentation. Image processing is indeed a vast and fascinating field with countless applications, and mastering these basic techniques is vital for progressing to more advanced topics. By deploying techniques like convolution, edge detection, clustering, and histogram analysis, you can achieve a deeper understanding and manipulation of images. This knowledge paves the way for exploring machine learning, where these image processing methods are vital in training algorithms to recognize patterns and make decisions based on visual data. So, I hope you are excited about the potential of image processing. As you dive deeper, remember that every pixel tells a story and your skills can help unravel it. Thank you for joining this tutorial. Keep practicing and soon you'll be crafting images like a pro. Welcome back to our image processing tutorial. Today we're diving into advanced image processing techniques that will elevate your skills to the next level. So far we learned about the core concepts of image processing, including the manipulation of pixels in digital images and the representation of color values in RGB format. We explored techniques for grayscale conversion, image filtering using convolution, and the implementation of edge detection for feature extraction. Additionally, we discussed image segmentation through methods like k-means clustering and analyzed images with color histograms. This foundational knowledge prepares us for advanced applications and techniques in image processing. Now let's see how we can implement a simple image classification task using a pre-trained MobileNet model in TensorFlow. We begin by importing essential libraries such as NumPy and TensorFlow, as well as specific modules to handle image processing and the MobileNet architecture. The MobileNet model, which has been trained on the ImageNet dataset, will allow us to classify images with high efficiency. Next, we load the MobileNet model, specifying that we want to use the pre-trained weights. Then, we proceed to load an image, ensuring we replace the placeholder path with our specific image location. It's crucial to resize the image to 224 x 224 pixels, as this is the input size expected by MobileNet. To prepare the image for prediction, we convert it to an array and adjust the dimensions accordingly, followed by preprocessing, which scales the pixel values appropriately. Once our image is prepared, we utilize the model to predict its classification. The model returns predictions which we decode to extract the top 3 classifications along with their confidence scores. Finally, we loop through these predictions and display the results, providing insights into what the model interprets the image to contain. This method streamlines the classification process, demonstrating the power of deep learning in image analysis. Now let's implement image augmentation using the Keras library to enhance our dataset. We start by importing the Image Data Generator class from TensorFlow's Keras module. This class allows us to apply real-time data augmentation on the training images, which is essential for improving the model's generalization capabilities and reducing the risk of overfitting. Next, we create an instance of Image Data Generator, specifying various augmentation parameters, such as a rotation range of 40 degrees, width and height shifts of 20%, shear, zoom effects, and horizontal flips. These transformations enable the model to learn from different variations of the same image, effectively diversifying our training dataset. After setting up the data generator, we load a sample image and convert it into a NumPy array to prepare it for augmentation. Once the image array is ready, the flow method of the image data generator instance is used to produce augmented images. We set up a loop that displays the augmented images one by one and set a limit to show only the first 20 augmented samples. This process visually showcases the types of augmentations applied and primes our model to handle real-world image variations. Now let's implement a basic example of image stitching with OpenCV. In the code, we begin by loading the images that we want to stitch together into a single panoramic view. The CV2 imRead function is utilized to read each image from the specified file paths, storing them in a list called images. Next, we create an instance of the Stitcher class, which is designed to handle the stitching process. This is crucial because it contains all the necessary algorithms to analyze the images for common features and align them correctly. Now let's see how we can perform the stitching operation using the stitch method associated with our Stitcher object. This method takes our list of images as input and attempts to merge them into a single image. The method returns a status code and the stitch result. If the stitching process is successful, the status will indicate success. Therefore, we check this status, and if it's confirmed, we display the stitched image using CV2 imShow. However, if an error occurs during stitching, perhaps due to insufficient overlapping features, we print an error message. This functionality effectively showcases the power of image stitching and enhances our visual experiences by creating cohesive panoramic views. Next, we will write the following code to create and visualize a voxel grid, a fundamental concept in 3D image processing. The first step involves importing the necessary libraries, NumPy for numerical operations and Matplotlib for visualization. We then create a 10x10x10 NumPy array initialized with zeros, effectively representing empty space in our 3D grid. To demonstrate occupancy, we fill a central cube within this grid with ones, marking those voxels as occupied. Moving on to visualization, we begin by setting up a 3D plot using Matplotlib's projection equals 3D feature. We use NP indices to generate the x, y, and z coordinates corresponding to the shape of our voxel grid. These coordinates allow us to depict the 3D structure accurately. The xVoxels method is employed to render the voxel grid in a three-dimensional space, using the defined coordinates in our voxel data, with black edges for distinct visibility. Finally, we call PLTShow to display the constructed voxel grid, providing a visual representation of the occupied space in 3D, which is crucial for understanding object representation in various applications like medical imaging and gaming. Now let's implement a style transfer technique using TensorFlow. We begin by importing the necessary libraries, including TensorFlow Hub, which provides access to pre-trained models. The first step is to load a pre-trained style transfer model from TensorFlow Hub that simplifies the process of combining the content of one image with the style of another. Next, we need to load our content and style images using a predefined function, load_and_process_image, which ensures the images are processed correctly for the model input. This processing is crucial for maintaining the integrity of the content and styling during transfer. Once we have our images ready, We use the model to perform the style transfer by feeding the content and style images into it. The model processes these images and generates a new stylized image that amalgamates the content of the content image with the artistry of the style image. This transformation yields visually stunning results that often mimic famous art styles. Finally, we display the resulting image using Matplotlib, turning off the axis for a cleaner look. This code encapsulates the essence of style transfer, highlighting the creative possibilities within image processing. Now let's implement a basic example of processing images in parallel to enhance the efficiency of our image processing applications. We start by importing the necessary libraries: OpenCV for image handling, NumPy for numerical operations, and the multiprocessing module to enable parallel processing. Next, we define a function called processImage that takes an image path as an input. Inside this function, we use OpenCV to read the image and convert it to grayscale, a common preprocessing step in image analysis. This function serves as the core of our parallel processing logic, allowing us to process each image individually and efficiently. In the main section of our script, we specify a list of image paths that we will process. This is where you can replace the placeholder names with your actual image files. Using a pool from the multiprocessing module, we create a pool of worker processes, setting the number of processes to 3. This allows us to distribute the workload across multiple CPU cores. Finally, we employ the map method to apply the processImage function across all image paths concurrently. Once the images have been processed, we display each resulting grayscale image in a window, providing a clear visual representation of our parallel processing results. This approach not only speeds up the workflow when handling multiple images, but also effectively utilizes system resources, demonstrating the power of parallel computing in image processing. In conclusion, understanding advanced image processing techniques opens up numerous possibilities, from machine learning applications to creative endeavors such as style transfer. We've walked through a variety of approaches, including model inference with pre-trained networks, image augmentation for dataset enhancement, stitching techniques for panoramic images, 3D voxel processing, and artistic style transfer. Each of these methods showcases the power and diversity of image processing and serves as a stepping stone into exciting fields like computer vision and AI. As you advance in your journey, keep experimenting, learning, and pushing the boundaries of what you can achieve with image processing. Thank you for joining this comprehensive tutorial. Your deep dive into the world of image processing is just getting started. Happy coding! Assembly language serves as a bridge between high-level programming languages and machine code, allowing developers to write instructions that are closely tied to the architecture of the computer. Today we will delve into the introduction of assembly language, focusing on how it empowers programmers to exert fine-grained control of what happens at the machine level. We will explore how to use assembly, its syntax, and provide practical examples to ensure you leave with a solid understanding. So far we learned about advanced image processing techniques, starting with core concepts such as pixel manipulation, grayscale conversion, and edge detection. We've explored applications of machine learning and image classification using pre-trained models, as well as techniques for image augmentation to enhance datasets. Additionally, we discussed image stitching for panoramic views, 3D processing with voxel grids, and creative implementations like style transfer. These foundational skills prepare us for a deeper understanding and application of image processing in various fields. Now we will talk about assembly language and its role in programming. Now let's take a look at a piece of assembly code that demonstrates how we can add two numbers and store the result. We begin by defining a data segment where we declare 3 variables, num1 and num2, to hold the numbers we want to add, and result to store the outcome of the addition. This setup is crucial as it allocates memory for our data. Next, we move to the text segment, where we specify the starting point for our program with the label start. The first instruction we see is mov al num1, which loads the value of num1 into the AL register. This register is part of the x86 architecture and allows for efficient arithmetic operations. The add al num2 instruction then adds the value of num2 to what's currently in the AL register, effectively performing our addition. Finally, we store the result back into memory using the mov result al instruction. This vital step ensures that the result of the addition can be accessed later in the program, demonstrating a fundamental use of data handling in assembly language. This concise code snippet exemplifies the essential operations in assembly, showcasing how direct interaction with CPU registers facilitates powerful computing tasks. Now let's see how we can implement a conditional check based on the result of our addition in assembly language. In this code, we first define a data segment containing a threshold value of 25. This will be used to compare against the result of our addition operation. In the text segment, we start by moving the value of num1 into the AL register and then add num2 to it. The result of this addition is now in the AL register. Next, we utilize the CMP instruction to compare the result stored in AL with our predefined threshold value. This comparison is crucial because it allows us to make decisions in our program flow. If the result is greater than the threshold, the JG instruction, meaning jump if greater, redirects the execution to the label above threshold. This is where you can add any specific code that should run when the condition is met. Conversely, if the result is not greater than the threshold, the program will continue to execute the subsequent instructions, which in this case handle a standard exit with an exit code of 0. Thus, this code effectively demonstrates how conditional branching can be implemented in assembly language, showcasing its ability to manage program flow based on arithmetic outcomes. Next, we will write the following assembly code to print "Hello World" to the console using system calls in a Linux environment. This code begins in the data section, where we define a message that includes our output string and a new line character to ensure the cursor moves to the next line after printing. We then calculate the length of this message with the ec directive, which will help us specify how many bytes we want to write to standard output. Moving to the text section, our program starts with the start label, which serves as the entry point for execution. We prepare for the system call by placing the appropriate values in the registers. The mov instruction is used to load the syscall number for syswrite into the EAX register, which tells the operating system that we want to perform a write operation. The EBX register is then set to 1, indicating that we are writing to standard output. We use ECX to point to the message we wish to output and EDX to specify the message length. Finally, we invoke the int0x80 instruction. This generates a software interrupt and transfers control to the kernel, allowing the system call to execute. After printing the message, the program exits cleanly by calling the exit system function, ensuring the program terminates properly. Now let's take a look at how we can implement inline assembly in Zig to perform a system call that prints a message to the console. In this example, we define a constant string MSG containing the text "Hello Zig World" and calculate its length. This is achieved by using the @int from ptr function to get the pointer's value and adding 16 to account for the string's length. Next, we use the asm keyword to insert inline assembly code for the system call to write the message. The mov instructions set up the necessary registers: rax for the syscall number, RDI for the file descriptor representing standard output RSI to point to our message, and RDX for the message's length. This way we prepare the processor to execute the syscall, which is invoked with the syscall instruction. Finally, the program exits cleanly by performing another syscall, this time to exit with a return code of 0. With this code, we effectively harness low-level assembly instructions while still working within the high-level confines of Zig, achieving both performance and control over the output. In summary, both assembly language and inline assembly empower developers to craft code that can execute with efficiency, giving them the reins to directly control the machine code that is generated. With assembly, we can optimize for speed, tweak performance, and manage system resources at a granular level, which can be essential for performance-critical applications. In our next sections, we will continue exploring assembly language, diving deeper into optimization techniques, exploring more complex assembly constructs, and understanding the intricacies of different assembly language syntax across various architectures. Whether you are working on systems programming, developing embedded applications, or simply looking to deepen your programming knowledge, mastering assembly language offers invaluable skills that aid in understanding how computers work beneath the hood. Inline assembly is an expression which returns a value and enables programmers to embed assembly language instructions directly within a high-level programming language. This powerful feature allows developers to optimize performance-critical sections of their application, bridge the gap between high-level abstractions and low-level hardware controls, and unlock the full potential of the underlying architecture. So far, we learned that assembly language acts as a low-level programming interface, closely relating to machine code and optimizing program performance through direct control of hardware. We explored fundamental assembly concepts, including instructions, registers, and flow control, using code snippets for practical illustration. Additionally, we looked at system calls and inline assembly within high-level languages like Zig, highlighting their benefits for precise machine-level operations. This foundation prepares us for advanced topics in assembly language optimization and application. Now, we will cover inline assembly syntax and usage, diving deep into how it works and how you can leverage it in your projects. Now let's see how we can implement a simple addition operation using inline assembly in Zig. In this code, we start by importing the standard library which provides essential functionalities for our program. We define the main function where we declare and initialize two variables, a and b, which hold the values we want to add, 10 and 20 respectively. Next, we introduce a variable result to store the sum of a and b. The inline assembly block is where the magic happens. It uses the asm keyword followed by the assembly instruction add. This instruction adds the value of the second operand b to the first operand a while storing the result in the result variable. The equals a output operand notation signifies that we want to output the result into a register, while the input operands a dictate which registers to read values from. Finally, we utilize std debug print to elegantly display the sum, demonstrating the seamless integration of high-level Zig with low-level assembly instructions. This approach highlights how inline assembly can be leveraged for efficiency while maintaining clarity in our code. Now let's take a look at how to calculate the square of an integer using inline assembly in Zig. In this code, we define a function named square, which takes a 32-bit unsigned integer value as an argument. Inside the function, we initialize a variable called result, which will store the calculation's output. We then employ inline assembly with the asm keyword, where we specify the assembly instruction emul%1%0. This instruction represents integer multiplication, effectively multiplying the value by itself. The use of %1 indicates the input operand, the value passed to the function, while %0 refers to the output operand, which is where the result will be stored. After the inline assembly block executes, we return the result, providing an efficient way to compute the square of the integer. In the main function, we define a constant number, set it to 5, and call the square function. Finally, we print the squared value, illustrating how the use of inline assembly can optimize performance while keeping the code clean and straightforward. Now let's take a look at how we can interact with the CPU's registers directly using inline assembly in Zig. The configure CPU function provides a compelling example of this interaction. Here, we are leveraging the asm statement to embed assembly instructions directly into our Zig code. The first instruction, movex0x1234, loads a specific configuration value into the EAX register. This allows us to directly set the state of the CPU at a low level, which high-level abstractions typically conceal. Following that, the outdx-al instruction sends the lower byte of the EAX register to a specific I/O port identified by the DX register, enabling communication with hardware components. This direct manipulation is critical for performance-sensitive applications where efficiency and control over hardware behavior are paramount. After calling configure CPU, we print a message indicating successful configuration, reinforcing the function's role in hardware interfacing. By understanding and utilizing these concepts, you can expand your programming capabilities to optimize low-level operations effectively. Now let's take a look at a practical example that demonstrates how inline assembly can be integrated effectively within a Zig function. In the possible failure function, we initialize a variable number and set it to 0. This is critical for our next step, where we use an inline assembly instruction to create a debug breakpoint. When number equals 0, the assembly instruction int3 is invoked. This is a special instruction that causes the program to trigger a breakpoint, allowing us to halt execution and inspect the state of the application during debugging. By incorporating this low-level operation, we seamlessly integrate a powerful error-checking mechanism into our code without cluttering our high-level logic. Additionally, if number were not 0, the code would simply proceed to execute any further processing logic. This illustrates the elegance of combining the straightforwardness of high-level constructs with the precision of inline assembly. By strategically placing such critical checks in our code, we maintain clean abstractions while allowing for immediate intervention when necessary. This approach empowers developers to track down potential issues more efficiently, especially during debugging processes. As we draw our tutorial to a close, it's vital to remember a few best practices when using inline assembly. Always encapsulate inline assembly blocks for clarity and maintainability. Try to minimize the amount of inline assembly code to only what is necessary, This helps keep your overall codebase clean and easier to understand. Furthermore, comment extensively on any segment where you use assembly instructions, as this might be invaluable for anyone reading your code later, including your future self. Harnessing inline assembly effectively requires a solid understanding of your architecture's assembly language and its specificities. Dive into your architecture's documentation, pay attention to the calling conventions, and study examples relevant to your work. Slowly integrating inline assembly into your projects may yield fantastic results when you spot performance issues or need low-level access. In summary, inline assembly is an excellent tool for embedding low-level operations into high-level languages, giving developers the power to optimize critical paths, manipulate registers, and directly interact with hardware. By mastering this feature, you unlock a deeper understanding of how your programs operate under the hood, all while enhancing their efficiency and performance. So go ahead, experiment with inline assembly in your projects and see how it can take your programming skills to the next level. The Zig programming language is an exciting tool for systems programming that emphasizes performance and clarity. In this lesson, we'll delve into some fundamental concepts of Zig, including built-in functions, compile-time parameters, and the importance of knowing how these features work can significantly enhance your programming experience. So far, we learned that inline assembly combines low-level operations with high-level languages, enabling developers to optimize performance and interact directly with hardware. We covered the syntax for using inline assembly in Zig, practical examples of mathematical computations, and techniques for manipulating CPU registers. Additionally, we discussed the importance of careful usage to maintain code portability and readability while emphasizing best practices for integrating assembly into projects. This knowledge equips you with tools to enhance program efficiency and tackle performance bottlenecks effectively. Now we will cover the basics of the Zig programming language, focusing on built-in functions and the significance of the comptime keyword. Now let's see how we can implement a simple program that retrieves and displays the current timestamp using Zig's built-in functions. In the code, we start by importing Zig's standard library with import std, which provides us access to various useful functions for debugging. The main function main is defined to return no value indicated by void. Within this function, we use the built-in function at timestamp to get the current time, which is stored in the variable time. This use of at timestamp directly illustrates Zig's emphasis on efficiency, as it allows us to access system-level functionality without needing additional libraries. Lastly, we utilize std debug print to output the current time in a formatted way, demonstrating how easy it is to print variable values in Zig. This example showcases the straightforward yet powerful nature of built-in functions in Zig, reinforcing how they simplify programming tasks and enhance code clarity without sacrificing performance. Now let's see how we can utilize the comptime keyword in Zig to create a function that squares an integer. In the code, we define a function named square that takes a comptime parameter called x, which is an integer. By using comptime, the value of x is known at compile time, enabling the Zig compiler to optimize the function call efficiently. When we call square 5 in the main function, the compiler resolves this calculation during the compilation stage rather than at runtime. This not only reduces overhead but also enhances performance, critical aspects in systems programming where every cycle counts. Additionally, the main function initializes a constant variable named result that stores the output of the square function. Finally, we use Zig's built-in debugging function to print the result to the console. This approach exemplifies how compile time evaluations can lead to optimized code execution, demonstrating the power of Zig's type system and highlighting the advantage of using comptime for functions requiring compile time parameters. Next, we will write the following code to showcase how to create a dynamic array in Zig using compile time parameters. The function createArray accepts a comptime parameter called size, allowing us to define the array's size during compilation. This is a powerful feature that enhances flexibility while maintaining the advantages of static typing. Inside the function, we utilize the Zig standard library's heap allocator to create an array of unsigned 32-bit integers. If the allocation fails, we handle the error gracefully by printing a message and returning null. In the main function, we invoke createArray with a size argument of 10, demonstrating how easy it is to create and manage a dynamic array. We then ensure that the allocated memory is properly deallocated using the defer keyword, which schedules the destruction of the array at the end of the scope. Next, to populate the array, we use a loop to initialize each element with its corresponding index, casting it to U32. Finally, we print out the contents of the array, showing that this approach combines dynamic memory management with the safety of compile time checks. Now let's take a look at a practical example demonstrating the comptime concept in Zig through compile time conditional logic. In this example, we define a constant named isDebug that indicates whether the debugging features should be enabled. The log message function accepts a message as an argument and checks this constant within an if statement. If isDebug is true, the function will print the provided debug message using Zig's standard debugging print function. This approach effectively reduces runtime overhead by ensuring that debug information is only compiled and executed when necessary, in this case, during development. Consequently, when creating production builds, you can set isDebug to false, allowing for a smaller binary size with no debugging output. By leveraging compile time flags like this, developers can maintain different builds of their applications efficiently, switching features on or off as needed without altering the core logic of the code. Thus, this strategy encourages cleaner code management and performance optimization, which are vital in systems programming. Now let's take a look at an example demonstrating Zig's error handling mechanism through file operations. In this code, we begin by importing the standard library to access essential functionalities like file handling. The main function is declared to return an error type, indicated by the symbol, which signifies that it can either complete successfully or return an error. Next, we attempt to open a file named example.txt. The try keyword is crucial here. It allows us to call std-fs open file and automatically handle any potential errors. If an error occurs during this operation, such as if the file does not exist, the function will stop executing and return that error, providing a clear and efficient way to manage failures without convoluted error codes. After successfully opening the file, we ensure it's closed after usage by employing a defer statement. This guarantees that the file will be properly closed even if an error occurs late in the code. We then read the entire content of the file using another try statement. If reading is successful, we print the content to the debug output, showcasing how Zig's error handling keeps the code clean and straightforward while ensuring robust operation. As we wrap up our discussion on the basics of the Zig programming language, we've covered the significance of built-in functions, the power of the comptime keyword, and the nature of error handling in Zig. From using built-in functions prefixed with the symbol to optimizing functions with compile time parameters and ensuring safer code with clear error handling, these fundamentals empower developers to write more efficient and effective Zig programs. Remember, the next time you sit down to code, these concepts are your toolbox, ready to help you construct the incredibly powerful and efficient systems you envision. Thank you for joining me in this lesson, and I look forward to diving deeper into more advanced topics in Zig. Now let's see how we can implement a simple C header file to perform mathematical operations such as addition and subtraction. We begin by creating a file named mathfunctions.h, which declares two functions, add and subtract, both taking two integers as parameters. This header file allows us to define functionalities we want to utilize in our Zig program while leveraging existing C libraries. Next, we will write the Zig code that imports this C header. First, we import the standard library for debugging output. Using the @c_import directive, we include our C header file with @c_include. This enables Zig to parse the C functions defined in our header at compile time, generating bindings that we can use in our code as if they were native Zig functions. In the main function, we call cImportAdd with two integers to compute the sum and cImportSubtract for the difference. Finally, we print the results using debugging output, showcasing how seamlessly Zig can integrate and utilize C libraries, enhancing our project while maintaining performance and safety. Now let's see how we can create a generic function in Zig to determine the maximum of two values, illustrating the power of compile time types with comptime parameters. We start by defining a function named max, which takes a comptime parameter representing the type t of the values a and b. This means that the function can operate on any data type that supports the greater than operator, making it extremely versatile. Inside the function, we use a simple conditional expression to return the larger of the two values. Next, in the main function, we demonstrate how to use max by calling it with different types. First, we find the maximum of two integers and then the maximum of two floating point numbers. The beauty of this setup lies in its efficiency, Since type resolution happens at compile time, the generated code is optimized for performance while allowing us to write clean and reusable code. The ability to handle different types seamlessly makes generics a powerful tool in Zig, allowing developers to write components that are flexible and efficient in dealing with various data types. Next, we will write a function to generate a Fibonacci sequence at compile time, showcasing Zig's powerful comptime feature. The Fibonacci function takes a comptime parameter n, which determines how long the Fibonacci sequence will be. Inside the function, we initialize an array with the first two Fibonacci numbers, 0 and 1, and then use a loop to calculate the remaining numbers up to n. The loop iterates from 2 to n, with each number being the sum of the two preceding ones. This precomputation happens during compilation, which means the values are embedded in the binary, leading to improved runtime efficiency. In the main function, we declare a constant fib sequence and call Fibonacci 10 to generate the first 10 Fibonacci numbers. The for loop then iterates through fib sequence, printing each number to the console. By constructing the Fibonacci sequence at compile time and leveraging Zig's ability to handle complex data structures, we can achieve both performance and clarity, illustrating the flexibility and advantages of compile-time execution in Zig. This approach allows developers to embed pre-calculated values directly into their programs, reducing runtime overhead and enhancing efficiency. Now let's implement the following code that showcases Zig's memory management features and its defer keyword, which emphasizes safe resource handling. In this example, we first import the standard library and define the main function, where we set up an allocator for dynamic memory management. Here we use the page allocator to allocate a block of memory for an array of 1024 bytes, capturing any potential allocation failures with error handling. If the allocation fails, we print an error message, and the function returns a null value. This approach demonstrates Zig's robust error handling mechanisms, ensuring that your code reacts gracefully to memory allocation issues. Next, we use the defer statement to ensure that the allocated memory is automatically freed when it is no longer needed, regardless of how the function exits, whether normally or due to an error. This pattern reinforces the safety aspect of Zig, preventing memory leaks and promoting clean code practices. Finally, we manipulate the allocated memory by writing a value to the first element and printing it. This simple example illustrates the importance of managing memory in systems programming while leveraging Zig's safety features effectively. Now let's take a look at how we can implement testing in Zig to ensure our code behaves as expected. Zig provides a built-in testing framework that allows you to easily write test cases using the test keyword, promoting better coding practices. In our example, we define two simple test cases, one for addition and another for subtraction. For the addition test, we perform a straightforward operation by adding 3 and 2, then we verify the result using std, testing, expect, which checks whether the outcome matches our expectation of 5. This check not only confirms correctness but also provides immediate feedback if the assumption fails, making it easy to catch errors early in the development cycle. Similarly, in the subtraction test, we evaluate the expression 5 minus 2 and expect the result to be 3. This approach of embedding tests directly in the code allows for a streamlined process where testing is integrated into the development workflow, ensuring that as we modify our functions, we can quickly validate their functionality without additional overhead. By utilizing Zig's testing capabilities, we enhance our code quality and reliability, making our development more robust and structured. Now we've covered a variety of advanced features in Zig, from integrating C code and leveraging generics to exploring compile-time execution, memory safety, and effective testing practices. These elements make Zig a powerful language for systems programming while maintaining clarity and efficiency. Its unique approach allows developers to write expressive and robust code, ensuring high performance across a wide range of applications. In this lesson, we've equipped ourselves with additional tools and techniques that elevate our Zig programming skills. From importing C libraries effortlessly to pre-computing Fibonacci numbers and implementing rigorous testing, we are now more prepared to tackle complex systems programming challenges with confidence and clarity. Thank you for joining me on this advanced journey through Zig, and I look forward to continuing our exploration in future sessions. Let's dive into the world of semantic checking in programming, particularly in the context of the Zig programming language. Semantic checking is a crucial aspect of compiling code, where the program's logic and structure are analyzed to ensure correctness. However, Zig provides mechanisms that allow code to bypass or avoid these checks, which can be advantageous but also requires careful consideration. So far, we learned that the Zig programming language offers advanced features that enhance systems programming, including built-in integration with C code via cimport, which enables seamless use of existing C libraries. We also explored generics with comtime parameters, allowing for flexible and efficient code reuse, exemplified by a generic maximum function and a linked list structure. Additionally, we discussed compile-time execution, which optimizes performance by computing values during compilation, alongside Zig's emphasis on memory safety and built-in testing support that ensures code reliability. These concepts equip developers with essential tools for effective and robust systems programming in Zig. Now we will talk about how certain constructs in Zig can be utilized to avoid semantic checks, and how they can impact your programming practices. Now let's take a look at a simple yet effective implementation using an if statement to determine whether a number is even or odd. In this example, we define a function named decide, which takes a 32-bit unsigned integer as an argument. Within the function, we create a constant called output, which will store the result of our evaluation. The evaluation occurs through an if expression that checks whether the number is evenly divisible by 2. If this condition is true, output is assigned the string even, otherwise it receives the string odd. The beauty of this approach lies in the fact that if the value of x is a compile-time constant, Zig can evaluate the expression at compile time, which enables the compiler to generate optimized code that omits unnecessary runtime checks. Finally, we print the result using Zig's standard library dbg print function, allowing us to see the outcome of our decision process. This method exemplifies how Zig takes advantage of compile-time evaluation, enhancing both performance and clarity in code. Now let's see how we can utilize comptime functions in Zig to enhance our code's performance. The computeValue function, defined to take a compile-time constant Boolean parameter called condition, illustrates a powerful feature of Zig. Depending on the value of this condition, the function returns either 10 or 20. This mechanism allows decisions to be made during compilation rather than at runtime, which can significantly improve execution speed and efficiency. In the main function, we invoke computeValue with a true condition, effectively instructing the function to return 10. The result is then printed to the debug output using Zig's standard library. By leveraging compile-time evaluation, this approach uncouples the logic from runtime constraints, enabling you to produce more generic and optimized code. This exemplifies how employing comptime not only aids in reducing unnecessary runtime checks, but also provides developers with the flexibility to craft sophisticated applications without sacrificing performance. Such constructs empower programmers to exploit Zig's capabilities fully, promoting both efficiency and clarity in their systems programming endeavors. Now let's take a look at how we can implement a function that utilizes compile-time evaluation to optimize code performance. In this example, we define the printType function, which leverages a switch statement to handle different types provided at compile time. The key here is that the type T is specified as a compile-time type, allowing the compiler to determine the correct code path during compilation rather than at runtime. When we call printType with types such as U32 and F32, the respective branches of the switch statement are executed without incurring the overhead of runtime semantic checks. This results in enhanced performance because the code paths are established beforehand, allowing for faster execution when the program runs. Moreover, the else case is included to handle any unexpected types, ensuring that our function remains robust while still being efficient. This approach exemplifies how Zig's ability to perform compile-time evaluations can lead to significant optimizations in systems programming, allowing developers to write leaner and more effective code. Now let's see how we can implement the @compile_error function to enhance input validation in our Zig code. In the validation function, we check whether the input number is less than 0. If it is, we deliberately trigger a compile-time error using the @compile_error function, indicating that negative numbers are not allowed. This mechanism ensures that if a developer attempts to call the validateInput function with a negative number, the compiler will abort the build, providing immediate feedback about the error. This approach serves two primary purposes. It helps guide developers during the coding process by enforcing valid input ranges, and it prevents potential runtime issues that could arise from improper inputs. By utilizing @compile error, we can lean on the compiler's strictness to maintain code validity, thereby reducing the risk of unexpected behavior during execution. Ultimately, this technique exemplifies a proactive stance towards error handling in the development lifecycle, aligning with Zig's philosophies around safety and reliability in systems programming. Now let's take a look at how we can utilize the @compile log function in our code to enhance our debugging capabilities during the compilation process. In this example, we declare a variable count of type U32 and initialize it to 5. This serves as our starting point for demonstrating compile time logging. Next, we employ the @compile log function to log the value of count before it undergoes any modifications. This allows us to see the initial state of count during compilation, providing valuable insights into its value at this stage. After logging the initial value, we increment count by 1, altering its state for subsequent evaluation. Following the increment, we once again use @compile log to output the updated value of count. This log serves as a representation of the state change and reinforces how @compile log can be utilized to monitor values throughout the compilation phase. Finally, we print the final value of count using std debug print, demonstrating that while the compile time logs do not affect runtime execution, they are instrumental in understanding how our code behaves during compilation. In conclusion, while Zig provides powerful tools for avoiding semantic checks, it's essential to use these features judiciously. They can offer performance benefits and allow for highly optimized code, but they also require careful planning and validation. By understanding how to leverage if statements with compile time constants, comptime functions, and other compilation mechanisms like @compile log and @compile error, you can write efficient and effective systems code. As you explore these features, always remember that clarity and maintainability are just as critical as performance. So next time you write Zig code, consider how these constructs can help form robust and efficient systems while keeping your code safe from the pitfalls of omission. Happy coding! Now let's take a look at how to utilize the @compile log function to observe compile time values. In this example, we begin by importing the standard library and defining our main function where we declare two constants, value 1 and value 2. These constants are assigned values of 42 and 24, respectively. Next, we employ the @compile log function to log messages during the compilation phase rather than at runtime. This allows us to see the values of value 1 and value 2, as well as their sum directly in the compilation output. Unlike traditional print statements that execute when the program runs, @compile log provides immediate feedback during the compilation process, enhancing our debugging capabilities without affecting runtime performance. By utilizing @compile log, we can effectively verify and understand the values of our constants without modifying our code for debug purposes, thus maintaining the purity of our implementation while gaining insights into our program's behavior during compilation. This approach not only optimizes our coding process, but also highlights the powerful compile time functionalities that Zig offers. Now let's see how we can implement a function that validates age inputs using the @compile error utility in Zig. The validateAge function checks if the provided age is within an acceptable range, specifically ensuring it is not negative or unrealistically high, such as over 130. If the age fails either condition, the function triggers a compile time error with a message indicating what went wrong, effectively stopping the build process. This acts as a safeguard against invalid data before the program even runs, much like having a personal bodyguard for your code to ensure only valid entries are processed. In the main function, we call validateAge with an age of -1, which clearly violates the constraint set within our validation logic. When this code is compiled, the Zig compiler will issue a compile error, stating that the age cannot be negative. This illustrates not only the functionality of @compile error, but also the importance of implementing robust validation mechanisms in your code to prevent runtime errors and ensure that only acceptable data moves forward. This practice can be particularly beneficial in larger applications where user input can vary significantly. Now let's examine how we can compute the factorial of a number at compile time using the capabilities of Zig's comptime. Here, we define a function called factorial that takes a compile time constant n as an argument. This is denoted by the comptime keyword in its parameter list, allowing the function to execute evaluations during the compilation phase rather than at runtime. The factorial function uses a straightforward recursive approach, returning 1 when n equals 0, and otherwise it calculates the factorial by multiplying n with the factorial of n1. In the main function, we now take advantage of this compile time capability by calling factorial 5. The result of this computation, which equals 120, is determined before the program even runs, effectively eliminating the overhead typically associated with runtime calculations. Finally, we use the std debug print function to display the result, showcasing the calculated factorial alongside informative output. By leveraging comptime, we not only improve performance but also demonstrate the power of making decisions before execution, which is a hallmark of efficient programming in Zig. Now let's see how we can implement a generic function that finds the maximum value from a slice of any comparable numeric type. In this example, we define a function called maxValue that takes two parameters, a type t, which is specified at compile time, and an array of type const t. This setup allows the function to be reusable across different numeric types without the need to write separate implementations for each. Inside the function, we start by initializing a variable max to the first element of the array. We then iterate through the array to compare each value against max. If we find a value greater than our current max, we update max accordingly. This process continues until we have examined all the elements in the array. After completing the loop, we return the maximum value found. In the main function, we declare an array of unsigned integers and call maxValue with the type u32. The result is stored in maxNum, which we print out to demonstrate our generic function's capability. This highlights the flexibility of generics in Zig, allowing us to seamlessly work with various data types in our functions while maintaining type safety. Now let's implement a utility function that utilizes Zig's @sizeOf feature to print the sizes of various data types at compile time. The function printTypeSize takes a type parameter t and calculates its size using @sizeOf_t. By doing so, we can effectively determine how much memory each type consumes, which is vital in systems programming where memory management is a key concern. Within the function, we then use std debug print to output the type name and its corresponding size in bytes. This is incredibly useful for developers who need to be aware of memory allocation, especially when working with low-level data structures or optimizing performance in critical systems. Next, we define the main function where we can test printTypeSize by passing in different built-in types such as u32, f64, and bool. Each invocation will trigger a print statement displaying the name and size of the respective type, allowing us to easily compare them. This approach not only deepens our understanding of type sizes in Zig, but also reinforces the significance of efficient memory usage in programming. Now let's take a look at how we can leverage enums in Zig to manage related constants more effectively. In this example, we define an enum called color that includes three distinct constants, red, green, and blue. Enums provide a structured way to handle these values, enhancing the readability of your code and ensuring type safety. Next, we implement the function printColor, which accepts a color enum value as a parameter. Inside this function, we utilize a switch statement to determine which color was passed in. Depending on the value of the enum, the corresponding message is printed to the debug output using the standard library's std debug print function. This approach not only allows us to clearly represent the different colors, but also eliminates the need for ambiguous strings or magic numbers. Finally, in the main function, we call printColor with the enum value color green, demonstrating how easily we can reference our defined constants. This use of enums facilitates better code organization and improves maintainability, making it a valuable feature when working with related states or configurations in our Zig programs. Now let's implement a union in Zig, a powerful feature that enhances type flexibility while conserving memory. In this example, we create a union type named data, which can hold either an integer i32, a floating point number f32, or a string represented as a slice of unsigned 8-bit integers. This design allows us to efficiently manage different data types using a single variable. Next, we will write the printData function, which takes an instance of the data union as an argument. Within this function, we utilize a switch statement to determine the current type held by the union. Depending on the value type, we print an appropriate message. This approach eliminates the need for excessive type checking, since each case in the switch corresponds to a specific type defined within the union. Lastly, in the main function, we demonstrate how to utilize the printData function with different instances of the data union, showcasing its capability to handle various types in a concise manner. This implementation underscores the synergy between unions and switch statements in Zig, allowing for an elegant and efficient handling of diverse data within a unified structure. As we wrap up our deep dive into advanced features and functions in Zig, it's apparent that these tools and constructs greatly enhance both performance and flexibility. By effectively using compile-time functions, logging utilities, generics, and unions, you can write cleaner, more resilient, and efficient code. However, remember that with great power comes great responsibility. Balancing performance with maintainability and clarity is key. So that's a wrap. You've read about powerful constructs that Zig offers, from compile log to unions. As you implement these features in your projects, think of ways to enhance not just the performance but also the overall architecture of your applications, keeping them robust and maintainable. Happy coding, and see you in the next video. Understanding the Zig programming language and its built-in functions can feel like navigating through a labyrinth, but don't worry, I'm here to guide you through each twist and turn. Today, we're diving deep into the core functions that make Zig not only powerful but also a joy to use for systems programming. So far, we covered advanced features of the Zig programming language, focusing on tools that enhance performance like compile log for debugging, compile error for enforcing conditions, and comptime functions for compile time evaluations. We also explored generics for reusability and built-in capabilities like size of, enums, and unions, all improving the quality and performance of our code. Now we will talk about built-in functions specific to memory operations, including the essential @memcp, @memset, and @memove, their uses and why they matter. Now let's see how we can implement the @memcp function to copy memory in Zig. In this code, we declare a source array called source data initialized with 5 bytes, 1, 2, 3, 4, and 5. This array serves as the origin for our copying operation. Next, we create an empty destination array named dest_data, which will hold the copied values. To perform the memory copying, we use the @memcp function, passing references to both dest_data and source data. This function is designed to copy bytes efficiently from the source to the destination, ensuring that the destination has enough space to hold the copied data. After the memory operation, we utilize Zig's debugging capabilities to print the contents of dest_data. The output should reflect the bytes that were copied from source data. By employing @memcp, we enhance performance by executing bulk memory operations, which are typically faster than iterating through each element manually. However, it's crucial to ensure that the source and destination arrays do not overlap to avoid undefined behavior, a consideration important in low-level memory management. Now let's see how we can implement the @memset function to zero out the contents of an array. In this example, we begin by declaring an array named data, which is defined but initially contains garbage values. This is where @memset proves to be invaluable. By calling @memset and data 0, we are instructing the program to set every element in the data array to 0. This action is crucial as it effectively initializes the array, preparing it for further use without the worry of residual garbage data causing unexpected behavior. When we run this code, we use std_debug print to display the contents of the data array, which will reveal an array full of zeros, showcasing how @memset can seamlessly reset memory within an array. It's important to understand that while @memset is a powerful tool for initialization, if you're working with sensitive data such as passwords or cryptographic keys, it's advisable to utilize more secure methods like std crypto secure 0 to ensure that the information is securely erased from memory. This highlights the importance of choosing the right function based on the context in which you are operating. Next, we will write the following code to demonstrate the @memove function, which is essential when we need to shift data within overlapping regions of memory safely. In this example, we start by declaring an array called buffer, which contains 10 unsigned 8-bit integers with values from 1 to 10. Now let's see how we can shift the contents of this buffer to the right by 1 position. We achieve this by calling @memove with the destination as the address of the second element of the array, and buffer1 and the source as the address of the first element, and buffer0. This operation carefully handles the overlapping memory regions, ensuring that we do not accidentally overwrite data before it has been copied. After executing this operation, the first element will be lost, while the remaining values will shift to the right, creating a new arrangement in the buffer. Finally, we utilize std_debug print to display the modified contents of the buffer, showcasing how @memove effectively manages memory during this operation, especially in applications like circular buffers where overlapping regions are a common scenario. Now that we've dug into these essential memory functions, let's also touch on some best practices. When working with these functions, always make sure to maintain proper size checks to avoid buffer overruns. It's essential to stay mindful of your memory layout to ensure that the element types between source and destination match up, as failing to do so could result in unpredictable behaviors. Moreover, it's good to remember that Zig is designed for low-level systems programming where you frequently work close to the hardware. This gives you granular control, which is both powerful and, if not careful, dangerous. Memory management and error handling are vital components of programming in Zig, and functions like @memcp, @memset, and @memove are your allies when invoking performance optimizations. Now we've covered the memory copying essentials with Zig. You should feel more empowered to manipulate memory effectively. Remember to incorporate these built-in functions into your projects to leverage performance gains. In conclusion, the Zig programming language provides robust tools with its built-in functions for handling memory, significantly enhancing your coding efficiency. Functions like @memcp, @memset, and @memove empower you to manage memory manipulation safely and effectively while ensuring your program runs efficiently. So far, we have covered the intricacies of the Zig programming language's built-in memory functions. Now you can confidently apply these functions in various scenarios, optimizing your code for greater performance and safety. If you have any questions or need clarification on anything, feel free to ask. Happy coding! In this video, we're diving into an essential aspect of the Zig programming language, its built-in functions. Specifically, we'll be discussing a fascinating built-in function that returns the natural logarithm of a floating point number. This function harnesses a special hardware instruction for optimization when it's available, making it an efficient tool in your programming arsenal. So far, we covered the built-in memory functions of Zig, like @memcp, @memset, and @memove, which enhance memory manipulation. With a firm grasp on those essential tools, you're already well equipped to improve efficiency and safety in your projects. Now let's turn our focus to mathematical operations, specifically logarithmic functions, and understand how Zig simplifies complex calculations with its built-in capabilities. Now let's see how we can implement the natural logarithm function using Zig's built-in capabilities. In this snippet, we start by importing the standard library, which provides essential functionalities like the debugging print function. The main function is defined next, where we declare a constant floating point number set to 10. This number will be the input for our logarithmic calculation. We then make a call to the @ln function, passing our number as an argument. This operation computes the natural logarithm of our specified number using Zig's efficient implementation. After calculating the logarithm, we store the result in the variable natural log. Finally, we employ the std debug print function to output the results to the console, formatted to show both the original number and its corresponding natural logarithm. When executed, this code will display that the natural logarithm of 10 is approximately 2.302585, illustrating how easily Zig allows us to perform mathematical calculations while keeping the focus on algorithmic logic. This example serves to reinforce the simplicity and clarity of utilizing Zig's built-in functions for mathematical operations. Now let's see how we can efficiently compute the natural logarithm of multiple numbers using the @ln function. First, we define an array of positive floating point numbers containing 5 elements. This array will serve as our input for logarithmic calculations. Next, we utilize getStdout writer to set up the standard output, allowing us to print the results to the console. We then iterate over each element in the numbers array with a loop. Inside the loop, we check if each number is greater than 0, since logarithms are only defined for positive values. If the condition is satisfied, we calculate the natural logarithm using the @ln function and store the result in the natural log variable. Following the calculation, we use stdout print to display the number and its corresponding logarithm. In cases where the number is non-positive, we print a warning message indicating that the logarithm cannot be computed for the given input. This approach not only demonstrates how to use the @ln function effectively, but also emphasizes the importance of input validation in programming to prevent runtime errors. Now let's see how we can implement the calculation of logarithmic returns based on a series of stock prices. We start by defining an array of stock prices, which in this case includes 5 different values reflecting the price of the stock over time. The code utilizes Zig's standard library to access I/O functions, allowing us to print to the console. Next, we iterate through the prices using a loop that goes up to the second to last price, allowing us to access both the current price and the next price in the sequence. Inside the loop, we calculate the logarithmic return by taking the natural logarithm of the ratio of the subsequent price to the current price. This is done using the built-in @ln function, which efficiently computes the natural logarithm. Finally, for each price pair, we print the current price, the next price, and the computed logarithmic return. This approach not only facilitates the tracking of stock price changes, but also provides insight into the percentage changes while factoring in volatility. Through this implementation, we leverage Zig's built-in capabilities to perform essential financial calculations quickly and effectively. While we've concentrated on @ln for the natural logarithm, Zig has several other built-in mathematical functions that can also streamline your coding experience. Functions such as @sqrt for computing square roots and @exp for computing the exponentials of numbers can be equally essential. For instance, suppose we want to calculate the exponential growth of an investment after several compounding periods. This can be achieved easily using the @exp function along with our logarithmic functions to determine growth factors. Now let's wrap all this up with a deeper understanding of why using built-in functions like @ln is beneficial. When utilizing these functions, you're not just gaining access to mathematical capabilities that are directly expressed. You are also taking advantage of the underlying efficiencies provided by the Zig language, making your code not only cleaner but more performant. It's clear that mastering these built-in capabilities can vastly improve how you approach mathematical problems in programming. You will not only learn how to do complex calculations, but will also understand how to do them efficiently, guarding against common pitfalls like non-positive inputs. As you incorporate these practices into your projects, you will find that your ability to solve mathematical problems in code becomes much more adept and robust. In summary, we delved into the capabilities of the @ln function for calculating natural logarithms in Zig. We examined practical usages, explored underlying optimizations that enhance performance, and even touched on applications in financial modeling. Armed with these insights, you're better prepared for building sophisticated applications that require mathematical computations. Keep leveraging these built-in functions and let them serve as the powerful tools they are in your programming toolbox. Thank you for joining me in this exploration of Zig's built-in functions. Don't forget to practice with these examples and discover new ways to apply logarithmic functions in your projects. Happy coding! Now let's take a look at a practical implementation of memory allocation in Zig using a simple example. In this code, we start by importing the standard library which provides essential features for working with memory. We define the main function where the first task is to select an allocator, in this case, the page allocator, which is adept at managing heap memory. Next, we specify how many elements we want in our array by setting a constant count to 10. We then proceed to allocate memory for an array of integers, specifically i32, using allocator create. This function not only requests memory but also leverages error handling to ensure the operation is successful. After successfully allocating memory, we populate the array with values that correspond to their indices through a loop. This step demonstrates how easy it is to initialize memory once it's allocated. We then print out the contents of the array, showcasing the initialized values. Finally, we highlight the crucial step of freeing up the allocated memory using allocator, destroy, emphasizing the importance of manual memory management in Zig to prevent leaks. This example illustrates both the flexibility and responsibility that comes with managing memory effectively in Zig. Now let's see how we can create a temporary buffer for string operations using stack allocation in Zig. In this example, we define a function called string operation, which takes an allocator as an argument, although we won't use it here since we are allocating on the stack. Inside the function, we declare a buffer of 64 bytes using a stack allocation, meaning it will be automatically deallocated when it goes out of scope. We then define a constant message, hello Zig, and utilize the std_mem_len function to determine its length. The std_mem copy function is employed to copy the message into our buffer, showcasing the ease of memory manipulation in Zig. After populating the buffer, we print its contents, which confirms that the message has been successfully copied. This example elegantly illustrates region-based memory management, emphasizing the safety and efficiency of stack allocations. By managing memory explicitly, we not only ensure our resources are utilized optimally, but also reduce the chance of bugs associated with improper memory handling. This highlights a key advantage of Zig's approach to memory management, allowing for clearer and safer code. Now let's implement a function that elegantly allocates an array while handling potential errors. In this example, we define a function named allocateArray, which takes an allocator and a count of elements we wish to create. By utilizing Zig's error handling mechanism with the try keyword, we ensure that any allocation failure is propagated back to the caller, allowing us to handle the error gracefully when we invoke this function in main. In the main function, we first acquire the default allocator provided by Zig, the page allocator. Then, using the allocateArray function, we attempt to allocate an array of 5 I32 elements. If the allocation succeeds, we then proceed to initialize each element with a multiple of 10 based on its index. This showcases not only the ease of using the try mechanism for error propagation, but also emphasizes the importance of explicitly managing memory. Finally, we ensure to free the allocated memory using allocator destroy, highlighting the significance of cleanup to prevent memory leaks. This code illustrates how Zig promotes safe and efficient memory management practices while providing a clear and structured way to handle errors associated with dynamic memory allocation. Now let's implement a specialized allocator that ensures proper memory alignment for our structures. We begin by defining a function called aligned struct allocator, which takes a pointer to an allocator as its parameter. Inside this function, we first determine the required alignment for our structure, myAligned struct, using the addAlign of intrinsic. This is essential because ensuring the correct alignment can enhance performance, particularly in scenarios where we utilize SIMD operations or when specific hardware constraints are at play. Next, we use the allocator's create method to allocate memory for one instance of myAligned struct, passing the calculated alignment as an argument. By doing this, we explicitly request that the memory allocated adheres to the alignment rules associated with the structure type. If successful, the function returns a pointer to the newly allocated structure. In the main function, we initialize the allocator and call our aligned struct allocator. After successfully allocating the struct, we can assign values to its fields and demonstrate its correctness by printing the values. Finally, we clean up memory by calling allocator destroy, ensuring we manage resources effectively and maintain optimal performance in our application. Now let's take a look at how we can implement a simple pool allocator in Zig. This pool allocator struct is designed to manage a fixed size of memory efficiently, allowing multiple allocations without surpassing the defined limit. At its core, the struct maintains a pointer to a standard memory allocator, a counter for used memory, and the maximum size it can allocate. The init function initializes the pool allocator, setting up the allocator and the maximum size while starting the used memory count at 0. When we allocate memory using the allocate function, we first check if the requested size would exceed the maximum limit. If that's the case, we return an out-of-memory error. If there's enough memory available, we proceed to increment the used count and actually allocate the required memory through the standard allocator. In the main function, we demonstrate how to use the pool allocator. We instantiate it with a 1024 byte limit and then allocate 100 bytes for an array. After printing the allocated address, we ensure to decrement the used count and clean up the memory, preventing any leaks. This approach effectively showcases the efficiency of using a custom allocator tailored to specific allocation patterns, reducing fragmentation, especially in scenarios involving numerous small allocations. In conclusion, mastering memory management in Zig is not just about freeing and allocating memory. It's about understanding how to create programs that are not only efficient but also resilient against the common pitfalls of incorrect memory usage. By learning to handle allocations explicitly, maintain lifetimes manually, and leverage the powerful tools Zig offers, you will be able to write robust libraries and applications. As we explored today, we covered the basic principles of memory management, allocation, deallocation, error handling, alignment, and even custom allocators. This knowledge empowers you to build performance systems tailored to your specific needs. In our next lesson, we will delve deeper into Zig's concurrency model, discussing how to manage threads and synchronize data efficiently in our applications. Thank you for joining me today, and I look forward to our continued exploration of the Zig programming language. So far, we learned about the significance of memory management in software development, particularly in the Zig programming language, where developers must manually allocate and deallocate memory. We explored the use of the STD mem allocator interface for optimized memory usage, including techniques for stack allocation and handling potential allocation errors. Additionally, we discussed the benefits of alignment and the creation of custom allocators to enhance performance and memory management. In the upcoming lesson, we will shift our focus to Zig's concurrency model and the effective management of threads and data synchronization. Now let's dive into an intriguing aspect of the Zig programming language: its interoperability with C. Although Zig is independent of C, and unlike most other languages does not depend on lib, it acknowledges the importance of interacting with existing C code. This interoperability allows developers to seamlessly integrate legacy C libraries into their Zig projects, enhancing functionality without having to rewrite existing C code. Now let's take a look at how we can utilize Zig C-type primitives, specifically the cint type. For seamless interoperation with C in this code snippet, we declare a variable of type cint and assign it the value 42. This is significant as it ensures that the variable adheres to the C ABI, allowing for straightforward communication between Zig and C functions. Next, we use the std debug print function to output the value of A to the console. The use of A within the print statement is a placeholder that will be replaced by the value of A. This demonstrates how easily Zig can handle printing operations while maintaining type compatibility with C. The importance of using types like cint lies in their guaranteed compatibility, enabling developers to effectively pass variables to C functions and maintain data integrity across both languages. With this snippet, we see a practical example of leveraging Zig's type system to ensure a smooth interaction with existing C code, showcasing both the flexibility and power of using Zig for cross-language development. Now let's see how we can enhance our Zig programs by leveraging C libraries using the @c_import feature. The given code begins by importing the standard library with const std import std, which provides essential functionalities for input and output operations in Zig. Next, we declare a constant C that utilizes the @c_import function, allowing us to include C header files directly. Here we include the stdio.h file, which contains the declaration for the C function printf. In the main function, we introduce a call to C printf, enabling us to print formatted output to the console just as we would in C. The string hello from Zig and C is passed to printf, illustrating how easy it is to use C functions within Zig. This integration demonstrates the power and flexibility of Zig's interoperability with C, allowing developers to access existing C functionality while enjoying the expressive syntax and safety features of Zig. Such collaboration enhances our capabilities without needing extensive boilerplate code, making it an excellent choice for developers transitioning from C to Zig or integrating the two languages in their projects. Now let's see how we can leverage Zig C translation CLI to effectively convert a C source file into Zig code. The command zig translate cmifle co output.zig serves as a powerful tool for developers working with existing C codebases. By providing a C file as input with this command, you initiate the translation process. The O flag allows you to specify the output file where the translated Zig code will be saved, in this case, output.zig. This feature greatly simplifies the transition from C to Zig, enabling developers to gradually port their projects. As you run the command, you will notice that it automatically generates equivalent Zig code, which preserves the original structure and functionality of the C code. This is particularly beneficial for large codebases where rewriting code entirely would be impractical. Furthermore, by using additional flags such as target and C flags, you can customize the translation to better suit the needs of your specific platform or project requirements. This capability not only boosts productivity, but also aligns with Zig's goal of combining modern features with the robustness of legacy systems. Now let's see how we can handle C functions that return no specific type in Zig. One effective way to achieve this is by using the any opaque type. This allows us to define an external function that corresponds to a C function returning void. In the provided code, we declare an external function signature pub extern fn some C function, any opaque. The keyword extern signifies that this function is defined outside of the Zig code, specifically within a C context. By specifying any opaque, we indicate that the function does not return a value that we need to use directly, offering flexibility for various C APIs while maintaining type safety in Zig. This integration is invaluable as it enables developers to seamlessly call and interface with a wide array of C functions, expanding the potential for utilizing existing C libraries in Zig projects without the need for extensive boilerplate. This feature exemplifies Zig's emphasis on efficient interoperability, making it easier to leverage C code while enjoying the safety and modern features Zig provides. Now let's see how we can interface with a standard C library for mathematical operations using Zig. The code begins with the @c_import function, which allows us to include symbols from the C header file math_h. This inclusion is crucial as it enables us to access C's built-in mathematical functions directly within our Zig program. Next, we define the main function where we will perform our calculations. Inside this function, we utilize the sqrt function from the C library, passing it the value 16 to calculate the square root. This showcases the seamless integration of C functions into Zig, allowing us to leverage the performance of these well-optimized C routines. Finally, we use Zig's std debug print statement to output the result to the console, formatting it to display the calculated square root. This example elegantly illustrates how straightforward it is to call C library functions in Zig and effectively handle their outputs, reinforcing Zig's role in enhancing productivity while maintaining strong performance through direct interoperability with C code. To wrap it up, Zig's design encourages developers to write new code while allowing them to leverage well-established C libraries, minimizing the workload associated with rewriting existing codebases. This ensures that developers can confidently utilize C libraries without fear of losing the advantages provided by Zig. In conclusion, Zig stands out for its straightforward approach to C interoperability. Whether through C-type primitives, the @c_import feature, or the C translation CLI, Zig provides a rich environment for developers transitioning or integrating projects with C. So far, we have covered the foundational aspects of how Zig handles memory management and its dynamic capabilities. Next, we will explore Zig's concurrency model and how it adeptly manages threads and data synchronization, ensuring you have all the tools at your disposal for developing efficient, modern applications. Now let's write the addition function for our Zig library. We declare a function named add which takes two parameters, both integers denoted as a and b. The function returns an integer that is the sum of these two inputs. By prefixing the function with the export keyword, we ensure that it becomes part of our library's API, allowing it to be easily called from C programs. This is a crucial step as it facilitates interoperability between Zig and C, enabling us to leverage existing C code while utilizing Zig's features for enhanced safety and performance. Next, we will compile our library using the command zig buildlib mathtist, zig. This command will generate a static library that can be linked in our C programs. If we want to create a shared library instead, we simply add the dynamic flag to the command. This flexibility allows developers to choose the right type of library based on their use case, whether for performance or compatibility reasons. Now let's see how we can utilize this library in a C application. In the C code, we include the generated header file to access the declarations from our Zig library. We then call the add function, passing two integers and print the result. This straightforward integration demonstrates Zig's capability to interoperate seamlessly with C, making it a powerful choice for modern system programming. Now let's implement a function that decodes base64 encoded strings using Zig's standard library. The decode base64 function we are defining takes four parameters: a destination pointer for the decoded bytes, its length, a source pointer for the encoded bytes, and the length of the encoded data. Within the function, we first slice the source and destination pointers according to the provided lengths to ensure we only work with the relevant portions of memory. We then utilize the base64 decoder from Zig's standard library, which allows us to calculate the necessary size for the decoded output. The calcSize4Slice method estimates how much space we will need for the decoded data, and if the calculation fails, we use catchUnreachable to handle any unexpected scenarios gracefully. Next, we leverage the decode method from the decoder to transform the base64 input into the decoded output stored in the destination slice. Finally, the function returns the size of the decoded data, enabling the caller to know how much data has been processed. This approach effectively integrates Zig's powerful memory management and error handling capabilities into the base64 decoding process, illustrating how Zig enhances legacy C functionalities. Now let's take a look at how to implement a variadic function in Zig, which allows us to create a function that can accept a variable number of arguments. In this example, we define a function called add that takes an integer count to specify the number of additional cint arguments it will receive. Inside the function, we initialize a variable argument pointer, app, using the @cvar start built-in, which prepares the function to access the variable arguments passed to it. After that, we use defer to ensure that @cvar end is called to clean up the argument pointer once we're done processing the arguments. This prevents any memory leaks or undefined behavior. We then set up a loop that iterates from 0 to count, where each iteration retrieves an integer argument from the variadic list using @cvar_arg, adding it to the cumulative sum. Finally, after summing all the arguments, the function returns the total sum as a cint. This kind of function is beneficial when you want to provide an interface in Zig that closely resembles C's own variadic functions, such as printf, enhancing compatibility and usability in C environments. In summary, Zig offers a unique approach to systems programming with full control over memory management and seamless interoperability. With C, the ability to export libraries with the C ABI opens up a wide range of applications in various programming ecosystems, allowing developers to work efficiently and safely. So, what have we covered today? We discussed how to export libraries from Zig that can be used in C and potentially other languages. We constructed basic and complex functions for demoing integration using Zig, and we also explored variadic functions. What's coming next? We are going to shift our focus on Zig's concurrency model and data synchronization techniques. These aspects are key to understanding how to efficiently manage multiple threads in Zig. Get ready to boost your Zig programming skills. Zig programming language is gaining traction for its efficiency and flexibility in systems programming. Today, we're going to explore a crucial aspect of writing great Zig code, the style guide. These coding conventions are not enforced by the compiler, but they are provided in the documentation along with it for anyone who wishes to adhere to an agreed-upon coding style. This guide aims to improve readability and maintainability of code, while also providing us with a common reference point. Now let's implement a basic structure to illustrate the naming conventions in Zig. The code begins by defining a structure named myStruct. According to the Zig style guide, type names should use title case, which is demonstrated perfectly by this definition. Within myStruct, we declare a field called myField of type i32, adhering to the snake case convention for variables. This reinforces the principle of clarity in code, allowing developers to quickly infer the purpose of each component. Next, we define a public function named myFunction, following the camel case convention for function names. Although the body of the function is not implemented in this snippet, this structure sets the foundation for future functionality. This approach exemplifies the recommended practices of organizing code through clear naming conventions and structuring, which facilitates better understanding and maintainability. By adhering to these guidelines, we create a codebase that is not only readable but also coherent and intuitive for any developer who may encounter it later. Next, we will write the following code to define a simple structure for representing users in our system. This code showcases how we can create a user type, which includes fields for the user's identification number and name. By defining user as a struct, we're encapsulating related data within a single type, thus enhancing clarity and organization in our code. The id field is of type u32, allowing us to store a unique integer identifier for each user, while the name field is defined as a slice of constant unsigned 8-bit integers, effectively allowing us to store user names as strings. This ensures our representation of users is both efficient and flexible. Following the struct definition, we declare an array of user objects called users. This array is initialized with 2 user instances representing Alice and Bob, demonstrating how we can easily create and manage multiple users. This succinct definition of user data emphasizes our earlier discussion about avoiding redundancy in naming. Simply using user rather than user data enhances readability and directly communicates the purpose of the type. Through this code, we establish a clear and effective model for managing user information in our application. Now let's take a look at a practical example that showcases proper formatting as per the Zig style guide. In this example, we have a function named calculateArea that takes 2 parameters, length and width both defined as F32, which is the Zig type for 32-bit floating point numbers. This function's purpose is straightforward. It calculates the area of a rectangle by multiplying these two parameters. We notice how the open brace is positioned on the same line as the function declaration, a recommended practice that helps maintain visual coherence in the code. Inside the function, the return statement provides the computed area by multiplying length and width. Each line of code is indented using 4 spaces, contributing to a clean and organized structure that aligns with the guidelines set forth by the style guide. Following these practices not only enhances the readability of code, but also makes it easier for developers to collaborate on projects by ensuring uniformity across different code bases. Now let's take a look at how to utilize functions effectively while adhering to the line length conventions outlined in the Zig style guide. In the following example, we implement a function call to calculate area that takes 2 parameters, the length and width of a rectangle. To maintain readability and comply with the recommended maximum line length of 100 characters, we've broken the function call into multiple lines. When writing code, it's essential to consider how easily others can read and understand the logic. Here, we see that we've placed each argument on its own line, clearly aligning them with the function name. This structure not only enhances clarity, but also allows anyone reviewing the code to easily identify the parameters being passed without the need to scroll horizontally. By following this style guideline, developers can promote a more user-friendly coding environment, making it simpler for teams to collaborate on projects. Each segment of code communicates its purpose transparently, showcasing how adhering to conventions can lead to cleaner, more maintainable code in Zig. This practice improves comprehension and helps ensure that future modifications can be made with minimal confusion. Next, we will write a function that calculates the area of a rectangle, a fundamental concept often encountered in programming. The function calculateArea takes 2 parameters, length and width, both of which are floating point numbers represented by the type F32. This allows for the measurement of lengths that might not be whole numbers, which is useful in real-world applications. Inside the function, the area is computed by multiplying these 2 parameters together, producing the rectangle's area and subsequently returning this value. Notably, the code includes a comment above the function that succinctly describes its purpose, reinforcing the importance of clarity in code documentation. The single-line comment within the function serves to specify the return value, an approach that adheres to best practices by providing context without stating the obvious. By effectively utilizing comments, we enhance the comprehensibility of the code, ensuring that future readers can quickly grasp its functionality without confusion. This exemplifies how thoughtful documentation and clear code structure contribute to maintainability and ease of understanding in programming. Now let's take a look at a simple example of defining a struct in Zig. In our code, we create a new struct called myStruct. This struct encapsulates 2 fields, id, which is a 32-bit unsigned integer, and name, a pointer to an array of constant unsigned 8-bit integers. This structure allows us to represent a meaningful entity with an identifier and a name, which could be useful in various applications, such as user management or object representation. Next, we adhere to the Zig style guide by placing the struct definition inside a file named myStruct, Zig. This file name convention indicates that the file's primary content is related to myStruct, making it easy for developers to navigate through the codebase. By organizing our files in this manner, we enhance the readability and maintainability of our Zig programs. This structured approach to code organization mirrors the best practices discussed in our previous lessons, making it easier for collaboration and understanding across the team. Now let's take a look at how to import the Zig standard library and utilize it in our program. In Zig, the standard library is integrated using a clear and concise import statement. Here, we declare a constant named std, which will hold the result of the import operation. This makes it easy to reference standard library functions throughout our code. Next, we define the main function, which serves as the entry point for our program. The void return type indicates that this function may return either a successful completion or an error, adhering to Zig's explicit error handling. Within the main function, we use the std debug print function to output a simple message, "Hello world," to the console. The \n escapes the newline character, ensuring that the output appears correctly formatted. This example not only demonstrates the basic structure of a Zig program, but also emphasizes adhering to the Zig style guide by using clear naming conventions for imports and functions. Such practices enhance readability and maintainability in your code, making it easier for both you and your peers to understand. Now let's implement the following code to demonstrate Zig's explicit error handling using the syntax. The code begins with the readFile function, which is designed to accept a file path as an argument, and may return either the file's contents as a byte array or an error if the file cannot be accessed. The use of the try keyword here is significant. It enables the function to attempt opening the specified file and automatically handle any errors that arise during this process. If the file is opened successfully, the function proceeds to attempt reading its entire content into memory. Once we've defined the readFile function, we move on to the main function. This serves as the entry point for our program and contains a straightforward implementation where we call the readFile function, passing it the name of a file, hello.txt. The try keyword is used once again, ensuring that if an error occurs during the file reading process, it will be dealt with appropriately. If all goes as planned, the contents of the file will be printed out to the console. This structured approach not only enhances predictability in error management, but also promotes a clean and manageable flow in the code. Lastly, let's discuss the practice of not solely relying on convention but knowing when to apply common sense. While the guidelines exist for a well-structured codebase, flexibility is key. Sometimes deviations from the standards are necessary to accommodate unique cases while maintaining the intent and functionality. For example, if your project integrates with an existing naming convention that vastly differs from the Zig style guide, it may be better to comply with the established patterns. Balancing conventions with practical usage will further enhance collaboration among team members. In conclusion, adopting Zig's style guide isn't just about following rules, it's about fostering a coding environment that values readability and maintainability. With these conventions as your framework, you can create code that is not only easier to understand but also more enjoyable to work with. So, embrace these guidelines and let your Zig programming flourish. Now let's take a look at how to define a function in Zig using the fn keyword. In this example, we are implementing a simple function named greet that takes one argument, name, which is specified as a pointer to a constant ASCII string. The function itself does not return any value, indicated by the use of the void return type. Within the body of the function, we are using the std debug print function to output a greeting message to the console, enhancing user interaction within the program. The format string hello \n indicates that we will insert the value of name into the output, demonstrating how to effectively handle strings in Zig. This approach illustrates not only the syntax for function declaration, but also the practical use of I/O functions to make our program interactive. Creating such a function is fundamental in programming, allowing you to encapsulate and reuse code effectively. This example serves as a stepping stone for understanding more complex functions and their utilization in broader applications in Zig programming. Next, we will write a simple example using the const keyword to define a constant value. In our case, we are setting pi as a constant with the value of 3.14159. By using const, we ensure that the value of pi remains unchanged throughout the program, reinforcing the principle of immutability that is crucial in maintaining accurate calculations. Now let's see how we can implement a function called calculateCircumference, which takes the radius of a circle as an argument and computes its circumference. The function uses the formula for circumference, which is 2 times pi multiplied by the radius. This method highlights the practical application of constants, as the function relies on pi to ensure that any calculation performed will always reference the correct value. By utilizing the const keyword, we promote both clarity and reliability in our mathematical operations, ensuring that the foundation of our calculations remains intact across the program. This exemplifies how defining constants can lead to cleaner and more maintainable code. Now let's take a look at the add function, which serves as a practical illustration of how to use the return keyword in Zig. This function is defined to accept 2 parameters, a and b, which are both integers of type i32. The primary purpose of this function is to compute the sum of these 2 integers. When the function is called, it executes the expression a plus b, calculating the result of the addition. By utilizing the return keyword, we ensure that the result of this calculation is sent back to the caller of the function. This is essential for any function that aims to produce an output that other parts of the program can use. The beauty of this approach lies in its simplicity. Once defined, the add function can be reused throughout your program, making code more efficient and organized. You can easily call add with different parameters to perform additions as needed, showcasing the modularity and flexibility that functions provide in Zig programming. This example highlights the fundamental role functions play in encapsulating logic and facilitating code reuse. Now let's see how we can implement decision-making in our code using the if and else keywords. In this example, we define a function named checkValue that takes a single argument called value, which is expected to be of type i32. The core of this function lies in its conditional logic. It evaluates whether the provided value is greater than 0. If this condition is true, the function executes the block of code within the if statement, where we utilize std print to display a message indicating that the value is positive. This immediate feedback is important for the user because it confirms the state of the value being checked. On the other hand, if the condition evaluates to false, the program flows into the else block where it prints a different message, that the value is non-positive. This clear distinction between the two paths of execution illustrates how we can effectively control the program's behavior based on variable values, establishing a fundamental concept in programming that helps guide the application's logic and responses. Next, we will write a function that leverages the for keyword to iterate through a range of integers. This function is called printNumbers, and it accepts a single parameter named up_to, representing the upper limit of our iteration. Inside the function, we initiate a for loop that starts with the variable I, initialized to 0. The loop continues as long as I is less than up_to, which we ensure is cast to the correct type using the @int_cast function for compatibility with the loop's condition. With each iteration, we increment I by 1 and print its value to the console using std print. This implementation demonstrates the simplicity and efficiency of the for keyword, which handles repetitive tasks seamlessly. By utilizing this approach, developers can easily perform operations on a sequence of numbers, such as logging or processing data without complicating the code. The printNumbers function serves as an excellent example of how to manage loops in Zig while maintaining clear and readable code. Now let's implement the following example using the switch keyword to categorize numbers. In this function named describeNumber, we evaluate the variable value against predefined cases, which are the integers 1, 2, and 3. When value matches any of these cases, the corresponding message is printed, indicating the number's name, such as 1 for the value of 1 or 2 for 2. The beauty of the switch construct lies in its clean and organized approach to handling multiple conditions compared to a series of if-else statements. If none of the specified cases are met, the else section executes, providing a default message stating not 1, 2, or 3. This fallback ensures that we cover all possible inputs, enhancing the robustness of our function. By structuring the code this way, we significantly improve its readability and maintainability, making it easier to extend with additional cases in the future if needed. This practice is especially useful when you need to compare a variable against numerous potential values, as it streamlines the control flow and logic handling within your programs. Now let's take a look at an essential function that demonstrates error handling in Zig using the try keyword. This function, safe division, takes two integer inputs, the numerator and denominator. The purpose of this function is to perform division while gracefully handling situations where the denominator could be 0, which would typically lead to a runtime error. Within the function, we first introduce a check to see if the denominator equals 0. If it does, we return a custom error called error, divide by 0. This approach is significant because it allows us to communicate the error condition explicitly without crashing the program. By using the try keyword, we can attempt the operation. If an error occurs, it immediately exits the function, simplifying error management by avoiding verbose conditional checks throughout our code. If the denominator is valid, the function proceeds to perform the division by first casting both the numerator and denominator to floating point types. This ensures that the result of the division is accurate within the context of floating point arithmetic. The elegance of this implementation lies in its clarity and the robustness it offers in handling potential failures in division operations. Now let's take a look at how to define complex data types using the struct keyword in Zig. Structs allow us to group related data together, making it easier to manage and organize information in our programs. In the code, we define a struct named point, which represents a two-dimensional point with x and y integer coordinates. This encapsulation of data allows us to create meaningful abstractions, enhancing the clarity and maintainability of our code. Next, we implement the createPoint function. This function takes two integer parameters, x and y, and returns an instance of the point struct initialized with these values. By using the pointxy syntax, we clearly indicate that we are creating a new point instance with the provided coordinates. This approach not only streamlines the management of coordinate data, but also promotes clean and organized coding practices by grouping related behaviors and data structures, making future modifications and enhancements much simpler. In this way, using structs in Zig empowers developers to create expressive and robust applications. Now let's take a look at how we can define and use enums in Zig, which play a significant role in categorizing related values. In our example, we define an enum named color consisting of 3 distinct values: red, green, and blue. This encapsulates the states that the color can represent, enabling us to use meaningful names instead of arbitrary numbers, which enhances code readability. Next, we'll implement the printColor function, which takes a parameter of type color. Inside this function, we utilize a switch statement to determine the specific color being passed. The switch checks the value of color and executes the corresponding case, triggering a print statement that outputs the color name to the console. This method showcases how enums can be combined with control flow structures to cleanly handle different scenarios. Utilizing enums not only adds clarity but also makes our code easier to maintain and debug, as the semantics of the color states are clear and unambiguous. Through this example, you can see how enums enhance the robustness and structure of your Zig applications. Now, let's take a look at how we can utilize the defer keyword within a function to manage cleanup operations effectively. In the example provided, we define a function named example that demonstrates the usage of defer. As the function execution begins, it will first print inside function. This message confirms that the primary operations of the function are being carried out. Now, observe the placement of the defer statement. It is set to execute a print statement displaying exiting function right before the function exits. This mechanism is crucial because it ensures that any necessary cleanup or final messages are handled in a predictable manner, regardless of how the function exits, whether it completes normally or encounters an early return due to some condition. By utilizing defer, developers can maintain clarity and organization in their code, making sure that essential final tasks are executed consistently. This practice enhances robustness and prevents resource leaks by guaranteeing that cleanup code is executed as expected. Thus, the defer keyword proves to be a powerful tool in managing function lifecycles in Zig. Now let's take a look at the comtime keyword in Zig, which plays a vital role in metaprogramming. In the function we'll implement, we define array size, which takes a parameter size of type usize declared with comtime. This allows us to pass a compiletime constant to the function, enabling specific optimizations during the compilation process. When we use the comtime designation, the value of size is known at compiletime, making it possible to allocate an array of that size efficiently. When executing array size, the function returns an array of 32-bit unsigned integers, initialized to 0 with a length equal to the compiletime constant provided. This approach not only enhances performance by avoiding runtime computation, but also allows the compiler to generate more efficient code that works with static sizes. Overall, using comtime serves as a powerful tool for developers, allowing for maximized efficiency and optimized performance in Zig programming. As you implement this functionality in your projects, you'll notice the significant advantages that compile-time constants can provide, helping you write cleaner and more efficient code. This comprehensive guide to Zig's keywords showcases the flexibility and power of the language. From basic structure to advanced concepts, mastering these keywords is essential for any aspiring Zig developer. Each keyword has a specific role, making code easier to read, write, and maintain. By adhering to these principles, you'll be well on your way to creating robust Zig applications. So go ahead and experiment with these keywords in your own projects and unleash the full potential of the Zig programming language. Welcome to this lesson on the Zig programming language, where we'll delve into the fascinating world of containers in Zig. If you've been following along, so far we learned about the importance of the Zig-style guide for improving code readability and maintainability, emphasizing clean naming conventions and effective error handling. We also explored several essential keywords like fn for function declarations, const for constant variables, and return for exiting functions, alongside control structures such as if, for, and switch. Additionally, we covered the try keyword for error handling, struct and enum for data structures, and defer for cleanup operations. Mastering these keywords is critical for effective programming in Zig, aiding in the creation of clear, maintainable, and robust applications. Now we will talk about containers in Zig and how they are central to organizing your code efficiently. Containers in Zig are more than just simple objects, they act as namespaces to hold variable and function declarations. To really understand the crux of what containers are, think of them as organizational units in your code. This makes the code easier to navigate and manage. Zig supports a variety of containers such as structs, enums, unions, and even entire source files. All of these structures use curly braces to define their boundaries, but it's crucial to differentiate these from function blocks or code statements. Containers don't hold statements, they encapsulate structures and types, defining a scope for the declarations within them. Now let's take a look at how we can define a simple point struct to represent a point in a 2D space. The struct consists of two fields, x and y, both of which are 32-bit integers, providing a straightforward way to store the coordinates. Next, we will implement a constructor method called new, which enables us to create instances of point with specified coordinates. This method returns a new point initialized with the provided values, facilitating clear and intuitive instantiation. Additionally, we will create a method called distance. This method computes the Euclidean distance between the calling point instance and another point instance. Inside this method, we calculate the differences in the x and y coordinates, square them, and then apply the square root function to find the distance, which is returned as a floating point number. Finally, in the main function, we'll create two instances of point, p1 and p2, and utilize the distance method to find the distance between them. This simple structure demonstrates how we can work with custom data types in Zig, showcasing encapsulation and method usage that leads to organized and maintainable code. Now let's take a look at how we can define an enumeration in Zig to represent various directions. The direction enumerator is declared to group related constants that denote upward, downward, leftward, and rightward movements. This kind of structure makes our code more readable and self-explanatory, as it allows us to use meaningful names instead of arbitrary values. Next, we'll implement a function named move, which accepts a parameter of type direction. Inside this function, a switch statement is employed to execute different actions based on the specific direction passed in. For instance, if the direction is up, the function will print moving up to the console. This design highlights the advantage of using enums, enabling us to clearly delineate valid movement options, and ensuring that the function can only accept these defined values. In the main function, we demonstrate how to use the move function by calling it with specific direction values such as direction, up, and direction, left. This not only shows the function's versatility but also exemplifies how enums can streamline control flow in our applications, enhancing both clarity and maintainability. Now let's take a look at how to create a union type in Zig with the shape declaration. In this example, we define a union that can represent either a circle or a rectangle. Each shape is modeled using a struct, which enables us to store specific data attributes, such as the radius for circle and the width and height for rectangle. This design illustrates the versatility of unions, allowing us to create a type that can encapsulate different kinds of data while adhering to a single interface. Next, we will implement a function called area that calculates the area based on the shape passed to it. Using a switch statement, we can safely determine the specific type of the shape union. By pattern matching on the union types, we can access the respective fields of the shape and perform the necessary calculations for each case. This approach not only enforces type safety, but also ensures that all possible cases are handled, enhancing code reliability and maintainability. With this pattern, we embrace the power of unions in managing complex data types within our applications. Next, we will explore how to define an opaque type in Zig, which is a powerful concept for hiding implementation details. To begin, we define a type called opaque type using the opaque struct keyword. This declaration signifies that the internal structure of opaque type is hidden from the outside world, allowing us to limit access to this type solely through designated functions. This encapsulation is essential for maintaining abstraction in APIs and libraries, where you want to shield users from the underlying complexities. Now let's implement a function named createOpaque that will allow users to create instances of opaque type. By returning an instance of opaque type initialized with an empty structure, we ensure that external code cannot manipulate or view its internals directly. This design not only preserves the integrity of the data, but also affords us the flexibility to make changes to the internal implementation without affecting any external code utilizing this opaque type. Thus, we achieve a robust and maintainable architecture, minimizing dependencies and potential errors due to direct access. Now let's take a look at a practical example that encapsulates shape-related data using a union in Zig. The code begins by defining a shape union where we can represent either a circle or a rectangle. Each shape type encapsulates its own properties. The circle has a radius and the rectangle features width and height. This approach enables us to create a flexible structure where a single variable can represent different kinds of shapes, enhancing both code clarity and type safety. Next, we can extend this concept by creating functions that operate on the shape union, allowing us to perform operations like calculating the area. Each time we use a shape, we can ensure proper handling through the union's defined types, allowing for concise and meaningful code. By organizing all shape-related functionality in a dedicated file like MyShapeZig, we not only promote modularity but also establish a clear boundary for where shape definitions and functionalities reside, improving the overall maintainability and readability of the codebase. This demonstrates the power of containers in Zig, enabling efficient code organization while fostering strong type safety. In conclusion, containers in Zig are essential constructs that significantly enhance your ability to structure and organize code effectively. We've examined structs, enums, unions, opaque types, and even the role source files play as containers. Each of these types not only encapsulates data but also provides a distinct namespace that keeps your code clean and manageable. As you progress with Zig, utilizing containers will be crucial for developing maintainable and robust applications. With everything we've covered, keep practicing and exploring how these containers can simplify complex problems in your coding journey. Happy coding!